Over the last few years, data science has become one of the fastest growing and highest paying careers in the world. Companies like Google, Microsoft, Amazon, Netflix, Deloitte, and thousands of startups are investing billions in data to make better business decisions. And because of this, the demand for skilled data scientists has never been higher. Today, entry-level data science roles can offer salaries ranging from 6 to 15 LPA in India, while experienced professionals often earn 25 LPA to 40 LPA or even more. Globally, data science continues to be one of the most sought-after careers in technology. But to build a successful career in data science, you need more than just Python. You need a strong understanding of how to work with data and how to extract insights from it. That's exactly what you will learn in part 2 of this course. We'll start with Pandas, where you will learn how to work with real-world datasets and perform data analysis using data frames. Then we'll build a solid foundation in statistics, covering concepts like the central limit theorem, hypothesis testing, z-test and t-test. Finally, we'll master probability and probability distributions, the mathematical foundation behind data science, machine learning and AI. And once you have finished watching both part 1 and part 2, you can claim your course completion certificate. You'll find the assessment link and certificate details in the description and the pinned comment. Let's get started with part 2.
Let's begin. Okay, let's begin. Where was I? Yeah. So Pandas, right? This library called Pandas. The name is derived from panel data. And if you remember in the NumPy sessions, we spoke about 2-dimensional arrays, 3-dimensional arrays, things like that. Panel data is essentially mostly 2-dimensional arrays. Okay, where we spoke about rows and columns and things like that. So Pandas is actually open source Python. The whole of Python is open source, in fact, right? And Pandas, which is built on NumPy, by the way. So it's an open source data analysis and manipulation library for Python, which is built on top of NumPy. Okay. So in other words, when you import Pandas, it actually imports NumPy automatically in the backend. Okay. So it's completely built on top of NumPy. And here the most important thing is the two data structures that we'll be studying. One is Pandas series and the other one is Pandas data frame. Okay, so series is essentially one feature. So it's like, you know, production values or temperature values or revenue values, something. So it's one feature. Data frames will have multiple such features. Okay, it's actually 2-dimensional object data frame. So the one thing I should mention here is that most of the methods and operations which are applied on series is also applied on data frame. The reason for this is that Pandas data frame is nothing but collection of Pandas series. We will see this when we go to data frame, but because the methods are so similar and the application is so similar, we will spend only some time investigating Pandas series. Okay, and the rest of the, you know, experimentation with series, it is left to the audience, right? But we will study Pandas data frame in detail. Okay, and as I said, most of the methods are similar between the two. So once you understand data frame, and when I show you what's happening in data frame, you'll understand even better. Then you will easily be able to, you know, connect all these methods with series methods. Having said that, we will still spend some time you know, doing Pandas series. All right. So again, the expectation is that you run the code along with me so that we are on the same page. Okay, so that we know you know, everything's working out and, you know, we are learning together, right? That's the expectation. So let's import Pandas, and typically when you import Pandas, the you know, the name used is PD. Okay. So first we'll talk about Pandas series. Pandas series is essentially a 1D labeled array capable of holding data of any type. Basically, it's a super array. Okay. Now, if you remember the you know, arrays from the NumPy classes, we'll you know, compare that with the series here. All right. All right. So first, you know, creating series, and I just put this here on purpose so that we get this warning. As you can see, right, it's giving me some warning. It's saying, you know, the default data type for empty series will be object instead of float. Specify a data type to silence this warning. So these kinds of warnings and updates and those kinds of things, right? This is very common in Python because it's an open source language, right? All the libraries also open source. So development keeps happening. right? So don't be surprised if you're getting any of these warnings. No problem. Sometimes you may even get an error. No problem. We just need to find out, okay, what did they change, right? What was the change in the package update or the code update, right? So what you need to do is you need to read it, right? What does it say? It says default data type will be object instead of float, and that obviously object is better. Specify a data type to silence the warning. Okay, this is very common. So what did I do? Now I'll specify data type. Okay, so the command I'm using is pd.series. Note that it's a capital S. Okay, so here empty series equal to pd series, data equal to, I'm saying none, data type equal to int. Okay, I run this. Now if I just print this empty series, what does it say? It says it's a blank series with data type int32. Now if I check the type of this object, it says pandas.core series.series. Okay, so this is actually the class, right? This is the class, and the method to initiate this, an object of this class, is pd.series. All right, you can also print it using the print command, and it will give you the same result. So basically there is this data, and then there's the data type. This much we know. Okay, this much we know from NumPy arrays, that we need to specify some data, we need to specify a data type. Now in NumPy array you can specify data type, it automatically selects best data type also if you don't specify. Now this is where the power of the Pandas series starts becoming obvious. Okay, so suppose I have a list which has kind of some production data. So you can think of this as 1000 units produced by a factory in day 1, 1200 units produced by the factory in day 2, and so on, right? 1100 units produced in day 3. Now if you see here, I have one list which stores the production values. I have another list which tells me the day number. Notice that these are strings, these are integers. Okay, now I have these two lists. What I'm going to do is I'm going to pass the actual values, the production data values, into the data parameter here for series. Let me pass in the days, day 1, day 2, day 3, the string information, the string list, right, in the index parameter. Okay, so here I'm passing production day, and I'm giving a name to the series, right? So there's another optional parameter where you can actually give a name to the series. The name is stored along with the series, right? So this is the name of the variable. So here I'm saying daily underscore production. This is the name of the variable. This would be the name of the series, and this is optional, by the way. So anyway, let me run this. So now the series has been created. You can take a look at it. This is what a typical series is going to look like. Notice that it is different from an array, right? So series is actually a one-dimensional array, but it has labeled indices, not just integer indices. Okay, remember NumPy 1D, 2D, 3D, whatever, these NumPy arrays do not have anything other than integer indices, right? That is how we were indexing 0, 1, 2, 0, 1, 2, 0, 1, 2, correct? So now Pandas series, what it has is it has labeled indices. Okay, that doesn't mean that it does not have integer indices. It has. By default, the position of 1000 is 0, position of 1200 is 1, position of 1100 is 2, and so on. So it has the integer indices. On top of that, it also has label indices. Okay, now if you quickly look at the documentation of this thing, data none, index done, dtype name. Okay, so these are the main things, and you can read this more detail when you want to, but these are the things that typically that one would pass. So now I have this nice labeled map between the object day number 1 and, for example, the amount of units produced on day number 1, which is 1000. Okay, so giving a name is optional, but this is more useful when we study data frames. Okay, we'll see that. And as you can see here, I have not given the name in the second command here. I did not give the name. And this thing here, it says name is production details. So as you can see, this name thing, this name attribute is part of the object. Okay, and here there's no name, right? So for example, if you want to see the attribute, then you just do this, right? Dot name. Okay, let me check. Okay, this thing doesn't have name right now. Yeah, I need to run this again. Then only I will get name. So now if I do daily production dot name, here you will get see name of the object, which is daily production. So notice that this is the variable name and this is the name of the series. It's as I said, it's optional. It will become more important when we do data frames. Anyway, so let me run these two cells again. Now, what else, right? Now, one thing you need to notice is that it's built on top of NumPy, right? So any mismatch in the shape is going to cause a problem. So here, see, I'm taking production data from one to end. One to end means what? We know this by now, right? So if I say one to end, that means this much, right? 6 items, except the 0th item. Okay. So if I pass that as my data, and if I pass the full index, production day is 7 items here, right? So if I pass that as my index, then obviously there's going to be a problem. And by the way, if you retain the correct order of the parameters, then you don't need to specify the parameter name each time, like data index, right? So that I have not used here. So if I run this, it's obviously going to give me error. It says length of value 6 does not match length of index 7. Clearly the index and the data must have same length. So there is one thing you can do is either fix the index properly or you don't even specify it. So actually the index is also optional. Why is the index optional? Because on the back end, integer indices still exist, correct? So if I just declare a new Pandas series with the production data, you see the integer indices 0, 1, 2, 3, 4, 5, 6. Okay, so this is what I mean when I say that Pandas is built on top of NumPy, right? It has all the functionality of NumPy plus more, right? So if you don't specify the index, no problem, integer index, right? And if you don't have any data, then there's no point of having the series. So the main thing is the data. Anyway, so let me redeclare my daily production variable. This time I'll put the data, I'll put the index. Okay, so now I have day 1 1000 units, day 2 1200 units, and so on. And of course this is a Panda series. Now many attributes here, right? And we'll go in more detail for data frames, but as I said, there is a name attribute. Right now if you just run this, you will not get any output. Why? Because we didn't specify any name actually, right? So here if you specify a name and then you declare the variable, right? Then if you do daily production dot name, you will get the name. Right now there is 0 output. The cell is running, but there is 0 output, which means there is no name. If I just do daily production dot index, it gives me the index. If I do daily production dot values, it gives me the values. Okay. And of course you can even check the data type. So daily production dot data type, if you do, it says int64. And as I said, all of this is built on top of NumPy, which means all of this should work. Shape and dim, all of these things should work. So what is daily production dot shape? It is an array of one-dimensional array with 7 elements. And what is this daily production, guys? What is this variable? This is actually the series, right? So on the back end, it's an array, right? I hope now this whole connection is becoming clear. So NumPy is the mathematical foundation. On top of that, Pandas is the connection to data science and data analysis. Okay. And dim also will work. What is the dimensionality of the series? Obviously 1. It has only 1 dimension. What is this? You can even pull out the length using this size command. Okay, it has a size. I think NumPy arrays also have a size. Maybe we didn't explore it, but you guys can check it out later. Okay, I believe it should have a size. Maybe I may be wrong, but yeah, check it out. Then you can even use length, right? If it's a one-dimensional object, you can use len, and len is a Python method, right? It's a basic Python method. So this also gives you 7. So notice, if you want to understand your series and in terms of its attributes, you can use these commands to do that. Shape and dimension, data type, values, index, right? Everything is here. And there's also one quick way to check whether your series is empty or not. So if I just do daily production dot empty, this is what we call a flag in programming. It's called flag. Okay, flag. So this flag is false, which means that my daily production series is not empty. Okay, so if it was empty, you will get true. Fine, great. So Another way of defining series, for example, is to use dictionaries. So here in the previous case, if you saw, we used two lists. Okay, we used two lists, and this list we used for values, that is data, and then this list we used for the index, right? Very nicely, we can connect this with dictionaries. Okay, so suppose I have a data like this, which is monthly expenses. It's a dictionary. As you can see, it's a dictionary. I have the keys January, February, March, April, May, and I have the values 2567, 2809, 3001. These could be in like rupees or dollars or whatever, right? So I've stored my data in dictionary, correct? Dictionary is a basic Python data structure. Again, why should we convert this to series? To do data analysis, right? That's why we're doing basic Python data structures such as list, dictionary, and so on. They are built for general purpose. So now we use those generic things and use more specific libraries like NumPy, Pandas to convert them into objects which allow us to do quick data analysis. So you can directly use this dictionary, and very interesting, right? This is one object, this dictionary is one object. That object I am passing as data. Okay, this one object I will pass as data into pd.series. Okay, now let me print the series. Notice how the index and the values are meaningfully interpreted from the keys and the values of the dictionary. So all your keys of the dictionary goes to the index, and all your values from the dictionary goes to the values. Very interesting, right? Very clean connection between dictionary and series. Okay. And for example, here what I've done, see here I have made a string input for February, and here if you see the data type is float, right? So here for this series the data type is float because all of these values are floating values. Let me use the same thing again, but instead of this 2809 floating value I will put it in quotes, so which is a string right now. Interestingly enough, what happens is the series still allows to be built without any warning or error. Right now it looks like these are still floating values, but notice that the data type of the series has changed to object. So then you might be thinking, all of these things also, did the data type get converted to object? That's what happened in NumPy arrays. When you mixed string and integer and whatever into the same array, then the array automatically takes the best data type to incorporate all the data and converts. Series is actually better than that, right? So for example, if I take the January element, so accessing we will do in more detail, but the way to access is just expenses series, name of the series, and then bracket, and then give the key value, that is Jan, right? So if I take out the Jan, it says float. Type of the Jan element is float. And if I take out February, which is supposed to be float, right? If you remember, this was a floating value, right? 2567, this is a floating value, which means it's a number. Okay, and type of February we specified here as string. So if I print this, it says string. So notice how the series shows object data type. Okay, but all the elements within the series still have their own data type and it is retained. Notice how powerful this is. So this doesn't mean that you should just have January, February, March, April, day 1, day 2, day 3, and then you have same kind of value like revenue, or profit. No, you can actually have mixed information. You can have name of employee, salary of employee, right? Position of employee, location of employee, various data types you can have in the same series, right? So hope we are starting to see why this is important for data handling and data analysis, right? Very powerful object. Okay, so what we did was we looked at some important attributes of series. Okay, you are definitely encouraged to explore series further, but primarily we'll be spending a lot of time on data frames, right? Okay, example 2, some series operations. As I said, we will look at a few operations, okay, but all of these we will look in more detail when we do data frame. So again, I'm going to use daily production. So again, day 1, day 2, day 3, day 4, 1000 units, 1200 units, so on. And what is the name here? Well, it has no name, right? So one interesting method to rename this thing, you can actually rename the series, right? So here if you say daily production dot rename, and then you just give the name. So see, sometimes I'm showing the parameters here, but most methods in Python are designed such that even if you forget the parameter name, it will work. That's how they design the libraries. They make it human friendly. Okay, but still I'm showing the parameter name. So rename and then index equal to, so suppose I want to give the name daily underscore prod. Okay, so now if you see here it says name is daily underscore prod. Okay, this is one way to rename. Right, but if you see here, this is the funny thing, right? If you print this again, where is the name? It is not there because this is not in place operation, right? We spoke about this in place operations, right? You remember? So if you want to make changes directly to your object, most pandas methods give you this parameter option in place. Okay, this will become very important when you work with a lot of data. So same method, daily production dot rename. Okay, and I'm giving the new name. This time I'm saying in place equal to true. Now, if you check the documentation, okay, I'm not opening it here, but if you check the documentation, the default value of in place is false. Okay, why? Because safety. By mistake, what if I change the original data, right? So default is false. So the user has to specifically say in place equal to true. Okay, so now if I say that, of course, the output is the same as previous, right? This output and this output are exactly the same, but my name has now been updated. Okay, so this is to sort of show that, look, in place operations are everywhere in pandas. What most of what you do will not be in place. Okay, similar to NumPy, and this time they actually gave us a proper parameter to control that. Another way to another point is, this is not the only way to make changes, right? You can make changes like this also. Very interesting. So this is temporary, right? This command here, whatever I highlighted, that is the same thing which is here. Okay, so I did not put in place equal to true here, right? Which is why your name did not get updated. But it gives me a temporary output, isn't it? This not in place operation gives me a temporary output. That temporary output I can assign to my original data, and that will replace the original data. So suppose here the name I want to give is prod daily, and I assign this whole output, right, of the temporary output of the operation to the object, right? And then I check daily production name, it is now updated properly. That is another way of making changes. There is still other way of making changes, which is directly changing the attribute. So right now, daily production dot name, this attribute of this object, daily production, is prod underscore daily. You can directly change the attribute of the object. So here, daily production underscore name, I'm giving a new name, which is daily underscore production. Okay, so this I'm using to change the attribute itself. Now if I print the updated attribute, as you can see, the name has been updated. So the point I'm trying to make here is, see, Pandas offers multiple ways to achieve the same effect in many of its methods. Okay, you can directly change the attribute, you can assign the temporary output to the original variable, or you can set in place equal to true. Typically, what we do typically is we try to use the in place parameter wherever we want to change the original object. We will control this parameter typically, but you can use the other methods also, no issues. Okay. And one small thing to notice here is that the very interesting part is that the index of the series has a name and the series can have a different name. Okay, so this is not very important. It's just for people who are interested a little bit more in all these things. You can check these methods. Okay. Now, for example, right now daily production, you see these are the index, right? Day 1, day 2, day 3, day 4, day 6, day 7. There is a method called reset index. So object dot reset index. If I do this, very interesting. What you're looking at here is called a data frame. Okay, we will study this in greater detail a bit later in the session, but this is what a data frame looks like. So look here, this is what a series looks like. Okay, it gives you the index, values, data type, and optionally name. Now this reset index method, what it did was it basically forced my index to become integer. So my previous index was day 1, day 2, day 3, day 4, right? It kicked out that index and stored it as a separate column, and it forced the actual index to become integer. Now if you check the type of this object, so I'll just take this command because it's a temporary output, right? It's not in place operation. So if I copy this whole thing and then again I execute the command and this time I check type, here you will see it says pandas.core.frame data frame. Okay, so this is the thing that we'll be working with a lot. Anyway, so now obviously these are not in place operations again, right? These are not in place operations. So if I print daily production again here, I will get my series, because all of this is like, you know, temporary outputs, not in place. Okay, so currently my index is day 1, day 2, day 3, day 4, whatever. So the same reset index method, if I say drop equal to true, there is a parameter called drop, and I think we can all understand what it's for. It's choosing whether to keep the old index or drop the old index. Okay, so previously I did not specify, right, the drop parameter, which obviously by default is false, which is why the old index has been retained. I can choose to drop it. So if I now drop, as you can see, the old index is gone and you can only see the integer index now, 0, 1, 2, 3, 4, 5, 6. Again, this is obviously not in place. Okay, now if you check the type, and it should be obvious, this by now we know what a series looks like and what a data frame looks like. This is a data frame, this is a series. So if you check the type of this, it will say pandas core series. Okay, and another thing very obvious, that none of these operations is in place. So my original daily production object is still intact. It's still the way it is, day 1, day 2, day 3, day 4, 1200, whatever. All right, and the index is day 1, day 2, day 6, right? So if you want to reset index and you want in place, then you have to choose the correct combination of parameters. So if I say drop equal to true and in place equal to true, and then print the index, now you see the index is a range. Okay, it's not day 1, day 2, day 3 anymore, it's a range index. Okay, and if you print the daily production object at this stage, you can see that it has changed. The object has changed. Now, as I said, there are multiple ways to change things in pandas. In place is one way. I said another way is assigning. So now if I want to assign a new index, what I can do is I can use a list, right? So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, instead of day 1, day 2, day 3, right? So this list I can assign to the attribute itself, right? So daily production, the pandas series object has an attribute called index. So I can change that attribute directly. So here I am assigning this list to this attribute. Currently, what is the attribute or index? 0, 1, 2, 3, 4, 5, 6. That you can see here. Range index, start 0, stop 7, step 1. Okay. So currently this is it, 0, 1, 2, 3, 4, 5, 6. Now I can just assign this and see what happens. As you can see, the new values are updated in the actual variable. Okay. All right. Typically, see, pandas library, as I told you, calls numpy by default in the backend, but we can import it explicitly if we want, which is typically the general practice. Now in this notebook and maybe tomorrow's session, we may not be using numpy more directly, right? But more or less, when you do more advanced analysis, these two things will always be imported. Import numpy as np, import pandas as pd. These two will almost always be imported together. Okay, so for now, let's just import them to, you know, show some things. Basically, I want to show that it's not just lists that you can use for data and index. You can use arrays also, right? So in Python, we call this list-like or array-like objects, right? So many of these packages allow for multiple similar behavior data structures. So when I define the values and the index for the pandas series earlier, I use lists. The dictionary one is separate, that is another method. But if you want to do it separately, I specified lists. That doesn't mean I cannot use arrays. I can use arrays. Okay. So suppose if I have now, you know, employee names Arti, David, Mahmood, and Pranjal. This is an array, and I have employee IDs 7634 something something something. These are also arrays. So these two are actually numpy arrays now. You can use these as data and index also, right? Any list-like object, any array-like object can be used. So notice that the index comes second and the name comes first. Okay, that is something you guys need to remember. The first parameter is the data, the second parameter is the index. So index, what happened? My employee ID went to index and name is my value. Okay, and as I said, you can specify this without any index also, no problem. And if you just pass the array, you will get integer indices. Okay, on which day did my factory produce more than 1000 units? Answer should be Tuesday, Saturday, Sunday, right? So if I just do this, what will you get? False, true, true, false, true, 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 whatever, right? This is exactly like what is that? NumPy, isn't it? Exactly like NumPy. And notice that the output is also a series, right? This output, this logical output, is a series, and the name of the series is still the same, daily production, and data type is Boolean. So when you apply logical operator like this on a series, it will output a series. That is the powerful part, correct? So now I can use this to subset this. Okay, so wherever true is there, it will give me that value. So if I say daily production index with daily production greater than 1000, you will get the subset of the series where the production was more than 1000 units. Very simple. Tuesday, Wednesday, Friday, Saturday, Sunday. Similarly, you can do multiple. So if I have greater than 1000, I have these false, false, true, true, whatever. Less than 1500, I have true, 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 false, whatever, right? Now, if you want to do both of these, you just need to combine the logic, right? You just need to do AND operation between these two if you want both, right? And we've already seen this doesn't work because of ambiguity. So if you do this, it's ambiguous because there's no brackets, right? Which operation to do first. So there's a problem here with ambiguity. Typically, the way to solve is to put your logical operations inside parentheses, brackets, and then you can use AND. So when you do this and this, wherever both are true, only that will be true, which means both conditions need to be satisfied. So both of these conditions, if you satisfy, what is this, 1000 and 1500, right? So if you go here, this should come, this should come, this should come, this should come, right? Tuesday, Wednesday, Friday, Saturday. These four should come. Those are between 1000 and 1500. So now you can use this full logical condition, right? Put it inside indexer, right? Use this for indexing, and then print from daily production, you will get Tuesday, Wednesday, Friday, Saturday. So logical operations, same as NumPy. Okay. Other operations also same as NumPy, max, min, all of these things, right? So if you do daily production dot max, out of daily production, let me just print it again, daily production. Out of these, which is the maximum value? Obviously Sunday, 1760. So daily production dot max gives you 1760. The interesting thing about pandas is there's a nice method idx max, index max, by the way. That's what this method is. It gives you the index where the value is maximum. So now if I ask the question, on which day did my factory produce the maximum number of units? Sunday. Okay, so this function idx max gives you the index where the maximum value is there. Similarly, you can have min. So daily production dot min, if you do, you'll get 950, right? And again, you can use idx min. This is giving you the index of the minimum value. So when did my factory produce the least units in this week? Thursday. So now I can go ask the question, why Thursday, why Sunday, right? This is the beginning of analyzing data, right? So some other methods like sort values, these are very important in pandas. In NumPy, typically sorting we did not look at because it's more of a mathematical structure named NumPy array where I don't want to mess around with my data so much, right? But in pandas, it's perfectly normal. It's expected, right? When you do data analysis, it's expected to do sorting and all of those things. So there's a method called sort values, which sorts the series according to values. Okay, and remember that the output is series. Each time when you apply this function, and these are all built-in functions. So this function is actually built into the object, the daily production object. This is a built-in function. So it will sort the values in this variable. And the output is also series. Okay, now if I do sort values, it is sorting all the values in ascending order along with the keys or the index. And if I just print daily production again, obviously the original object did not change because these are not in place methods, right? This is ascending, and if you want descending, you just choose ascending equal to false. How do I know the parameter name? We have to study the documentation, guys, right? So whenever we are using any function, method, whatever, please go look at the documentations. Okay, so there's a parameter called ascending, which by default it is true. So if you want descending, then make it false. So then if you use the method, now it will give me descending. Again, this is not in place, so my actual object did not change. If you want descending and you want to change the object, notice that this method sort values, again there is this parameter in place equal to true. Notice many methods wherever we are working with pandas, you will get this in place parameter. Okay, almost all methods will give you the in place parameter, and default is false. Okay, so if you want to change, you have to put equal to true. So let me do descending and let me change in place. So, and notice one more thing, when you choose in place equal to true, it does not display the output. Okay, understood that? So when you just do this kind of method, it gives you the temporary output. Okay, but when you put in place equal to true, it does not give you the output in the same execution, because it has gone and changed the object itself. So now if you print the object, as you can see, the object has changed. Okay, okay, there are also the other methods are also similar. You have sum, you have mean, those kinds of things. So if I say, hey, what is my total production in this week, just take the object and do dot sum. Total production is 8490 units. Great. What is my average production in this week? Dot mean. Okay, 1212 units per day is my average production in this week. Okay, great. So all of the numerical methods, statistical methods that we studied before, right? Many of those are directly accessible in pandas objects. Okay, now I want to show some more interesting things here, why this was built on NumPy. So suppose I have one series, I have these people here, Asif, Bhairavi and Chad, right? And suppose this is their expenditure in a hotel. Okay, so on Monday, these three people spent this much money on the hotel. On Tuesday, these three people spent this much money in the hotel. So suppose I build this series, data, index and name. Okay, so now I have series 1, it says Monday, these are the expenditures of these three people. Okay, and series 2, Tuesday, these are the expenditure of these three people. Now if you add these to these, what is your expectation? The expectation is that I need to get the total, which is exactly what happens. If I just do series 1 plus series 2, it adds the values, right? It adds the values and then it gives me the total. Okay, similarly, I mean, plus is not the only way to do the operation. There are object built-in methods like dot add. Okay, this is an object built-in method. So you can choose series 1 dot add series 2, or you can also choose series 2 dot add series 1, because addition is commutative. That is the word, right, in mathematics. Symmetric, commutative, something. It's a commutative operation. The order doesn't matter, right? So series 1 dot add series 2, you get the same thing. And notice our output is also series. Okay, series 2 dot add series 1, exact same. Okay, now one thing to note is that all of this is working very beautifully because index is proper. So suppose I have series 1, Asif, Bhairavi, Chad, and suppose I have series 2, Asif, Bhairavi and Colin. Obviously Chad and Colin are different people. Okay, now my series 1 and series 2 have 3 elements each, but here it says Chad spent 187 on Monday, Colin spent 202 on Tuesday. What will happen when I add the two series? So if I add the two series, this is where you start getting not a number, right? We discussed this NAN business in last lecture or something, right? So pandas expects proper strict indexing, right? This is critical in data science because you don't want to mix Chad information with Colin. You don't want to mix Colin information with Chad, right? The basis of data analysis, data science is integrity of data, isn't it? So by default, no pandas method will allow you to break that integrity. It follows very strict indexing. So what it will do is it will create a new series and it will say Chad I don't know, Colin I don't know, right? It's Asif and Bhairavi, it knows, so it will add. But Chad and Colin, it doesn't know, so it will just say I don't know, nan, not a number. Okay, so notice there are multiple safety checks and foolproof procedures when you use pandas, right? So that we don't break our data basically. So anyway, what we have done, see, we've introduced ourselves to pandas by looking at series. We understood that it is strict indexing, You can give index labels, you can perform all the operations that you did with NumPy, right? This is all we saw that, right? So my point is that now we'll get into data frames and discuss in much more detail, right? And all the methods and operations you learn in data frame you can use in series, and you are encouraged to explore this further. Okay. As I said, the most common data structure in data science from the Pandas library is the data frame object. Essentially, it's a table of series with a common index. We will see what this means in more detail. Before we go to next section, let's do a bit of quizzing here. Okay. Can everyone solve the first quiz? See, and I've given all of these things here so that you can, save time. You can just copy this 3, and as long as there are no errors in this, then you can directly run this. Okay. So consider the series here. I have customer names, I have customer bill, and I've given the command to create the series. So cust info is the series. Okay. Use any series operation that you understood to find out which customer spent maximum amount of money. Share your command in the chat. So you can use NP matrix if you want, but as I said, arrays are more powerful. That's why we didn't study NP matrix only. Okay. So I've given you the documentation link for matmul. Okay, check it out. It multiplies matrix. It uses arrays as for matrix multiplication, not scalar multiplication. So typically we don't even use np.matrix so much. We just use np arrays. Everyone is saying cust info idx max. Yes, this should give you Monisha, I believe was the answer. Let's check it out. So if I just do this, yes, Monisha, wonderful. Okay, can we try the next quiz then, guys? Same thing. You have the same information as before, but now you have some additional information. Okay, so here you have customer names, customer bill, and this is the series customer info. Suppose that customers have already prepaid the following amounts in the hotel. Okay, so I have new set of values here, 500, 1000, 750, 500, right? The customers have already prepaid this. Now use whatever series operations that you have learned to find out which customer has crossed the prepaid balance. Okay, so Chad, Fareen, Himadri, Monisha, they've spent 256, 434, 109 and 529 rupees in the hotel, but they had already prepaid 500, 1000, 750, 500. So obviously, like, who has crossed their prepaid balance means what mathematically. Think about that and use series operations to output the answer. We went up until cust info. Then obviously up to this point it is my original series. So if I just print this, right, cust info, that should give me a series. Okay, cust paid is a list. Now here, very good, right? We have now guys, see, now this is where I can see that you guys are understanding data analysis, right? You have converted the list into a series with the correct customer names. Wonderful, right? That is perfect. So now there is absolutely no way of going wrong. I don't care about the order of the numbers, whatever happens in backend, I don't care. Why? Because I have linked my customer names. In the original series, the customer name is linked with the bill, and in the new series, this prepaid balance series, the same customer name is linked with the correct prepaid values. So now all the information I need is already there. So prepaid balance, if I see, it's a new series. Chad, Farheen, Himadri, Monisha, 500,000, 750, 500. Wonderful. So all I need to do is compare these two. That's all. So that's what has been done here. Crossed balance equal to cust info greater than prepaid balance. Who spent more than balance? That's what you're asking. That's what this is, right? Cust info is the bill and prepaid balance is the prepaid. Who spent more than prepaid? And this logical is being used to get the is being used to subset. So I'll show that also in steps, right? So this is actually a Boolean series. So if I just print this, let me just print this here to show. So this is actually a Boolean series. Okay. So this Boolean series is stored in this variable. Now you can use this variable as an indexer, which is what is done here, right? So here say crossed customers equal to crossed balance, and then you are using the same logical to index it. Now notice that even the Boolean is a series, so it has index information. No problem. So you're using the values to subset the series, which is what is happening here. Okay, so this is subsetting this series, and the series index is what you will get from the index. Now if I just remove this index part and just print this, okay, crossed customers, if I just do this, you will only get the subset where it is true. What is true? Which is true? Cust info greater than prepaid balance. So wherever the bill is greater than the wherever the bill is greater than the prepaid, only that subset you will get. So here if I just do dot index, I will get the name. One step further, guys, if you want the string, just use bracket 0. Okay, one step further, if you want only the string, use bracket 0. Pick out the element inside the index. Okay, the index object is also list like object. Many of these objects are list like. Index, list, array, all of these are list like objects. Okay, so if you want the actual string, pull out the element. Okay, how to pull out the only element? Just index with 0. Okay, and now you can then print it. Wonderful. Okay, whatever. Answer is Manisha. Great, really nice. So we can start with data frames. Now I have a question to the audience. Do you want break now? Because then we can properly get into data frames. Or do you want break later? Please tell me in the chat. You can take it now, no problem. Okay, so it's 10:12. We can reconvene at 10:20. Okay, and I think again we have all the learners here. Before you go on break, guys, just reiterating the feedback that I gave in the beginning of the session. Please, if you can, give your feedback to us at the end of the session. Okay, that is quite valuable to us to understand what's going right and what we can improve. All right, so it's more of understanding the audience, right? So just keep giving that feedback for each session. It's really valuable. Just a request from our end. Anyway, we can go for a break now. We'll reconvene at 10:20 around. So see, a data frame is a two-dimensional table made up of multiple series. Okay, we will see how. But basically, these are many series put into one table, which is what we saw in example previously also. Okay, there are, as I said, many of the methods operations associated with data frames are also applicable to series, and no surprises here, right? Since a data frame is a two-dimensional version of multiple series, then of course most of the methods will be shared between the series object and the data frame object. So suppose, how do you create a data frame? The command is pd.dataframe. Remember D capital, F capital, that is the name of the method, right? So if I just create a data frame like this, df equal to pd data frame, it executes, right? It executes, and if I just print, it gives me blank. Obviously, there is nothing in this data frame. It is blank. What is the type of this object here? Pandas.core.frame data frame. And as I said, we already saw this empty attribute in series. Notice that we can use the same attribute to check for data frame. So if I do df empty, it says true. My data frame is empty. Okay. Now, how to actually use data frames? See, the thing is that in data frames, we are talking in terms of rows and columns. Okay, multiple series. Where are these series? Each row is a series, each column is a series. Now, when we build the data frame, I'll explain a little bit in more detail. But right now, what you need to understand is that columns are usually features. Okay, the word that we use in data science is features. Okay, this is the word that we use, features. So and each row, the word that we use is observations. So features will be in the columns, observations will be in the rows. Okay, so for example, in this case, these are my features of the data set: customer ID, name of the customer, email of the customer, phone number of the customer, and total purchases made by the customer. These are the features. Okay, what are the observations? These are the observations for these features. So for example, I have this customer here whose customer ID is 001, name is Alice, email is something, alice@example.com, phone number is a string, that's okay, no problem, 1 2 3 4 5 6 something, and then the total purchase is 20. My next observation is this customer 002, Bhushan, bob@example.com, 987 whatever 15. Okay, so notice that this is a list within a list. So please remember back to two-dimensional arrays, right? So 2D arrays, if you remember, they were list within list, and each of these is rows, correct? Each of the lists within the list is one row. So right now this one row should appear as one row in my data frame. This should be my second row in my data frame, and so on, right? And these things are columns. So 001, 002, 003, that's one column. That should come under customer ID. Alice, Bhushan, Carl, this should come under name, correct? So that's how I set up my data. Now I say df equal to pd.dataframe and data equal to customer data, this one. This is the data, all the observations, right? This is my data. And columns are these names here, customer ID, name, email, phone, total purchase. Now I'll run this and I'll show you what happens. This is what happens. So if you see this list here, it has been taken for the column names, customer ID, name, email, phone, total purchase. And each of these observations is now stored in a row. See, 001 Alice, Alice at example, whatever, right? So each of these observations, each of these lists is stored as a row here. Notice that a generic index has been generated. Okay, so of course the integer index exists. Okay, even at this stage, customer ID, name, email, phone, total purchase, these are label index, which Pandas gives you the the option to do that, correct? Backend NumPy is storing integer index. So customer ID is 0, name is 1, email is 2, phone is 3, and so on. Same way, you did not give actually names to the rows. You gave the rows directly, right? Each observation you gave it directly. So what Pandas does, it takes the integer indexing in the backend, which is done by NumPy, and pushes it forward, which is why you're seeing here bold, right? 0, 1, 2 in bold. So whatever integer index is behind, it has been generated as the label index also. Okay. Because we did not specify names for the rows. Now, of course, there is a way to specify names for the rows, and for that you can use the index parameter. So in data frame, the word index refers to the rows and the word column refers to the columns. Okay, that is the parameter names that you need to remember. So data is basically all of these observations. Columns gives you the column names, and then index, it's the index names. So suppose I use A, B, C, okay, customer index, and I provide that to index. So now I have data, columns, index. Now if I print this, you can see here the NumPy integer index went back and the label index is what you see, but the NumPy index is still there. Okay. Okay. So whether to use a standard integer index or whether to use unique identifiers like these, column names and things like that, that's a judgment call on the part of the analyst. Like depends on what you're trying to do. If you're doing some very temporary backend analysis, then you don't really need proper labels for the rows and things like that, right? But if you are doing data reporting, if you're showing reports to the business team and things like that, definitely you need proper names for the index and the columns and things like that. Okay. Okay. So typically column names are something that we retain. Even if we are doing internal analysis, column names we retain because it's easier. So I need to know, feature analysis, one of most important thing, right? So total purchases, for example, if I have 1000 customers and I have all the total purchase value, I don't want to remember which location, integer location my total purchase column is. My data set may be having 20 25 columns, 10,000 elements. Each time I cannot go find out where is my total purchase, but analyzing total purchase is important to me. I need to know what is average purchase, I need to know who did the maximum purchase. So to call that column, it's usually better to give proper column names in data analysis. Okay, typically it's good if you give both, but columns are more important to be named properly. Okay, because as I said, these are the features that you are studying in data analysis. So that's what I'm doing here. I'm not giving the index name. Okay, and my data frame, I'm just redeclaring it without the index. So now I have integer index. Okay. What happens if my observation is not matching with the uh, columns? So for example, here Carl, I deleted Carl's phone number. I have Alice full observation, I have Bhushan full observation, but for Carl I deleted the phone number. Everything else is same. What will happen? It executes, but now you see what happens to the data frame. It produces not a number, none. Okay, and what it did was it took the 25 total purchase value and put it inside phone column, which is wrong. Correct? So pandas cannot identify meaning like that. Pandas doesn't know 25 is phone number or 25 is total purchase. Pandas doesn't know that. So whichever order you put, same order will be matched with the customer columns, right? Same order will be matched with the column names. So typically it is suggested not to have this kind of data. You should make sure that your data is proper. Otherwise, as you can see, it will produce lot of missing values, right? And pandas is not intelligent enough, obviously, to match 25 with phone number or 25 with total purchase. How can it know what is what? So it just pushes 25 to the left. Okay. Now what happens? Now in this case, at least it is producing NaN. What happens if you do not even have the complete column list? So here it says customer ID, name, email, phone, total purchase. Here I deleted phone from the column. What will happen? In this case, it gives me a proper error. It says, look, 4 columns passed, but data had 5 columns. And at this stage, pandas will not accept this object, right? You gave me 4 columns, but your data has more. I don't know where to put. I don't know. Should I make a new column? Pandas doesn't know. So it throws an error, right? So typically it is better if length of each observation and number of columns are matching to avoid any interpretation issues, any data integrity issues. Always it is better to match the lengths of the observations with the length of the columns that you're specifying. Now, I have shown you this method with nested lists and things like that. Typically, the dictionary method is used more often. What I have seen is the dictionary method is very clean. Same way, if you remember in series, we just passed a dictionary. The keys of the dictionary went to the index and the values went to the values, right? A similar kind of thing happens in data frame. Not exactly same, similar. So here what's going to happen, if you can see this dictionary here, notice that the key of the dictionary is actually the column name. Customer ID, name, email, phone, total purchase. These are the keys of the dictionary and these are the column names. And your complete column list now as a column vector, not row wise observation. Okay, so if you go back to any of these data frame, what is the column vector for customer ID? What is the column list? It is 001, 002, 003. What is the column list for name? Alice, Bhushan, Carl, right? That full column list you can pass as the value. So customer ID is the key in the dictionary, and then you have the value, which is a full list. Okay. So, and then the next key is name, and then you give the full list, Alice, Bob, Charlie, whatever. So now you have all the column names in the keys, and then you have all the values as column wise features in lists, and directly you can pass this dictionary to data frame command. And as you can see, very nice. Customer ID, these are my customer IDs, these are my customer names, email, so on. So notice how the column names are directly interpreted from the keys, and the full list of the rows for each column is interpreted from the lists that you give. So typically this is a cleaner method to create data frames from scratch. Okay, and of course if you don't like this NumPy backend integer index, you can always specify the index. So same thing if I do here, now I can have as you can see here the labeled index for the rows. Okay, great. Now here and one last thing, as I told you, if you don't need to specify the parameter name each time if you know the order. For that you have to study documentation, see the order, data first, index next, columns next, dtype next, and then copy. Okay. Forget about copy and stuff like that right now. Let me just run this, and as you can see, it produces this data frame. And by the way, as I said, you don't even need to put parameter name. So if I just have a dictionary like this, right, I can directly just convert it to a data frame, and it takes the column names and the observations and all of that. Right. So one thing to point out, see, initially in data analysis, data pre-processing is a place where we may sort of use some of these creation methods like dictionaries and lists, but majority of data analysis, you will be working on collected data, so in the program. But as you do the program fully, by the end of the program, you will be expected to know data collection, sourcing, and pre-processing, then analysis. You understand what I'm saying? So right now we will get into these, as I think similar to what Sonal was asking, right? So all of these different techniques we will be discussing topic by topic, and slowly when you do some of these projects, right, we have course projects and things like that, assignments, there you will be using everything. And by the end of the program, you will be expected to know all the things, like sourcing the data, putting it together, cleaning the missing values. It's like there's a huge pipeline of activities, right, what a data analyst is supposed to do. So treat each session and understand what you're understanding from here. It will all be put together little by little as we go from topic to topic, and in a major way there are projects to sort of help you out in those things. Okay, so now we'll get into reading data. I think this is the fun part. So see, there are many read methods in Pandas. I am showing you read CSV, read Excel. You can go see the documentations. Pandas can read many type of files. What I have provided you is CSV files. Okay, now I don't think I gave you Excel access file. Don't worry, the same data is there in CSV. Please run this one and see if you are getting the buffet details. Can you confirm? Like, can you run this command pd.read CSV, and then the name is already there. Is everyone able to read the buffet data? Please confirm. Sunidhi, yes. Anusha, yes. Shri Prakash, yes. Sauradeep, no. What's the problem, Sauradeep? Was there a Ashish, yes. Others, we are able to read it. Rajat, no. Can anyone just tell me why? What's the error? No such file. Okay, Rajat, what are you using? Colab or Jupyter? Then please check whether buffet details CSV has been downloaded into the same folder where you have the notebook. Sauradeep, please check whether you have uploaded the data file, CSV file, into the Colab folder. So on the left side, you have some menus, right, in Colab. So there you will see a folder icon. You need to drag your file and upload it there. That's for Sauradeep. And for Rajat, check, just go to your system folder, wherever you downloaded the notebook. Just check in the same folder whether you have buffet details.csv. Okay, these are the advice I can give you guys based on what I can see from your responses. Okay, right. Now what I want to sort of show here is that, see, there are some parameters of this read function, file path or buffer, and then things like that. And see, when you deal with different types of data, it will ask for delimiters, right? So what is CSV? Comma separated variables. Okay, CSV means comma separated variables. So this CSV is an Excel CSV. So it is storing as comma separated using Excel. You can have different delimiters. Okay, you can have space delimited, comma delimited, so on and so forth. All of this will be explored a little more detail when you do data sourcing and things like that. Right now, we'll just read the file. Okay, so read CSV has that parameter, file path or buffer, which is where I gave my file name. Please note that this is not file name, it is file path. So the only reason that my code is able to read this file is because this file is in the same folder as my code. If the file was in a different folder, you can just provide the file path. Okay, so that's something that we'll not get into in this session, but you can Google it and read more about it. We will see file paths, things like that, in a later data pre-processing, things like that. Okay, so the reason that this is working is it's in the same folder as my code. Now there's another very nice parameter that I typically like to use. So if so look at the data. Okay, the data has room A1, A2, A3, A4, name Shilpa, Jaspreet, Dominic, Ahmed, age 1832, 1922, cuisine Indian, American, whatever, expenditure 24, 18, 27. These are in dollars. So what is this? This is basically the amount of money spent by these people, and then in a hotel, right? And they have also stored the room number which they are staying in, the age and the cuisine. Okay. So now here, just do one thing, right? Just make a new cell here and write pd dot read csv and put empty brackets. Just do this much. Can everyone tell me after doing this much? Just say yes. Create a new. Okay, 1 second. I think some sharing issues. 1 second. Yeah, okay. So everyone created a new cell and you wrote pd dot read underscore csv bracket. Correct? Correct. Now you can just press tab. Okay, and it will give you all sorts of things. Don't worry about that, right? Instead of tab, what you do is you put string. Okay, put string and then write just the first few letters. So I have written buf. Now if I just do tab, it is going to show me all the files that has been recognized by Jupyter. So if you just put string like this, just make a string and then tab, it will show you all the string objects, which is not good, right? So usually I just put 1 or 2 letters and then you press tab. Now Jupyter will show you everything, right? So where were we? We were reading this buffer detail file, and as I said, the buffer details, what it has room number, it has name, it has age, cuisine, expenditure. What again? Each row is an observation. Okay, so the first observation is Shilpa, who is staying in room A1, whose age is 18, who likes Indian cuisine, and she spent about $25 on Indian cuisine. Okay, and similarly you have all the different observations. Jaspreet stays in room number A2, age 32, and spent $18.54 on American cuisine. Okay, one interesting thing I like about PD read CSV and typically reading functions in Pandas, it allows to set the index column whenever you want. So notice that again here, what happened, it has so if you open the CSV file, which I'm not showing right now, but you can open it using Excel or something, it does not have these numbers. The 0, 1, 2, 3 is not there in the data. Okay, these are the NumPy indices, correct? So the 0, 1, 2, 3, 4, 5 is the NumPy backend integer index. So what Pandas does, it gives you option. If you want to set one of these features as the index for the data frame, Pandas allows you to do that. So there is a parameter called index underscore column. So again, if I do pd read csv and file path buffer, this is my name path of the file. This is the same, right? Same as before. I can specify index column to be one of the features. So if I say name, and then I read the file, now the index is name. Okay, and that feature is now not there inside the data frame. It has become the index. So one of the features you can overlay on top of the NumPy integer index. So now name is here. Also, name is a very bad index. Okay, I hope everyone can understand. Two people can have same name, right? So name is a very bad index here. What is a good index for this data set? Room is a good index for this data set because room is unique. As a hotel manager, you are interested in unique identifier. So room 1, room 2, room 3, right? So I have shown you index call equal to name, but obviously it's not the best index. Room is a better index. So for example, I can read, I'm using another function, read Excel. For you, it may throw an error because I did not give you the Excel access version. So you can just comment it if you want. but I'm just showing you that it works. Okay, so if I read Excel buffet details.xlsx with index column equal to room, it will print for me the same thing. You can read without any commands also, you can directly read. Okay, so finally what I want everyone to do is execute this command. Okay, all these different other versions we will not be using, we will use this version. Okay, so just do df equal to pd read csv buffet details.csv. Okay, and then print the data frame and confirm that we have this. Please confirm in the chat. Okay, great. Okay, so please solve these two quizzes, right? Load the car prices.csv into a data frame with the name df cars. Okay, and study it. Study it means don't worry, we'll study it. For this, don't specify the index column. What is the command? Do not specify index column. Read this into a data frame name with df cars. Can someone give me the command? So this has 205 rows, 21 columns. I hope you can see it gives you all the details here. 205 observations, 21 columns, and there are many columns obviously. So everyone able to read this file? Yeah, perfect. Yeah. Okay, then do the next quiz, please. Load the user movie rating CSV into a data frame named df movies, and this time specify the index column as the user. For this, you need to know what is the name of the column. Okay, so what you need to do, if you don't know the name of the column, what you need to do, either you go and open the CSV file and check there, or you read without specifying the index column to see the name of the column and then read with the index column. Okay, so basically you need the name of the column. Everybody able to do this? The first thing I would do here is pd.read CSV, and I'll just copy this here, right? And I will see the name. It's saying specify the index column as the user. So user means Arnold, Ben, Catherine, Disha, Euclid, whatever. So the name of the column is user. So I can just print this temporary output, copy this column name from here. I will say, one second. I will say here index column equal to string user, and here I will say, I mean, you don't need to give the parameter name, it will work. So this I want to store it as df movies equal to, okay, I'll print it. Everybody able to do this? Index call equal to user, yeah. Okay, so the whole point of this is that you need to know your data, right? Again, guys, I told you data analysis is not just about analyzing data, it's also about handling data, right? So we are getting a lot of first-hand experience here handling all these files, file path. This is all very important in data science. Okay, so great. The index column I have specified as user, which is the name of the column here, which has the users. Now I want to go through these two data sets, then we'll move on. See, this dataset car prices, what it has is it has 200 cars of different models. Okay, so you can see car name Alfa Romeo, Audi, something Volvo. All these are car types or names. Okay, then you have various features like number of doors, type of car body, engine location, wheelbase, car length. This I think is inches. Car width, again these are in inches. And then you can see dot 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 because there are too many columns to display. Okay, so we can't see all the columns here right now. It's giving me number of cylinders of the car, engine size, bore ratio, all sorts of things. And then, one of the most important feature is the price of the car. And I think this is in dollars. You can also see mileage, miles per gallon, right? Obviously this is not metric unit, this is American unit. But yeah, miles per gallon mileage is here, highway mileage, city mileage, horsepower, all these things. So this one is actually, a fairly standard data set. It's a real data set which is used to train ourselves in data science. It's a very, very nice data set. It has many type of feature and really nice. This other one, this is a smaller data set slightly. What it has is it has usernames. First, let me just print without the index column. So what it has is it has the usernames here: Arnold, Ben, Catherine, Disha, Euclid. It has a few movies. Thor, Justice League, Spider-Man, whatever, Casablanca, Kissing Booth, Annabelle, Insidious. So it has the ratings given by each of the user on a scale of 1 to 10 for these movies. So Arnold gave rating 6 to Thor, 5 to Justice League, 6 to Spider-Man. Clearly Arnold does not like action movies. Ben gave 9, 10, 8 to Thor, Justice League, Spider-Man. Ben really likes action movies. So on, right? So 1 to 10 scale, you have ratings of all the different movies by these users. Okay, so let me put back the index column. All right, so everyone was able to load both, right? We can move on with studying data frames now. Please put yes. So to study data frames quickly, right, there are some very interesting, nice methods. One of the method is called head. And notice these are all built-in functions. Okay, so this object called df, which is where I loaded the cuisine thing, right? That object has multiple built-in methods. By the way, these methods will work for series also. Go try later. Okay. So df.head, what does it do? Basically, it gives me the top 5, right? First 5 observations of the data set. Why do we need this? Of course, our data may be very big, right? Maybe we have thousands of observations. So if you quickly want to know what does my data look like, then you can use the head command. Okay. And here you can specify how many observations you want to see from the top. So if I say df head n equal to 3, then it will give me the top 3. So top 3 means first 3. So 0, 1, 2. Okay. Similarly, there is a tail command. This gives you the bottom. Default is 5. Okay. Default is 5. So 1, 2, 3, 4, 5. So from the bottom, it gives me 5. Again, you can specify from the bottom how many you want to see. Df.tail. What are the things we need to remember here? 1, the output is a data frame. 2, these are not in place operations. Main things that you need to remember with these commands. Output is a data frame. In place, not happening. So if you now quickly just print df, of course your original data is still there, right? Purpose of data analysis is to analyze, right? Of course, when you want to mess with your data, you can do that. But typically you want to analyze what's in your data, study what's in your data. So a lot of methods, as I said, will not change your original data. Okay. So head and tail. Now, again, if you want to know the axes of your data frame, I told you there are 2 axes, right? One is the rows, and one is the columns, right? So it shows you here the observations, the index of the observations. Right now, it is a labeled index of 0, 1, 2, 3, 4. Why? Because we did not provide any, index for the rows. So what is happening? The NumPy integer index 0, 1, 2, 3, that is being pushed forward. So that is what is being shown here. Okay. And what about the column? Column is here. Room, name, age, cuisine, expenditure. So this rows go from 0 to 9. Okay. So stop equal to 10 means exclusive. Okay. 0 to 9. And then index for column is room, name, age, cuisine. Don't get confused with the word index. Okay. That's why I said this is called observations and this is called features. This is an index object. This is also an index object. Both are indices. According to NumPy, both are indices, right? But in Pandas language, that changes little bit. So if I do df.index, it will give me the row index. So for NumPy, index means everything. First dimension, second dimension, third dimension, whatever. For NumPy, all are index. For Pandas, df.index specifically, that variable name is, attribute name is reserved for the rows. Okay. And here, of course, there are 9 observations. So you can directly check len of data frame. Length gives you the rows. Okay, len, not 9 observations, 10. So length of df gives you 10, right? For columns, what do you do? df.columns. So if I do df.columns, this attribute provides me the column index. So again, no confusion. Here the I is capital. This is the index object. Here the I is small. That is index attribute of the data frame. Okay. And as I told you, this is all NumPy based business. So df.shape should work. I have 10 observations. I have 5 columns. df.size also should work. It says 50. df.size, why does it say 50? All the number of unique elements in my data frame. So 10 into 5 equal to 50. So totally I have 50 data elements in my data set. You can also check DFD types. So for each feature, it will tell you what is the data type. So room has been loaded as object. So room, if you see, it is A1, A2, A3. Ideally, it could have been string, but Pandas has loaded as object. Okay. Name is object, age is integer, expenditure is float, obvious, right? Age are all integer values, expenditure are float values, and so on. Now, typically, there is this one very powerful method to study the features, not feature, characteristics of the data frame. It is called info. So df.info, and notice this is not an attribute. This is a command. So you need to put info with brackets. Okay. So if I just do df.info, it gives me all sorts of quick characteristics of the data frame, right? It tells me what are the columns. Okay, it tells me how many values each column has which are not null. It tells me the number of rows. Okay, so number of rows is 10. It also tells me what is the row. It is 0 to 9, right? And since I have 10 rows and each column has 10 non-null features, that means there is no null value, there is no missing value in my data. It also tells me the type of each of the feature: object, object, integer, object, float, right? And it also tells me how much memory it's right now using. To store this data frame in my local system, it is using 532 something bytes. Okay, very powerful method, df.info. Okay, very powerful method. So typically these are sufficient. See, this shape, columns, index, info, these are sufficient to study important characteristics, but there are some methods which have been imported from NumPy, which gives you similar things like df.keys. If I do, it gives me the column, df.values, it gives me each of the observations. Typically we don't use these so much, but these also exist. So in some situations maybe it is useful. So df values giving me all of the observations, right? And df keys gives me the what is this, the column names. So this is again the, if you remember, when we created data frame, we gave data equal to something list within list, right? And then we gave columns equal to this, right? So those keys and values we are getting here. Typically it's just easier to use these methods: shape, column, index, info. Okay, some cases maybe you need this, but not very frequently. Okay, so okay, I want everyone to run this now. So if I do temp df, just please run this command. Okay, this time we are reading the buffet details, but this time we are specifying room as the index column. Okay, so read this and let's call it temp df and then print temp df. Can everyone tell me, are we getting this with the room as the index? Okay, great. Now again, if you do the same method, what will happen? So if you do head will still behave the same way, right? It will only give you the first 5 values of the data frame. Now if you do shape, notice that it is 10,4, not 10,5. If you do shape, you get 10,4. Why? Because your room feature has now gone and sat on top of the integer index for rows. So that feature is now an index for the rows. So now the shape is 4. Okay, so 1, 2, 3, 4. Name, age, cuisine, expenditure. Why? Because we use room for the index. Now if you do temp df.columns, you will not find what is that, room. Room you will not find. Okay, and if you do temp.index, here you will find name equal to room. Interesting, right? So room we have used as the index column. df.index, if you do temp df.index, if you do, here it says name equal to room, and here is the value. So data is not lost, it is there. So if there's a very, we'll do some methods later. There's a very nice method. You can just pop out this room feature back to the data set and push forward the NumPy integer indexing back. Okay, it's all there, right? Here if you do info now, what does it do? Very interesting. See this. It says my index is 10 entries starting from A1 to A10, and it says I have 4 columns. Okay, so we are all understanding what's happening here with the data frame and studying the data frame properties. Okay, now another thing, a few other things. df.d types, this I don't think I showed you, but info gives me data type anyway. So if I do info, I will get the data type. But if you want the data type separately, you can just do df.d types. and that gives me the data type for each feature. Okay. Transpose, same as NumPy. What will happen if you do df.transpose? As you can see, columns became rows. Okay, now the columns are 0, 1, 2, 3, whatever, and now the rows are room, name, age, cuisine. Okay, so now if I do df transpose d types, what's going to happen? It will give me the d types of the columns. So you can see here column 0 object, column 1 object. And why is this object? Obvious, because in each column you have integer, float, string, you have everything. So as far as Pandas series is concerned, it is object data type. But at the same time, each element still retains its data type also. So you have not lost your integer information. You have not lost your float information. Yeah. So again, what will happen if you use temp df now? You remember, this is the data frame in which we have, what is that? The room as the index, and just do transpose. What happens? Now the room becomes the columns, and then the previous columns, whatever name, age, cuisine, this become the label of the index. Okay. So basically what this shows, what this whole thing, what we learned is that, look, Pandas data frames are nothing but intersection of series. Okay. Think of it as a 2D array, but each slice is a series. Each slice. So A1 Shilpa 18 Indian 24.65. That's a series. Name Shilpa Jaspreet Dominic Ahmed Joseph Saju Monica. That whole thing, that is one series. So it's essentially collection of series, and a pair of series will intersect at an element. So room number A5, how much expenditure? $17.32. Okay, so pair of series intersecting at an element. Okay. Okay, time for quizzes. Please solve these right now. These are pretty straightforward. Print the top 4 observations in DF cars. How do you do that? I want to see some commands in the chat, guys, please. Print DF. Interesting. You don't need to print each time. Maybe I don't even know what result you're getting. Yeah. Don't do print. Don't do print. It gives you little weird result. Pandas already has a nice way to print it. So just directly do df cars.head. Because you can use print if you want. The result is just looks very weird. Okay, great. Next one. What about bottom 6 observations of DF movies? Yes, DF movies tail 6. I'm just going to copy it from here. Great. Wonderful. Nice. How many rows and columns does DF cars have? How are we going to solve this? How many rows and columns? What command should we use? How many rows and columns does DF cars data frame have? There are many ways to solve this. Very nice. Num rows, num columns equal to DF cars. Brilliant. Yeah. Info is also good. Typically, I would have said info, but Sunidhi has given much better answer. I'm going to take that. By the way, guys, I'm also part of the group who will use info. Okay, I will just do df info and I will check. Okay, it has so many rows, columns. But Sunidhi's code is really nice, so I'm going to take that. Okay, num rows, num columns equal df chorus shape, and we know that it's a 2-dimensional array. Shape is going to have 2 values. First value is number of rows. Second value number of columns. It's all NumPy business. Yeah, and I can just print it. Say print, and then I'll print this tuple. 205 rows and 21 columns. This is one method. Another method, df.info. Quickly check it. Array, not df. I'm very sorry. Df cars. Df cars.info. 205 entries. Okay, and 0 to 20, which is here 21 columns. Okay, 205 entries, 21 columns. Another method, just print it. If you just print df cars, you can see at the end here 205 rows, 21 columns. Okay. Okay, quiz number 6. What are the data types in DF cars data frame? What is the command we'll use? I mean, other than info. As I said, info gives you like almost 80% of what you need. Okay, how do you get the data types of the features in DF cars? DF type frame what? Shouldn't work. It's already there. Okay. I think the answer is already there. Whatever. So just print df cars.dtypes. I don't know where this came from, guys. Yeah, df cars.dtypes. Now, is everyone able to print that? Df cars.dtypes. Did we print it? Yeah. So in that, now you can see very nicely. You can see all the features: car ID, integer, symboling integer, car name, object, whatever. Whatever. Great. Yeah. Wonderful. Okay. Now comes accessing. Biggest pain, isn't it? NumPy accessing. Now pandas accessing. Okay. All right. So in this section, we will study access methods. We'll focus a lot on the fundamentals here. Okay. And some of the important other methods we will go in detail, but we'll kind of do it in an introductory way, because accessing is something that we will study in detail in pandas session, right? Later in topics such as data processing and all of that, the other methods you will anyway be using more and more often, in data visualization, data analysis, data processing. In all of that, you will be using some of the other operations and methods more and more. So this is the right time where we should learn the accessing. Okay, fine. Let's print df. This is my buffet data. Now suppose I want to pull out the column called room. Okay, so one way to do that is you can use the key name, which is why here room with a capital R is actually an attribute of this data frame, right? Because it's part of the list of keys. This is not typically used so often. You will find that, okay, this is one way of accessing the columns which is used sometimes, but here if you notice, all the column names are a single word. If your column name was two words with a space, then you cannot use this method. So for example, room number, if that was the name and then there's a space, then of course you cannot use this kind of method. But if you have a single word for the name of the column, you can extract that column. What is this object? What is this right now? Can everyone tell me? df.room I have printed. Can you tell me what does this look like in the chat? We have seen this data structure before in this session. Exactly, it's a series. So now if you just check the type, pandas core series. Okay, hope it's making sense now, right? No magic going on. Whatever series are there, each column is a series, each row is a series. So you pulled out a column, you got a series. Okay. Okay. Another way to access column is this. Okay, single indexing, indexing method with the square brackets. So if I just say df and then say the column name, it will give me the age column. So you can see here 1832, and the index it is giving is 0, 1, 2, 3, 4, because I did not specify a separate label for the index. So that same index is coming 0, 1, 2, 3, 4. Okay. Now, if you want to retain the shape, we already saw in NumPy what you need to do. You need to use square bracket 2 times. So now if you use square bracket 2 times and you use age, what's going to happen? It is going to give you a data frame. Okay? So this is a data frame with one column called age. Okay. If you want more than one column, then you can use methods like this. Now, one problem you need to remember is that this format in Python, remember, it is a tuple, isn't it? This a comma b business in Python, it's a tuple. So the argument to df is not a tuple. Okay, the argument to df should actually be a list in case you have two items. So if I want to get cuisine and age, then I have to create a list which has the two column names, and then I have to access with another square bracket. Okay, now if I do that, I will get both cuisine and age. All right. Now suppose I pull out df cuisine. So let me just just get cuisine from here. How do I access the first element? Just remember NumPy. Okay. So if I just do bracket 0, it will give me the first element, Indian. df cuisine, this is the series. So df cuisine 0 means what? The first entry in the cuisine feature. Okay. Notice that this is an integer right now. Okay, it's an integer. So here I have put string 0. This will not work. Obviously, it will give error because it's a key error. Okay, the word key in Python is used typically for indexing, right? So the key is pointing to some object. So here the integer 0 is pointing to this object called Indian. Okay, and we remember that, I hope we remember that this is the 0 1 2 3. Where did this come from? I did not specify. It is the NumPy integer indexing which has been pushed forward. Okay, so that is why if you try to use a string here, it will not work. Only the integer will work. In case that it was a string with 0, or suppose instead of 0 you can say a1 a2 whatever, right, the other data frame, then you have to specify it as string. For example, here temp df, if you see, the index is room a1 a2 a3 a4 a5, and we have name age cuisine. Now suppose I pull out temp expenditure. Okay, suppose I pull this out, temp expenditure, it is a series. Notice that now it is retaining the label, right? And don't say that it is not retaining label in previous case. It is. The only thing is that you did not give any index label for the rows. So numpy 0 1 2 3 has been pushed forward. So in a sense, you can think of it like there is a layer in which there is integer index. On top of that layer, there is a label index for both rows and columns. Okay. In the temp df case, now I pulled out this expenditure column. Notice that the integer indexing will also work and the label indexing will also work. Okay. So if I do bracket 0, it will give me 24.6. Why? Integer indexing still it is existing. Okay, in the backend numpy. And a1, will this work? Yes, pandas. Okay, the label indexing also works. So there are two types of indices. In pandas data frame, there are two types of indices. In numpy arrays, there's only one type of index, integers. In pandas data frame, there are two types. The integer indexing, on top of that, you have the label index. Okay, very powerful data analysis methods, right? So yeah, the point about this is that, you know, this kind of accessing may seem clean. Okay, this kind of accessing may look clean, but it is not. Let me show you some proof why it is not reliable. Okay, so suppose I do temp df a1, error. Why error? Because there is no such thing as a1 in the column. If you see this, it's all row index, correct? Okay, so suppose I do df0. If you remember, why is df0 also not working? Check df, right? Df should have a 0. It's not working, right? Df0 is not working. It's probably going to say key error. See here, key error, right? And here also it's saying key error, right? What I can do is probably transpose it and then access 0 if I want the row, right? I can do that. And for temp df also I can do transpose and then get it, right? But this kind of, obviously, why should I transpose my data and get the row and things like that, right? Why should I do that? In fact, let's just look at, for example, let's look at temp df. Suppose I want the first row. Okay, suppose I want the first row. Now I've obviously shown you that temp df indexed with a1 is giving me error. Okay, so maybe you think that, okay, what if I do temp df bracket colon a1 something, right? What if I do this? Absolutely not. Okay, it's again going to give you error because I just told you tuples are not allowed. Okay, let me put it in a list and okay, invalid syntax. See, so this kind of indexing may seem clean, but it is not reliable. It is not powerful. Okay, so this is called direct access. It is okay sometimes to pull out the columns, and then from the column you can pull out things because one column is a series. So from series, then you can access again like a series, right? It's okay in some cases, but the more powerful methods are something that we will see soon, right? Which I will mention soon. But first, can we solve these quizzes? Okay, let's solve these quizzes, guys. Access the car names feature from the df cars data frame. Okay, so first print the data frame and then see what you want to pull out and pull it out. Please give the command in the chat. Just print it, no need to assign it, Sunidhi. So directly you can just so for example df cars dot car name, that's all. No need to assign. That's one method. Any other method? Waiting for answers in the chat, guys. Any other method? Next, quiz number 9. Access the movie ratings for the movies Thor, Spider-Man, and Insidious from DF Movies. Prakash, that is correct. Again, is that a comma? Yeah, fine. I also make all these mistakes, guys. Dot, comma, colon. Just this is a practice, right? More practice. Sri Prakash is correct, by the way. I'm just saying that I've become used to checking each syntax. Okay, next quiz. Quiz number 9. Access the movie ratings for Thor, Spider-Man, Insidious. DF Movies. Anyone? So I'm just going to copy the command in the chat and put it here, guys. Right? I want to see, I want confirmation. Okay, I'm copying. Pratim, you are giving me previous quiz answer. I will take Ashish's answer here. DF Movies, Thor, Spider-Man, Insidious. Okay, wonderful. And I hope everybody is getting this output. Yeah. Okay. Okay. Notice that, and again, guys, keep remembering things like this. Okay, the output is a data frame. So what? So you can chain commands. Just for example, I'm saying. So now the output of this subset is a data frame. I can definitely do dot head, right? So, and the output of this is also data frame. So now I can do dot tail suppose 2 gives me Disha Euclid. You can chain commands, man. So now I do, okay, I just want Disha dot head 1. This is also data frame. Okay, I want Spider-Man. Now it's a series. Well, it's a series. I just want the first value. Answer is 7. So notice, okay, you should, by the way, chain commands. Okay, more speed and more efficient analysis. It may be hard in the beginning, but I told you the easiest way. Just remember what the output is. Output is a data frame. Okay, I can use some method. Output is a series. Oh, I can use another method, right? So you can chain all of these things. Okay, anyway. Now we will move on to, as I said, this kind of indexing is good some cases like these. But if you really want a strong indexing, then we have to do we have to go through as much mental effort. Yeah, Shri Prakash, that's how it is, right? So, I mean, see, the whole point of data science and everything, it's like if you are enabled with the tools and the math and everything in the beginning, then after that it becomes good. So, what I'm trying to say is, if I directly taught you, Shri Prakash, if I directly taught you some data analysis, I would not be able to fully impart, what I'm trying to say. But if I teach you the math and the programming and the NumPy and all of that, and then when I teach you some data analysis, you will understand what exactly I understand, right? So that's kind of the reason that the program is designed in this way, and kind of the reason that the initial part we have to put a lot of effort in getting familiar with the tools, the programs, the math, and those kinds of things, right? Anyway, thanks for pointing that out, Sri Prakash. Okay, so this kind of indexing method, direct access, it's nice, it looks clean, but it's not powerful. So in Pandas, we have two powerful indexing methods. Okay, one is called LOC, location, other is called ILOC, integer location. I think the second one everybody knows what it is. ILOC, it is NumPy integer index, full stop, right? Then if you know what ILOC is, then you know what LOC is. What is LOC? It is the Pandas label. So A1, A2, A3, A4 column names. That's all. So now let us see how to use this. So suppose I take my buffet thingy, right? And suppose I also take the buffet data frame with room as the index. So I'm taking two versions. Okay, I'm working with this version of buffet in which the row indices are just copies of the NumPy backend 0, 1, 2, 3, and in this version the row indices are labeled. Okay, so df.loc 0. If I just do this, what I will get the first observation. So df means this data frame. So in this df.loc0, 0 is the name, and notice the language I'm using, name of the first index element, not number, name. The only reason it is working is because numpy index was pushed forward. So df.loc with the name of the first element in the row index. In this case, it is 0. In df case, it is 0. That will give me the first observation, which gives me the series A1, room number A1, Shilpa, 18, Indian, 24.56, whatever. This one, right? The first one. Now, what about tempdf? Can I try tempdf loc0? Let me just try tempdf loc0. It gives error. Why? Because it's a key error. LOC is expecting the pandas label, not the numpy label. So in tempdf, what is the pandas label for your first observation? The pandas label is A1. So if I do tempdf.loc A1, that will give me the first observation here, Shilpa, 18, Indian, whatever. Okay, that is pretty clear. Fine. So the LOC indexer is not exactly positional, it is nominal. Nominal meaning name. Okay, positional means very strictly positional, it is your integer index. Okay, so for that there is a separate method. The similarity to numpy is that the first, if you give a integer, not integer, if you give a single element as the argument for LOC, then it will take the row, 0th dimension, it will take the row. Okay, if you want the column, for example, if I just print here df, right, and I want the column age, so you may think, okay, df.loc age, let me do that. No, age does not exist in the rows. If you give a single element, that is the row indexer. So age, if you will get a key error because age does not exist in the rows. So now remember numpy. How did we do the column access? We did colon, comma, and then you give the name, right? Colon, comma, name. Now for numpy, it was all integers, correct? For pandas, this works with whatever name you give to the columns. So here I have to do df.loc. What does this colon mean? It means give me all the rows, right? It gives me all the rows, comma, give me the column age. So now it will give me all the rows for the age feature, and the output is a series. Okay, so the LOC indexer defaults to observations if the argument passed is not a tuple. Okay, now for example, if I want one element, suppose, so as you can see here, this df.loc age, this is a series, and suppose I want this one 32. So what I can do is I can do like this, right? df.loc colon age, this gives me this complete series. Now I know that the output is a series, therefore I can use bracket 1 to access the element 32. This whole thing you can combine as a tuple, right? So df.loc 1, right, row with name 1, and then column with name age. Now similarly in tempdf, what you should do? In tempdf, remember that the names are strings, proper strings, A1, A2, A3, these are strings. So here if you want age of the person in room A1, which is 18, so I can get it by tempdf loc A1 comma age, which is 18. Now if I want all the details of the person in A1, then I can just do tempdf loc A1 comma colon. In fact, you can directly do tempdf.loc A1. This also will give you same. I usually do this. I mean, if I'm doing very quick analysis, maybe I do this. If I'm writing a more bigger code, I might do this, right, for consistency. And if somebody else reads, they will at least know that it's a tuple. Okay. Anyway, so you can also, so this is, we know all this. This is all NumPy business, right? Same way, if you want, age and expenditure of the first element, first observation in df. Notice how language is getting hard. If I do not give name label to rows, the data analysis language is getting harder. I'm saying first, 0th, second, third. Isn't it easier to say, get me the expenditure of the person who stays in room number A2? Much faster, much easier, right? So that is the transition from NumPy to pandas, right? From mathematics to data analysis. So anyway, we will study both in this session, as I told you before, right? Then slowly you can transition into the analysis part. So here, if I say, okay, get me the age and expenditure of the person whose details are in row with name 0, right? So then I can do df.loc 0 and then put age and expenditure in a list. So now it's a tuple. Now this is the, so in NumPy also we could specify that, right? So inside the tuple, the first element is the row index, second element is column index. The second element you can put a list with the column names. So here I put age and expenditure and I put 0. Now I'll get age and expenditure for whoever is in observation named 0. Okay. For example, in tempdf, if I take tempdf now, and I want the age and the expenditure of the people who stay in room A1 and A7. Then that's very simple. Tempdf loc, create a list with A1, A7. For the rows, create a list with age expenditure, print. You'll get A1, A7, age expenditure. Okay. Now, if you want continuous slices, that also you can do. Right. All of this is imported from NumPy access. Okay. So if you want continuous expenditure, continuous access, you can use the colon method. Notice here we are using colon with strings. See, typically this should not really give me an answer. It should give me an error. If I just do string colon string, that makes absolutely no sense to Python, right? These are not ordinal, numeric. They are nominal. They don't have position. They don't have location. Location they have. They don't have ordering, right? So it's giving me error. But if you put this slice inside LOC, it will work. So Pandas is able to interpret that. What it's going to do is going to take from A2 to A6 and it's going to print all those observations. So suppose I want age and expenditure for all the people who are staying in room A2 to A6 and I print this. It gives me from A2 to A6. Now I want everyone to look at this result. Can you please tell me one small difference between NumPy and Pandas in this specific example? Can you tell me one small difference? Anyone? Notice the output in terms of behavior. Can anyone tell me one small difference? I'll give a hint. Hint will be obviously a couple of words. And I'm putting the hint in the chat. This is the hint. Now can someone tell me the behavioral difference of the LOC method in Pandas versus the continuous indexing slices in NumPy? Nobody? It's including the last one. Wonderful. Great. So where were we? We were in this LOC business and I told you that slicing works. Okay. So for DF, if you see the labels are 0, 1, 2, 3, 4, 5, whatever, right? So this LOC is actually accessing the Pandas labels, not the NumPy labels. And of course, slicing still works. The only difference is that it is inclusive. Okay. So in tempdf, for example, if I have tempdf here, you can do slicing on both. So when I do A2 to A6, I will get this till A6, right? And for column, I'm saying age to expenditure. So ideally, I should be getting 3 columns. So if you print this, you will get A2 to A6, 3 columns. Okay. Right. So you can do the same with the DF data frame also. I think this stuff is pretty obvious at this point. So notice that the LOC indexer is slightly different from NumPy. It is inclusive of the end position. Okay. Everything else is the same. So for example, if you do A4 colon, this means what? This means from A4 till the end. And if you do colon cuisine, this means everything from the start to cuisine. So this is what? Tempdf. So you can print that separately. It should give me A4 to A10. It should give me name age cuisine, right? It should give me name age cuisine. So here A4 to A10, name age cuisine. And what is this going to do for DF? Again, you print DF and see what's happening. That's 3 is Mr. Ahmed here. So from 3 it goes to 9, right? 3 to end. And then for cuisine, it is from beginning to cuisine. So it will go from room to cuisine in this case. So now you have room to cuisine, 3 to 9. Okay. So the indexing and slicing operations are quite similar to NumPy arrays, but not exactly the same in LOC. Okay, fine. Now let's quickly sort the quizzes out, and then after that I'll launch the end poll, and then we can close the session. And again, just a reiteration, guys, please do give your feedback each time. It is valuable. Okay, quizzes please. Okay, just use LOC. Okay, which car's information is stored in 78th row of DF cars? Just use LOC. Don't even see the data frame. I don't even what are the index? I mean, at least to understand the index, you should print the data frame once. So here I can see it is integer index. So now df.loc what 78? Yeah, 78. Okay, I have a small doubt here. Okay, I have a small doubt. So let me just print df cars. Okay. Yeah. Can everyone see this Alfa Romero Quadrifoglio? I have highlighted this car, Alfa Romero Quadrifoglio. Please say yes if you can see what I've highlighted here. Would you say this is the second row of the data frame or the third row of the data frame? Third. Rajat says third. Sri Prakash says third. Abhishek says second. Parul says second. Right. This is where the language starts getting a little dicey. But see, most people are saying third row. Let's be honest here. Most people are saying third row. So for third row, the LOC should be 2. For the third row, LOC should be 2. Then if I say find 78th row, yeah, df cars.loc 77.car name. Okay, Mitsubishi Lancer. If I had said row named 78 or row number 78, then you will get the 79th row. But in English, if I'm saying get 78th row, yeah. So this is a distinction that we should all be careful about. Okay, distinction we should all be careful about. I'm not saying there's any exact right answer here, guys. I'm saying most people, if I say get the third row, you're getting with LOC 2, not LOC 3. Okay, that's all I'm saying. Okay, great, nice. What about the next quiz? What rating did Indira give to the movie Annabelle in DF movies? Can we extract this value, please? Give me the command. Indira has rated Annabelle something. What is that value? What is the command? Use LOC. Yeah, perfect. DF movies, Indra Annabelle. That's all. So that's how simple LOC is, and that's how at least for me, right? The kind of analysis that I've seen, I've done for data analysis purposes, it's important to have proper names. Okay, it's not necessary. It's important. Okay, it's easier. So I'm just copying one of the things here. df.loc Indra Annabelle. That is 6. Right. Now I think somebody had asked the question: if I have 1,000 rows, I have so big data, what to do in that case? See, I think it was Sonal, right? See, now we understand the methods. Do I even need to look at the data frame anymore? No. Okay. If I understand the methods, if I understand the data frame, that's enough for me. So I have told get the rating of Indira for Annabelle. Tuck LOC Indira Annabelle. Perfect. I didn't even see the data frame. Right. So this is my point. We train ourselves in all these things. Then when you see 100 columns, 1,000 rows, it really doesn't matter.
If you're learning to code, you probably want to master the tech world. Join our job-linked Data Science and AI Advanced Bootcamp program at upGrad and gain the skills employers are looking for. With a practical, industry-focused curriculum and hands-on projects, you will learn from seasoned experts and apply your knowledge to real-world problems. Don't miss out. Click the link in the description to start your data science journey today.
Okay, so what I'm going to do now is, so what we've been doing in the past is we've been running cells so that we can continue where we left off. But I think now we have developed enough familiarity with, these things that we know exactly which line of code we need. So let's start from that, right? Let's, what we need is we need df, we need temp df, we need what's the df movies, and we need df cars. So what you can do is you can actually just go up and select the required read commands, right? And we'll only execute those. And of course, we need to execute this import pandas. And we don't necessarily need import numpy, I think. If required, we'll import, but I don't think we need it for this session. We need, of course, df, which is our, what was it? The buffet details, right? So you can find that in reading data frames, right? So the last one, this one, yeah. So this is df. And if I remember correctly, temp df is nothing but the same buffet details with the index column set to room, right? So I'm just, collecting the commands that I need so that I don't need to run everything before that, So I need this, and then I need tempdf equal to this with index column equal to, what was that, room, and I need df cars, that's pd.read csv, and I think it's car prices.csv. In this, we did not set the index column, I think. So, and then df movies is pd.read csv. What was that, user with a capital U. So yeah, and in this we set this to user, right? So these are the 4 commands we need, I think, mostly. If we need something else, we'll check it out later. And we need import pandas as pd, okay, which I already executed in the beginning, that line. So now I can execute all of these, and these are all ready. So can we do this? Have we done this? Let me know in the chat. Okay, and always test your outputs. So does df look the way it's supposed to look? It's the buffet details with the integer indexes. Okay, then temp df is the buffet details with room indices. Then df cars is the cars data set with integer indices. And then df movies is the movies data set with user indices. Okay, always check that. So in the last lecture, we ended with LOC, which was the pandas labeled index method of accessing elements from data frames, right? Both columns and rows have 2 types of indices. One is the numpy integer indexing, which is always there, and the other one is the named label indexing, which we can place. So LOC was the one which indexed based on the labels. Okay, right? For in this case, it was we saw I think movie names, usernames, room number, and was the expenditure, those kinds of things, column names, right? Let's move on and continue with ILOC, and this should not come as any kind of surprise. ILOC is just the integer indexer, right? So for this, I'm going to use this df, which is the buffet details with the integer indices here, which has been pushed forward because I did not specify any row index, and temp df, right? And this one, in this case, I have used room as the index for the rows. So LOC, for example, if I do df LOC, this we already studied, right? This is working, 0 is working because in df we did not label the rows, right? So if I do df LOC 0, I'm getting room A1, name Shilpa, so on and so forth. Same df ILOC 0, right? So ILOC is accessing the numpy integer index, which is behind this. So there's a 0 here. You can see this 0 here. This is the pandas 0. behind that there is numpy 0, right? So iloc 0 is going to give you the same row, but it is now using the integer indexing. Now if I do tempdf.locA1, we saw that this also works, right? So it's essentially from this data frame, you're using LOC indexer and you're using this index here, A1, right? Now if I do tempdf iloc A1, definitely I can expect an error, right? So I just ran this and it gives me type error, cannot index by location index with non-integer key, right? So iloc requires integer key. That's what the error is saying. Okay, so now if I do tempdf iloc 0, I will get Shilpa age 18, whatever, right? So the first row, and that means what in Python language, it's row number 0, or you can say row with index 0, right? Which is the first row. So if you want to extract the first row when you do not have, when you have, in any case, even if you do have labeled index or you don't have labeled index, the integer index is always there. So in this case, if I do tempdf.iloc0, that is going to give me the first row, right? So similarly, you can get iloc1, iloc2, whatever. So iloc indexer is strictly positional and it accepts only integer, that is whole number arguments. Okay, and in fact, the iloc indexer references the default indexing that is at the back end. This is the numpy indexing, right? It is similar to LOC in terms of the argument structure and all, but obviously we there are differences which we are able to see now. Okay, now as usual, if you want more than one, if you want to access row and column, then you need to give a tuple. So for example, if I do df.iloc, and let me just print df here, right? So iloc 0, 1, 0, the first one refers to the row. So here obviously, I can use this one, iloc, in any data frame I can use, by the way. So it's the first row, and 1 means what? 1 means this column, second column. So 0 is the first column, room, in this data frame, and 1 is the second column, that is name. So df iloc 01 should give me Shilpa, right? So 0 is the first row, and then column number 1 means second column, right? This is the element I got. Right now, tempdf, in tempdf, if you see the 0 index here for iloc will again, it will index the first row, right? And 1 in this case will index the age because room has gone into the index. So now the first column is name and the second column is age. So 1 here will refer to the age column. So if I do tempdf iloc 0, 1, I should get 18. Okay, here I can get 18. Right, so again, all the same rules apply. The only difference, for example, here if I show you df.iloc 0 to 5, right? So here let me print df, and in df it has 0, 1, 2, 3, 4, 5, right? Now if I take 0 to 5 and then the first column, that is, column with index 1, which is the second column, by the way, name. I told you that this language is going to be a little weird, and I think sooner or later our minds will be understanding this language better than the English that we are speaking. Okay, so df.iloc 0 to 5, 1, it's going to give me name and it's going to give me what? That's the only thing that we need to see, right? Now in this case, it does not include 5. Why it does not include 5? Because this is based on numpy indexing, right? So you're using iloc, which is strictly based on numpy indexing. So you're using the integer index on the backend. Okay, so here when you do 0 to 5, 5 is exclusive, which is why you got Shilpa, Jasprit, Dominic, Ahmed, Joseph, 0 to 4. Okay, and this 1 gave you the column, second column. All the other things remain the same, right? You can slice, you can do lists, all that you can do. So if I do 0 to 5, 1 to 3, what will happen? 5 is excluded, 3 is excluded. So I will get 0, 1, 2, 3. I will get name and age, and I will get 0 to 4. So I got name and age for 0 to 4. Okay. So note that the iloc indexer is closer to the indexing behavior when accessing elements from numpy arrays. The reason that it's closer, it's because it's exactly built on top of that, right? It is exclusive of the end position. It is almost exactly the same as numpy. And here, whatever you could do with numpy array indexing, you can do using iloc for data frames. So you can even do things like this, right? So if you want row 0 to 7 and you want column 0 to 3, and what does that mean for df? What does that mean? 0 to 7 is what? Shilpa, Dominic, Preeti. And 0 to 3 column means what? Room, age, cuisine, I think, right? So let's print and see. Room, age, cuisine, and 0 to 7, right? These guys. Yeah, everything is clear. Let me know in the chat if everyone is, you know, in the zone. We are all on the same page. We are all in the zone now. Wonderful. Great. So great. Move on to the quizzes, right? There's no complication or magic here. We know LOC, we know ILOC, you know, we've gone through the hard work of NumPy. So Pandas should be easier. Yeah. Okay. Which car's information is stored in the 78th row of DF cars data frame? Use ILOC, give me the command. And remember 78th in English language means what in Python language. Okay. So, and sure, you can try printing the data frame, but try like challenge yourself that without printing the data frame, can you just imagine and get the command? Okay. But yeah, typically it's okay to print and study the data frame. It's fine. Just an additional challenge. Y comma 2. What are we getting, Ashish? Let me see. Ashish says comma 2. Oh, name. All right. Nice. Good. Yeah. Wonderful. That is right. So I mean, yeah, that's a really specific answer, Ashish. Theorian, your answer is also correct. No problem. Your ILOC is correct. Ashish, your answer is more specific, which I think, yeah, that's quite interesting. So I think that's much more pinpoint answer, right, to the question. Which car's information is stored here? So now you're telling to someone which car's information is there, you know, then to the point, if I have to say, then yes, ILOC 77,2. Correct. So yeah, this may be a bit hard if you do not print and study the data frame. And by the way, you can just print the data frame. I usually just print head 2 so that it does not occupy too much space. Then you can see actually, you know, what columns are there. And car name is obviously 0, 1, 2, which is why 2 is here. And 78th row means we are using ILOC 77. So the integer column index is 8 for Annabelle. And then count again from 0 here. 0, 1, 2, 3, 4, 5, 6, 7, 8. Start from 0. So I think it is DF ILOC 88. Yeah. DF movies ILOC 88. Yeah. Okay. Right. You have to do the counting. And there's a reason that we are doing these quizzes. First, let's solve the quizzes. Then I'll talk about it. Right. Next, what ratings did Manish and Ravi give to the movies Thor? Same question, but use ILOC. Please give me the command. Again, remember the integer index exists, but we can't see it if we have given labels. And both row and column starts with 0. Okay, we have one answer here. DF movies, Manish and Ravi. I'm only seeing one here, 112. So that seems to be Manish, I think. I don't know. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's Manish. Okay, we are somewhere there. Manish and Ravi. So Ravi, if Manish is 12, then 13, 14, 15, 16, 17. Ravi is 17. Okay, so I need to put this in another list. And here, because 0, 1, 2 is contiguous, you can also do 0 to 3 like this. Now you'll see Manish and Ravi for Thor, Justice League, and Spider-Man. Yeah. You can do list also, you can do slicing also, Ashish. Yeah. Okay, so the reason why we went through this exercise. So when you have much larger data frames, okay, ILOC becomes a little tedious to use. So this whole exercise, right, LOC we did yesterday, ILOC we are doing today. Ideally, we should do both in one day so that we get the comparison properly, but it's fine. We remember LOC. So, yeah, that's correct, Akash. Ashish, Akash is correct. You can also use integer index. Sorry, what am I saying? You can also use continuous indexing, right? So 0, 1, 2 is continuous. You can do 0 to 3 also. Yeah? That also is correct. So the point is, when the data frame is very large, ILOC becomes extremely tedious to use. Okay. which is why we usually, when we do data analysis, it's typically a good practice to give some unique column which has like unique identifier as the index. So in the buffet details data frame, I gave a column called room. Room has to be unique, right? So in one data table, how much did the person or persons in one room, how much did they spend on the hotel buffet or whatever. So I need a unique identifier there. So you see the decision making that you need to do. If you are not able to find a proper unique identifier for your row index, then you have to live with integer index. Okay, so that time 0 1 2 3 4 will be there. If you are able to find a good unique identifier for your row index, then you put that and you can use that. So LOC and ILOC both have their uses. Typically in analysis, it's easier if you do LOC for obvious reasons, right? ILOC becomes more technical, more abstract, more difficult to use. But in case you're doing things like automatic transformations and maybe loops and things like that, then that time you can think of using ILOC. Okay, the point of this was to show you the advantage and disadvantage, both LOC and ILOC, and of course we saw the direct access method also before. Okay, now having said that, there are some additional indexers which it's worth mentioning and worth exploring if later you can explore more. So we have a couple of indexers called at and iat. Okay, they are similar to LOC and ILOC. So what at does is so both of these give you one element basically. LOC and ILOC and the direct access method give you multiple elements if you want, right? At and iat will give you one element. So they are essentially single element querying operators. Okay. So at obviously is similar to LOC and iat is similar to ILOC. So for DF, for example, if I take DF, if I say which element is at 3 and expenditure. So 3 means this and expenditure is this. Therefore, I should get 19.54. Okay, so it extracts one element. Similarly, if I print tempdf say, and here I'm asking what is the preferred cuisine of the person or persons in room number A3, right? So that's what at does for you. So A3 and then cuisine. So that's Indian, right? I do this and I get Indian. Similarly, iat, these are integer indexers. So if you go back to df, what is iat 2 comma 3? That's 2 is here, 0 1 2 and then 0 1 2 3 cuisine. This should be Indian, right? Okay. Similarly, tempdf iat 4 comma 3. So 4 is obviously not A4, and that's the point. That's the difference between ILOC LOC. This is not 4. 0 1 2 3 4. 4 is actually A5. And 3 you have to count again 0 1 2 3. So cuisine of A5 Indian, that's what you're using the iat. Okay, which sorry maybe it's the wrong data. 0 1 2 3 is expenditure, sorry. Yeah, so you start with 0 here, 0 1 2 3. So third column with integer index 3 is expenditure, which is what I'm pulling out here, 3. If I wanted cuisine, I will do 2 Indian. Okay, so these things access single elements. They have its uses, of course. These are single query elements. You can, of course, do the same thing using LOC and ILOC. These are just more specified operators. Okay. Now, and since we are still discussing accessing, I'll show you other access methods. Now, LOC, direct access, ILOC. These are the most important major fundamental level access methods. Now I'm giving you examples of various different access methods which are typically used in different cases. So at iat, when you want single elements, sure, when you're doing very simple queries, you can do that. You can also access columns by data type. Very interesting. So if I just do, for example, df, and I check df d types. Okay, let me check the data types. So room is object right now, name is object, cuisine is object, age is integer, clearly integer, and expenditure is float. Okay, so now there's a inbuilt command for the data frame object called select d types. Okay, this also has its uses. Okay, so if you want to select only object type, then you can say df select d types include equal to object. Okay, so the basic parameter here is include, and if which is the first parameter. So if you know the parameter, you don't need to use it as long as you know that it's the first parameter. Okay, the parameter name is include. So select D types include equal to object. So if I do that, it will not give me age and expenditure. So it is only giving me subset of the data frame where the columns are object data type. So here you can see these are all object. Okay. I can also use this command to get integers and floats and things like that. So if I do df select d types integer, this gives me the integer features in my data set. Float, if you do, you will get float features in your data set, and so on. So basically you can access columns or features based on their data types also, and you can explore this further on your own. Okay, I've given you some examples here. You're free to explore more. Now we've done this in NumPy, I think, right? Conditional access, which is also called Boolean indexing. We did a similar exercise in series also, I think. So this is very common, right? Because most of data analysis involves conditional analysis, right? Whose expenditure is more than so much, or which factory units profit is less than certain value, right? So conditional indexing becomes very important, which of course is transported from NumPy, put into series, transported from series, put into DataFrame. So everything is coming from your NumPy access only. So suppose I have DF, and these are in dollars, by the way, the expenditure, and I can ask the question, where is my data frame's expenditure greater than 15? Now see the syntax for this. Okay, DF bracket expenditure greater than 15. Okay, so you're basically querying using the column. So if you print this, you will get, what is the output? What's the output here? It's a series. Okay, so df column, this itself is a series. Okay, this is a series. We know that every column is a Pandas series, that greater than 15. So then it gives you an output series with the row indices 0, 1, 2, 3. These are your row indices. So wherever the expenditure is greater than 15, it will be true. Wherever it is less than or equal to 15, it will be false. Okay, so now you can use this Boolean series to subset your data frame, right? So this whole Boolean condition, this output series, you can directly put it inside your data frame using the basic direct access method, that is square brackets, right? So if I just do this, it will give me the subset of the data frame where this condition is true. Okay, so note that. So what are the things to remember here? This is a series, it's a Boolean series. You're with the row indexes matching with the actual data frame row indices 0, 1, 2, 3, 4. So for all the rows, it is going to give me true, false for the condition that you put here. Now this series you can use to direct access from the data frame. So here df bracket df expenditure greater than 15. So then it gives me the subset of the data frame where the expenditure is greater than 15. It also gives me all the other information. Okay, if you only wanted the column, then treat it as a series, right? So instead of df bracket df expenditure, you can just put df expenditure, then df expenditure, like this, right? I hope that made sense. So this part is now already the subset of the data frame, which is a series, right? And and this output is a series. This output series you are now again indexing using the Boolean output, true, false, true, false, true, false. Okay, so if you want the full data frame, use the logical condition within direct access method of df. If you want only a subset, then you can actually specify that subset here. So here I can also do expenditure comma room, whatever. So now it is going to give me expenditure and room wherever expenditure is greater than 15. Okay, so here I'm using a combination of operations. I'm doing subset access plus conditional access. Okay, so as I told you yesterday, just keep in mind what are the outputs, and then it will be easier to understand this. Now we can even put conditions together, right? So df expenditure greater than 15, I have these, right? And already I think this should start making sense, why I should actually label my indices, because right now it is 0, 1, 2, 3, 4, and it says 0 true, 1 true, 3 true. So what information am I getting from this? I'm just getting that the row, the first row of my data frame, whoever it is, expenditure is greater than 15. The second row of my data frame, whoever it is, expenditure greater than 15. So if you want to increase the richness of the information, we should always set the row index as proper labels. Okay, in this case, room is a good example. Anyway, let us first do with df. Okay, so this is one series. Now we can also use other logical conditions. So suppose I want to know cuisine, and I want to know which of the observations in my data frame have spent money on Indian cuisine, right? Their preferred cuisine is Indian cuisine. So I'll say df bracket cuisine. So what is this actually? This is a series, isn't it? This is actually a series output. So this series output, now you're checking whether it is equal to Indian. Okay, so here you're going to get wherever it's Indian true, wherever not Indian false. Now this condition and this condition, you can put it together. Okay, so if you want both to be true, then you will put and. So here you can see and. If you want either or condition, you can see here there is a or. So for or, we will use this straight slash operator, right? Shift and then backslash. So you'll get the straight slash operator. For and, we know we will be using the and operator. So now if I take these two series and do a and operation between them, then true and true will be true, false and false will be false, true and false will be false. So wherever both are true, it will be true. So you can check that output. So you'll get true, false, true, false. So if you see here, true and true is true, true and false is false, and so on. Okay, so now you can use this complete logical condition to subset your data frame. So take this whole logical condition, right? Take this whole logical condition and use it as direct subset from the data frame. Okay, so now you will get wherever expenditure is greater than 15 and cuisine is Indian. So what is this subset really? Who of my customers in the hotel are spending a lot of money on Indian food? Basically, this is the answer to that question, right? Now I can even do more on top of this. Now I have the full data frame and I want to answer the question, give me the room numbers of the people in my hotel who are spending a lot of money on Indian food. Then I will do something. Then as hotel manager, I can provide to those rooms additional pamphlets of more Indian food, isn't it? So this is where data analysis is used. Okay, hope it's becoming clear. So if I just do df whatever, this whole condition and then room, I'll get A1, A3, A5. Now I'll just take this list and tell to my the management services in the hotel, you know what, these rooms, I think they really like Indian food. They're spending a lot. Just can we come up with a quick pamphlet of our new Indian delicacies, and we'll just give the pamphlet to these rooms, right? It's becoming clear, yeah? Data analysis, how useful it is, right? So another thing is that you don't need to put this at the end. As I told you, you can subset first, then you can put the condition, or you can put the condition first, subset, then you can take the subset, right? All that you can do. All right. So what does this command tell you? This command tells you that you can do the data frame subsetting with the conditional access first. Output is a data frame. And obviously, if the output is a data frame, you can do whatever you want with the data frame, like accessing, LOC, everything you can do, right? Because this output is a data frame. Now, what do I want from this conditional data frame? I want the room number. So this whole thing, how do we read it? It says subset my original data frame, use and keep all the columns wherever expenditure is greater than 15 and cuisine is Indian. And then from the data frame, give me the room column. That's how you read this. And that's what it is doing. Now the interesting thing is what? That you can actually subset the data frame first and then you can put the logical condition. So for example, here I've shown you, see, this is the same logical condition with the square bracket access method, right? So I'll not remove it. I'll remove this and I'll print df room. Now you will say this is a series, correct? This is a series. Now this is my logical access condition, isn't it? This is my logical access condition. Let me just remove the square brackets that I can print it. So this is my logical series. Now I have done basics of Pandas series before. We have done this before, right? You can access the original series if your indices match and you have the true false logical values of that series based on some condition. So since df room is a series, and I have my series output for the same row indices 0, 1, 2, 3, 4, 5, 6, 7. These two are the exact same series in terms of keys, right? Index or key, what do you want to call, they are the same, right? Because they come from the same data frame. So now this logical condition can be used to access or to subset from this series, DF room. So DF room is all the rooms series, right? And then you can access this using the logical condition, which is expenditure greater than 15 and cuisine equal to India. So you might be thinking expenditure cuisine don't exist. Well, it exists for DF. It exists for DF. So the object I'm using here to condition this is what? DF expenditure, which is what? DF. DF has all these columns. But the output is actually a series with the row indices. Getting clear now? So now you can go back and access the row indices where the output is true and false, it will not show. Now, once you access the row index, it depends on which object you are taking subset. If you're taking subset from data frame, it will show you all the columns of data frame. If you're taking subset from series, it will show you the values of the series where the condition is true. So what it has done is essentially subsetted the row indices. Okay. What it has done is subsetted the row indices. Then those row indices you can match. Either you can match with one column, which is a series, or you can match with the full data frame because it's the exact same row index. Okay, that is the thing that we are learning here. Okay, so for example, if I just do df bracket name, you can see the row index 0, 1, 2, 3, 4. This will become much clearer if you use tempdf. So for example, let me actually use tempdf for the next one. So here, let me use tempdf. Okay. So let's say tempdf, this is my room and whatnot. Now suppose here I do tempdf bracket name. Okay, what is the index? A1, A2, A3. It is the actual row index from the data frame. So the subset series that you got is still matching with the same row index from the data frame. So now if I say something like tempdf say expenditure, right? Tempdf expenditure greater than 15. What is the output? True, 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 false, false, false. But what is the index? Index is still room from the original data frame. So all of these components are series from that same data frame. Now this logical output series, the Boolean series, true, false, true, false, true, false, it's essentially saying A1 true, A2 true, A3 true, A6 false, A7 false. Now this, if I use to access any other component from the original data frame, wherever it is true, it will give me output. Wherever it is false, it will not give me output. So for example, tempdf name, if I now want to access, so I'm putting another square bracket, correct? This is a series. So square bracket for, calling out the index. Now here, if I say A1, it will give me Shilpa. If I do A2, this will give me Jasprit, correct? So I'm indexing using the keys. Now if I delete this and print again, it will give me the full series. So inside the square brackets, I can actually use the Boolean series. What will that give me? It will give me the subset of wherever it is true. So the index, row index, wherever it is true, that row index will match with the original. So here you see A1, A2, A3, A4, A5, A6, A7. So wherever this is true, that will be retained. So Shilpa will be retained. Whoever A6 is not retained, Saju is not retained. So now this logical condition, I can put it here. Shilpa, Jasprit, Dominic, Ahmed, Joseph. This thing works for the data frame also. So if I just remove this tempdf name, which is a series, right? Now it's only a data frame. I removed the column. So now full data frame. I print it. I will get the subset of the data frame where this condition is true. You can use this for subsets, any subset of the data frame, including the data frame. I hope we remember set theory, set language from mathematics. Any subset of the original data frame means what? The data frame is a subset of the data frame. 2, 3 columns from the data frame is also a subset of the data frame. Any single column from the data frame is also a subset of the data frame. So when you do logical accessing, it directly goes to the row index, which is common for all of these subsets of the data frame, which is what I showed you. Is it clear, guys? Please put in the chat if it is clear. Any more doubts on this? No doubts? Okay, great. So now the OR condition, this is something, OR means what? OR means either or, okay? Either this is true or that is true. it's a looser condition, right? It's not a strict condition in analysis. But point is, you can of course combine logicals using or also. So if you do expenditure greater than 15 or cuisine equal to Indian, then you can get the rooms where either the expenditure is high or the cuisine is Indian. Where is this useful? Maybe my hotel is efficient in creating Indian cuisine, so I'm saving money there. So probably I want to know who's uh, preferring Indian cuisine, so I can sell more Indian cuisine to them. Or if people are spending a lot on non-Indian cuisine, still my cost of creating non-Indian cuisine may be higher, but if those rooms are spending more on those, I'm okay with that, right? So this is more of a loose condition. So basically the hotel manager might say, see, Indian cuisine, we are obviously creating a cheap rate, so definitely find out the rooms who are having Indian cuisine. Also, regardless of the cuisine, if the room is spending a lot, that means that they really prefer and they're ready to pay for the cuisine. So find out who are those rooms. Doesn't matter if they have Indian cuisine or any other cuisine, no problem. So this is a loser condition. So for this you will use or. Okay, and I hope this access method is clear. Right. There's also some very interesting access methods like this one. So is in, okay, there is this dot is in method, which is a series method and a data frame method, of course. But for example, if I want to know whether which cuisine is either Indian or Chinese, so then I can do, for example, df cuisine dot is in, and that literally means is in. Okay, this cuisine is in this list or not. Okay, so df cuisine dot is in Indian Chinese. Now let me just print df to see what my cuisine is. Indian, American, Chinese. Okay, so df cuisine dot is in Indian Chinese. So obviously I should get, Shilpa, Jaspreet, Dominic, Ahmed. No, I shouldn't get Jaspreet. Sorry, Shilpa, Dominic, Joseph, Saju, Monica, so on. So everyone except American, right? So if I do that, again you will get a series. Okay, so again it's showing whose cuisine or which row's cuisine column value is in this list. Okay, so is Indian in this list? Yes. Is American in this list? No. Okay, so like that. And I hope everybody is aware of this tilde operator. Can you put in the chat if we know what tilde means? This one, this operator here. No. Okay, it means not. Okay, tilde means not, so opposite. Tilde means not. Okay, opposite. So here, wherever true, false, true, false, true, false, it's going to switch. Complement. Yeah, it's basically the logical complement. So if you want to know who is not in Indian and Chinese, who is not having Indian Chinese cuisine, then you use not in front of the Boolean series. So not df cuisine is in Indian Chinese means American, by the way. So I should get true for this one, that is index 1, and I should get true for Ahmad. I should get true for Preeti. So I should get 1, 3 and 7. Let's see, right? So here true you will get at 1, 3, 7. Okay, so not is basically the complement operator, opposite. Okay, so obviously you can now use these series. Not in. Good question. You can check that. I don't remember whether not is in. You mean not is in? I don't think it's there. So the reason it's not there is probably because it's so simple to complement the series. I think, right? Check it out. Pandas not is in. I don't think so. No, is in operator is there, but not will not be there because it's simple. It's just not of the output series. And by the way, logical operations are the most easiest thing for a computer to do. Correct? 10 10 10. Right? So that probably there was no reason to build it because is in operator is there. So function is there, so you don't need the not is in function. What can we do with these Boolean series, guys? I just explained to you. You can do you can subset your data frame, then apply the Boolean series. You can apply the Boolean series on the data set, then subset the data set that you get, right? Chain the commands and see what's happening. Okay, by the way, just to clarify, I am chaining commands very easily because I have a lot of practice with these things and a lot of experience with these things. If you're feeling that you need to break it down into steps, please break it down into steps, get a feel for how it is working, then start chaining commands. Okay, so please feel free to learn that way. All right. Anyway, so this Boolean series, what can I do? Subset the data frame. That's all. So this is just, and by the way, I hope we know, that this is not the only way to do. This is a more sort of user-friendly, efficient way to do, but this is not the only way to get this series. Can someone tell me, is there any other way to do this? This one, DF cuisine is in, take this one for example. DF cuisine is in Indian Chinese. Is there another way to access and get the same output series? Anyone? Any guesses? It's okay. Feel free to answer. Or operator. Exactly. Yeah, equal to with or. Correct. So if I just do df cuisine equal to what? Indian, and then bracket, I have to put bracket, otherwise it will get ambiguous. Or df cuisine equal to Chinese. If you see, these two series are exactly the same. Okay, and of course there's another method. Given you know all the different possible values of the cuisine variable, there is another method obviously which is not American. Okay, for that you need to know the complete cuisine variable. If you do know the complete cuisine variable, then I can do not df cuisine equal to American, and that will also give me the exact same series. Okay, so hope all these logicals are making sense to you guys. Let's practice this. That's the best way to get a feel for it. How many cars in the DF cars data frame are sedans? Please feel free to print the data frame and study it. And please give me the command. What are sedans, by the way? I think that kind of car, no? Maruti Swift. And I don't know, is Ambassador a sedan? I don't know. Do we have any car enthusiasts, car experts in this audience? I'm just saying, I'm not really a car expert, okay? So as far as I know, sedan is the car which has like this and then goes up and then back like this. Right? It goes like this, like this, like this, I think. Anyway, Abhishek says length. Okay, how many cars? Correct. Okay. Sauradeep, DF cars car body is in sedan. Correct. Question is length. So change the command. And here Abhishek says length DF cars car name sedan. I think this one will work. As you can see, guys, sedans. So obviously this is where, in data analysis, little bit of domain knowledge is required. So if I have absolutely no idea what is a sedan, then I have to sit and study this data frame for a long time. Then only I'll find out, okay, car body has something called sedan. Suppose your car body, all the features, all the first, let's say 100 values of car body is convertible. So you don't even see sedan. Then what? So this is where we need data analysis is, it separates from abstract mathematics. Abstract mathematics is different. Mathematics is different. Data analysis, we need to be in touch with the real world. We need to know what we are talking about really. So for example, I know for some reason, I don't know, but I know that sedan is something like this. It's a car type, as someone pointed out, type of car, right? Model, Abhishek said it's a type of car. So we need to know something about the data. Okay, that much is required. So studying the data, knowing what's in the data, little bit knowledge also will help to do much better data analysis. Okay, so DF cars, what is Abhishek's command here? Len DF car sedan. Yeah. So in car body, I can see there is something called sedan. Once I find that much, it becomes obvious that I need to just do len df cars car name equal to sedan. Answer is 205. Wow, there are 205. Let's quickly find the percentage. What? Our name, hey Abhishek, you made a mistake. That's why I was a little surprised here. 205? Not possible, right? Not possible. And length also will not help you here, by the way. Length of a false series is also okay. So let's go back here. So here we have some series. For example, let's take this series. DF cuisine is in Indian, whatever, right? So here, if I just do length of the series, it will give me full length. It will give me all the length. 10. It will give me all the length, right? So what I need to do? What I need to do? I can't take the length of the Boolean series. I have to take the length of the subset data frame. Using the Boolean series, I have to subset my data frame, then I have to take the length. The Boolean series length is total 10. This is what I've been explaining till now. Whatever logical condition you apply, it will give the true false value for all the rows. So the length of that series is what? Equal to the length of the data frame. Right? Only when you use that Boolean series to subset your data frame, then only you will get the subset data frame. And from that I have to find length. So this is point number 1. Second point, car body is not the one I have to use. Sorry, I have used car name. I'm very confused. Okay, Abhishek has corrected. Okay, car body is the one I have to use. Yeah. So basically what I need to do, see guys, basically what I need to do, df cars car body. This is the feature, car body equal to sedan. Okay. So now it will give me false true, false true, false true. Now I have to use this condition to subset my original data frame. Okay, what happened here? Boolean series key will be reindexed to match data frame index. Yeah, fine, whatever. Okay, df is wrong. Yeah, that's why I'm getting warning. Df cars. So df cars car body equal to sedan. Now this gives me the subset, and in subset you can see 96 rows here. So now on this I can apply length. Yeah, this new one I think is the same. Yeah, this is correct. Equal to sedan. Answer is 96. Are we clear? So there are 96 cars in my data frame which have car body sedan. Okay. Next, let's try this one. How many users in the DF movies data frame rated more than 7 for Thor and Spider-Man both, but rated less 7 or less for Doolittle? Okay, these are all movies. So just print it. Take your time, guys, and give me the command for this one. This one. DF movies Thor, Spider-Man greater than 7. That's the only thing that looks suspicious. And the reason is ambiguity. Okay. See, Boolean logic is the most fundamental type of logic, most atomic type of logic. It's the Boolean logic works in 0, 1 bits. It's not capable. So Boolean logic is a very low level, right? Only the atomic bits. So when you have written Thor, Spider-Man greater than 7, how does DF movies know which one you are asking greater than 7? Is it both? Is it any one? We don't. DF movies does not know. Right? So Boolean logic is a very atomic level logic. So you have to break that into two parts. Because of ambiguity, it does not know. Are you asking both 7? In that case, you should use AND. Are you asking, what is that? Any one greater than 7? In that case, you should use OR. Correct? So this will give you error because Boolean logic cannot handle such complex things, right? So you're saying 2 things greater than 7. This syntax is not understood by Boolean logic. Okay, Akash has given a code. Let me check this one. DF movies. Okay, indexing using DF movies Thor greater than 7. Okay, and DF movies Spider-Man greater than 7. And DF movies Doolittle less than equal to 7. Yes, this should work. Let's check. So 6 people. So in my DF movies data frame, 6 users have rated more than 7 for Thor and Spider-Man, but rated 7 or less for Doolittle. Okay. Okay. So let's go to the next quiz, guys, and we'll do this without chaining commands. How many cars in the DF cars data frame are convertibles with a city mileage more than 20 and price less than 15,000? It has 3 conditions. Please look at the screen. I'm going to show this step by step. Those who want to do it quickly in one line, please go ahead. Others who want to see the logic, please see the screen. Okay. So now what I do is first I print my DF cars data frame, and how many cars are convertible? So convertible, the word is here. Okay, it's a type of car body. So that is one condition that I need. What is that one condition? DF cars are body equal to convertible. Okay, now this we all know the output is going to be series. I'm going to store this series with a name. I'm going to say car body convertible Boolean series. That's a very big name, so I'm just going to call it convertible Boolean. Okay, I'll save it here. Next, city mileage more than 20. Now where is the city mileage business? If you check the columns, you will find city mpg here. Another way to check the columns, dfcars.columns. Correct. Let's do this, and here you will see there is something called city mpg. Okay, let me print my dfcars again. So I have city mpg here. So what is saying? City mileage greater than 20. So now I need mileage boolean equal to df cars. What is the name of the column? City mpg. I can actually just copy from here, right? df cars city mpg. What greater than 20? What is this going to be? It's a series output, correct? So see, again, it's a series output, Boolean series with the row indices matching with the data frame. Okay, so here on the left side, it's matching with the data frame. So this I will store it in mileage underscore Boolean. Okay. Next, price less than 15,000. Go back to DF cars, search your columns. There is something called price. So now price Boolean equal to DF cars price. Oh, sorry, DF cars price. Yeah. What do I need? Less than 15,000. So this is again a Boolean series with true false for the row indices of the data frame. I'm storing in price Boolean. Now question says how many cars in the DF cars data frame are convertibles with city mileage more than 20 and price less than. So all 3 Boolean conditions should be true. So now I can create a final, let's call it final Boolean. Final Boolean series is nothing but convertible Boolean and where is and mileage Boolean and price Boolean. All 3 should be true. So now final Boolean has been executed. We can check it. Obviously it is going to be a series. It is true false series, Boolean series with row indices matching with the data frame. Correct. So this contains the information of all 3 logical conditions, right? Final Boolean. What can I do now? I can just access my data frame using okay, wrong data frame, df cars. I can just access my data frame using this final Boolean. Only 2 cars, by the way. Only 2 cars are convertible with mileage greater than 20 and price less than 15,000. Those 2 cars are Alfa Romero Giulia something and VW Dasher, whatever that is. I don't know the cars. Okay. Now, if you want the length of this thing, what do you do? Just use the len method, which uses curved brackets. Okay. So len df cars with final Boolean, that gives answer 2. Is it step by step clear now? Yeah, please try. Please try. I want everyone to. Thanks, Sonal. Others, I hope it is becoming clear this Boolean. See, I was expecting that we can change the commands, but if it's becoming difficult, you use this. Do it step by step. And please solve the other also step by step. Okay, so as I said, if you are able to solve one of these, then definitely you can solve all of these, right? Okay, let's now move on to the next part, and let me just see, right? I have operations, then I have statistics, I think, yeah, and then other data frame operations. Okay, let's do some basic arithmetic and data type operations. There is Tom here due to his network. Unfortunate. I understand though. So now we move on to standard operations, you can say standard operations in data frame. So we will study some important methods used to manipulate data in data frame. So changing the values and things like that. Okay. So we will look at some important methods, while briefly looking at some other important methods. So most important methods we'll go in detail. Other important methods which are maybe situational methods we will go through briefly. And I think there's a bit in the end which I feel is moderately important. So that's something that I might choose to leave it to you for self-study, which is at the end, because anyway we'll be using that in later topics. Okay. So as written here, as I'm saying here, you will work with all these methods throughout your data science journey, learning journey and beyond. Okay. Right. So we'll start with example 1, working with data types. So we already know this, right? Print your df, you saw your data frame here, print df.d types, you will get object, int, whatever. So the thing is, you can convert data types very easily in pandas. So for example, if I take df expenditure, right now it is float. The way to convert it to some other data type is this method here, dot as type. So it will take that series and then convert the data type of the series. So if I just do df expenditure, which is right now float 64, right, float data, I will do dot as type integer. If I do that, you can see now all my float values are gone and it has been rounded to integers. Here you see 24.65, 18.54, 27.66, so on and so forth, right? So here dot as type integer. Okay. So now if you check your original data frame, no change. Why there is no change? It is not in place. Akash, excellent question, right? It is not in place. Okay, definitely not in place, right? The original data frame has not changed. Okay. So if you want to do in place, you should overwrite the column. Okay. So if you really want to do in place, which I don't want to do here, the command that I'm not going to execute this command, but if you want to do in place, this is what you should do. Df expenditure equal to. So you're basically rewriting the series, isn't it? Right. This new series you are putting in the place of the old series. Where is this old series? This old series is part of df. Okay. So this is one method that you can do. But typically if you want to do some changing data types and things like that, you might sort of do for some columns. There is okay, for example, before going to that method, I'll show you some other things. So suppose df age, if I do as type int, obviously this is not going to do anything because age is already integer, right? So this won't do anything. Now here it says data type int 32. The thing is, I can convert up. So if I do df age dot as type object, now age is object data type. These 1832, all of this object. In fact, I can even convert it to string. So df dot as type string. Now age, it says object, but what is object here? The panda series is object. So now if I just pull out the first element, which is 18, you can see it is a string. How did I pull out the first element, guys? I just used indexing method. How did I know that I can use indexing? Output is a series. Since the output of this thing is a series, I can use indexing. Okay, that gave me 18. So this is one way to convert the data types. Okay, all of these are not in place. Now there is a very interesting method which is you can use in most cases, but you should be careful sometimes, which is called convert d types. What it does is it converts the data types of the column series in your data frame to what Python believes is the best data type for the series. So right now, if you see df.d types, room is object, name is object, cuisine is object. So if you do convert d types, if you just do like data frame dot convert d types and assign it to the new data frame, okay, don't override the old one, assign to new data type. Now if you see the data types of the new data frame, now you get very clean, you know, room is a string data type, name is a string, cuisine is string, age is in 64, expenditure flow 64. So uh, convert d types is a nice method which correctly assigns, you know, the data type which is best for that series. The only thing is that sometimes maybe you don't want that. Typically it's okay to do that, but you need to take judgment calls. Do I really want this thing to be you know, a string? Do I want it to be an integer? So on and so forth. So use it, but always check the output. If you are satisfied with the output, then you know, take the new data types. Okay. So as I say here, converting data type as per suggestion from Panda is generally fine. Okay, these are universal libraries, NumPy, Panda. Typically, you know, the methods are well thought out, but there may be some cases, very rare cases, where you may need to check. Okay, do I want this conversion or not? All right, so we'll continue with some important operations, okay, with data frames. So example 2, arithmetic and intercolumn operations. These are quite similar because they are essentially series to series, you know, inter-series operations, which you've already done one before, right? In the series method, we did this prepaid amount and bill amount, right? And we found the, you know, series comparison. So it's actually comparing two series. So they're quite similar. So suppose I take my DF. This is my what do you call it? The buffet details, right? And suppose you know, I want to add 10 to my expenditure values. Now remember, this is very similar to the NumPy array operations. These are broadcast operations, right? So if I do DF expenditure plus 10, what's it going to do? It's going to add 10 to all of the expenditure values. Okay, so DF expenditure plus 10, 24.65 plus 10, 34.65, 18.54 plus 10 is 28.54, so on. So basically the same broadcasting operations from NumPy, right? So the same thing you can apply to DF expenditure. Suppose I want to do -5, and obviously these are not in place. Okay, these are not in place. So if you print DF again, your original values will be there: 24.65, 18.54, so on. Okay. So suppose I want to subtract, I can do -5 from expenditure. So now I have 19, 13, 12, 14. It is all -5, 24 -5, 18 -5, so on and so forth. Similarly, I can do multiplication also, DF expenditure times 2. Okay, whatever my DF values are, 24, 18, 27 into 2, right? So these are all multiplied by 2. I can do division, for example. So DF expenditure divided by 3. Again, it's 24, 18, 27, all of these. And you're dividing by 3, 8, 6, 9, 6.5, whatever. What are the things to note? 1, output is series. 2, broadcast operations from NumPy arrays. Okay. So you can manipulate data columns like this. Age, if you want to say plus 10, DF age plus 10, 28, 42, 29. Age into 2, 36, 64, 38. Original age is, you know, if you want to see, you can see it here. 18, 32, whatever, right? So plus 10 gives me 28, 42. Multiplying gives me 36, 64, 38, right? And so on. So obviously here we are using the basic Python operators. So these are all Python arithmetic operator syntax. Pandas also gives you its own functions, right? So if you want to add 5 to all the age elements, you can do dot add 5, right? So this is adding here. Now, as I told you before, you know, Pandas, most methods will be having in place parameter, but some of these methods will not have. Okay, for example, this add, if I'm not wrong, it does not have an in place parameter. So the only way to replace the age with the new age column is you have to replace the series itself in the Pandas data frame. I'll show you how to do that. So you have a function called add, which adds the number here, and then you know, you have a function called subtract, which subtracts the number from the age. Then you have dot mul, which multiplies the age by this number. You have dot div, which divides the age by the number, and so on. So typically we use the Python operations because they are just simpler. I think we are used to it. But Pandas offers its own inbuilt functions. Okay, so many of these inbuilt functions will match the Python basic arithmetic operations. Where it will not match is the more advanced statistical functions like mean, median, mode, and all these other things. Okay, so that's basic arithmetic operations for you. Now, if I want to do inter-column operations, and why did I put these two things together in the same example? Because they are inter-series operations in a sense. So when you're doing df expenditure minus 5, what's happening is you have a series filled with the values 5 and the same index as this series, right? So this series minus this series is exactly what is happening, right? 24.65 minus 5, 18.54 minus 5, and so on. So we can also do inter-column operations because they are also series with the same indices, with the same row indices. That is why you can do these operations. So suppose I want to add the expenditure and the age, okay, which probably doesn't have too much real meaning, but just to show how to add two columns, df age plus df expenditure. If I do this, I will get a new series. This is a new series. Okay, so this is 24.65 plus 18, which is here 42.65, 18.54 plus 32, 50.54, and so on. So what you're learning here is that with the same indices, if you have different values, you can add them, subtract them, divide them. Similar to what we did in NumPy, the same thing is being used here. Okay. So, and this works not only for integer, float, numbers, it will work for strings also. So for example, name is a string, cuisine is a string, correct? So if I add two strings using Python plus operator, what happens? It concatenates the string, correct? So this is the name, which is string, cuisine is also string. What will happen if I do df name plus df cuisine? As you can see, it produces a new series, it concatenates the element. So what's happening is element wise, Python is checking what should be the output be. So int plus float number, int plus int number, string plus string number. So element wise operations with matching series, matching index. Okay, that is what is going on here. And of course you can do bit clean operations. You can also add a blank. For example, if I add a blank here, so df name plus a white space character in string plus cuisine. So then I will get Shilpa space Indian, Jaspreet space American, Dominican space Indian, and so on. Okay. So, and one other example we'll discuss before we go on to generalizing some of these statistical things. So we have seen the round method, I think, from NumPy. It's the same thing that is here. Okay, df dot round. So if I just do df dot round, what happens? Notice round does not do anything to the string elements. Okay, obviously. So Pandas knows which function is applicable to which data type, basically. So if I do df.round, I'm actually applying round on every element in the data frame. Okay, but it will not produce any change in the string ones because round does not change the string values, but it will definitely change the integer and the float values. It is applying round on all of these values. Okay. Now, typically, this is not the way we use these functions. We identify columns which need, to be applied certain function. Then we will apply it. Then we'll maybe create a new data frame or replace the old data frame. This is typically not the way. You don't take a data frame and do dot round. It doesn't make sense. Your data frame has multiple type of columns, multiple type of features and data types. Okay. So you need to know your data frame. Then you need to manipulate the data. Okay. So for in this case, I can do, for example, df expenditure dot round. That makes more sense, right? And then I can assign this new series. I can just replace the original column with this. Okay. Of course, you can also round it to various decimals. You check the parameter here. If I want one decimal place, I put round 1 and then I get 1. I can put 2, it will round to 2 places, so on and so forth. Okay. Now, what I want to point out is that the rounding operation that I'm showing you here is actually the application of a function on the elements of the data frame. Okay. We will explore this a little more detail later because this is going to become important. What kind of functions do we need for string? What kind of functions do we need for integers, floats, those kinds of things. Okay. So so here what I'm going to do is I'm going to solve quiz number 1, okay, step by step. And then I want everyone to solve quiz number 3. Quiz number 2 and quiz number 4, I'm going to leave it for you guys to try out later. Okay. So these are a bit more, there are more operations that we need to do, right? So let's look at this. Find the mean of the city mileage and the highway mileage of each car, and please watch the screen. Let me solve this. Okay. Then you try to solve quiz 3. Okay. So here what is saying, find the mean of the city mileage and highway mileage of each car in the DF cars data frame. Add this value as a new column. Add this value as a new column to the existing data frame with a new feature name average MPG. Print the subset of the data frame, the new data frame, with the car name, city mileage, highway mileage, average mileage. Okay. So let me take this step by step. So first I'm going to check my DF cars data frame. And it's saying I need the mean, that is the average of the city and highway mileage. So I know that there is something called city MPG and highway MPG, right? So I need DF cars city MPG plus DF cars, and I can just copy the name from here, highway MPG. So if I just do this, it will give me summation. Okay, it is giving me the summation of the city MPG, highway MPG. Question is saying find the mean. So what do I need to do? I just need to divide this by 2. That's all. So put the bracket and divide by 2. Now I have the mean of these two values, city MPG and highway MPG, for all my cars. Okay. So this is step number 1. Step number 1. Let me just I have this output. Now it is saying add this value as a new column to the existing data frame with feature name average MPG. Now adding and deleting columns, there is a section at the end of the data frame which I propose that you guys should try to learn that and practice that on your own. I'll give you one instance here. Okay. So here I'm going to say df cars bracket, and I'm going to give the new column name here. That's all. So avg mpg, this is the new column name. So notice that this is a series. We all agree. Do we all agree? Please tell me in the chat that the highlighted part is a series. We all agree? Okay. Do we all also agree that the series has the exact same row indices as my original data frame DF cars? We agree? Wonderful. So now DF cars direct access average MPG is actually now going to create a column with the exact row indices of the original data frame, and therefore the series which has the mean data will directly map row to row to row to row to row, and there will be a column, new column. Okay. So let me show that DF cars average MPG equal to DF cars city MPG plus DF cars highway MPG divided by 2. Execute this, and now if I just print DF cars, and before I print DF cars, I'll show you the columns. Can you see here average MPG in DF cars.columns? So I have changed my data frame, and I think this is the first time in the complete Pandas workbook we are changing our data frame, isn't it? This is the first time we are changing our data frame. Yeah. So notice that when you change your data frame, you should be very careful. Okay. You should not lose your original data, and you should be quite clear why are you doing this, and so you should be careful when you change your original. Okay. So and that's what I add this value to the existing data frame. That is what I've done here. Okay. So as you can see, average MPG column exists. So now if I just print DF cars, and ideally what happens typically is that the new column always goes to the last. Okay. So there's average MPG, which is essentially the average of these two. So 21 plus 27, 48, divide by 2, 24. 19 plus 26, what is that? 45, divide by 2, 22.5. 24 plus 30, 54, divide by 2, 27. Okay. No, Akash, it will not change the data in the CSV file. No. When you close this notebook, everything is forgotten. So you need to save. So there is pd.toCSV. Okay. So those who are interested, I'm not going to get into this right now, but pd.to, so CSV, just search for pd.toCSV. I think it's not pandas function, it's an attribute, as in it's an inbuilt function. So df dot CSV. I believe that is how it is. But pandas, if you check the documentation, it will say pandas dot data frame dot to CSV. I think this is the way. Check the chat. I'm giving you the things, right? So if you Google it, this is the way that you will find the name of the function to CSV. So that will save as a CSV file. Yeah. Okay. Don't do that right now. Please explore that on your own later. Okay. So now I want everyone. So quiz 2 and quiz 4 I'm leaving for you guys to do later. Quiz 2 may be slightly complicated. Think about it. Do it later. Quiz number 4 doesn't seem that complicated. You can do it later. But let's do quiz number 3 right now. Okay. So I'll explain quiz number 3 steps. Let's do it. Each car in the DF cars data frame also has spatial dimensions associated with it, namely car length, car width, car height. So basically this is inches, height of car, width of car, and length of car. Okay. And there is something called curb weight, which is essentially the weight of the car in I think this is not an Indian data set, so the weight will be in pounds or something. There is curb weight. Okay, see, you cannot see all the data, which is why you should subset sometimes. Okay, so here I want what? Car length, car width, car height, and curb weight. Okay. Yeah. So this is in inches, and this I think it is in pounds, which is I think it's a measure for weight. Okay, whatever. This is the weight of the car. Curb weight is the weight of the car, and these are the spatial dimensions. Assume that all the cars are cuboidal. Okay, I know it's a funny assumption, but assume that it's all cuboidal. Okay, and then calculate the density. So do we remember formula of density? Anyone? What's the formula for density? F by A. I don't know what F by A is. Force by acceleration. So density is mass over volume. Yeah, density is mass over volume. Correct. Okay. Do we remember the formula for the volume of a cuboid? Mass over volume is correct. LBH. Yeah. Okay. So can you guys create a new feature in the original data frame under the name density? It is similar to quiz 1, what we did. Can we do this? Okay, please go ahead and do this. And after that, print the subset with the car name, car weight, spatial dimensions, and density. Okay. First, let's do the column. Okay. Right. So volume is L into B into H. Density is mass by volume. All the required columns are there. Car length is there, width is there, height is there, weight is there. Okay. It's called curb weight, and we are assuming cuboid. Okay. So this code looks messy, but it's easier because it's in one line. If you don't like this one line getting messy, then it's perfectly fine. So you just do something like car length equal to df underscore cars car length, then what is that? Car width equal to df underscore cars for car width, then car height equal to df underscore cars car height. So now I have 3 series, right? These are 3 series with my spatial dimensions. So now car volume equal to car length star car width car height. Okay. So can you all tell me what is this variable CARVOL? Do we all agree that this is going to be a series? Car wall, the one that I have defined here. First of all, do we agree car length is a series? AF cars car length, this one. Yeah, that's a series. Now I have multiplied 3 series together. Do we expect the result to be a series, Panda series? Let's check that. Yes, it is a Panda series. Okay. So this is my point. Inter-series operations will give you series. Boolean on series will give you series, right? And where is the series coming from? Each column of the data frame is a series. Okay. So obviously car volume is a series. Now because it's a series, then so what? So now if I say car weight, let's say WGT car weight equal to DF cars and what is it called, curb weight. Okay, now we all agree car weight is a series, CAR WGT it's a series, car weight is a series, right? Car volume also it's a series. Yeah, so what is series divided by series? That's also series, right? So if I just do, for example, car WGT divided by car VOL, output is a series. That's all. So this series you now have to provide to a new column. So DF cars and column name is density. So DNSIT equal to this series here. So now it's going to produce a series and store it in the original data frame. Does it say here to change the original data frame? Yes, change the original data frame. So if I do this, and then now if I check df cars columns dot column, in the end you will see something called density. And if I just print df cars, at the end you will see density. Okay. So all of this can be done in one command like this. Instead of all this, you can do in one command like this. Okay. So just do that. If you do that, it overrides the original series, by the way. So because I did this series already exists, but again I can overwrite it, no problem. And finally it says print the name, weight, spatial dimension and car density. So df cars, I think car name was 1, then what do you want? Car weight, so curb weight, spatial dimensions are here, just copy paste from here to here, right? Car length, car width, use that should be a comma, car height, and then the density, right? Volume cars equal to, explain once more. Yeah, Ankita, so just to summarize the steps, what the question is saying is that look, your df cars data frame, it has 3 columns called car length, car width and car height, which are the spatial dimensions of the car. Question also says assume that it's a cuboid. Okay, now there is another column in the data frame which is curb weight, okay, which is essentially the weight of the car in kilograms or pounds, whatever. That's also it's a series, it's a column in your data set. Question is saying calculate the density of each car and then store it as a new data frame. To calculate the density of each car and then store it as new data frame, what we have done, we have to first find the volume of each car. So volume of each car can be found using this command. Okay, df cars car length times df cars car width times df cars car height. Each of this is a series in your data frame. When you multiply, what will it do? It will do element wise multiplication. So for example here 168 into 64 into 48, that will be the first element in this series. Then next 168 into 64 into 48, again that will be the second element in the series. Next 171 into 65 into 52, that will be the third element in the series, and it will do this for all the rows. So the output of this, in fact I have calculated here, car wall. If I just say car wall equal to, and let me take df cars length into width into height, okay, and I'll print this car wall. So 168 into 64 into 48, here is the value 528019. 168 64 48, again 528019. 171 65 52, 587 592, and so on. So element wise arithmetic operations can be done for n number of rows. Here I am showing 205. You can do this for 1000, 2000, 10,000 rows. As long as you know what the columns are. That's the point. As long as you understand the columns, feel free to do the operations. So this is now giving me the volume of each car. Okay. Now having the volume of each car as a series with the index matching with my data frame, then what I can do? I can get another column from my data frame which will have the same index, and I can continue doing my operations. So what is the other column in my data frame? Curb weight. So if you see, you just print this curve weight here, that also has the exact same indices. Why? Because it's from the same data frame. So now these two series have the exact same indices. Okay. And now I can do weight divided by this series here, car volume. What it's going to do is going to do 2548 divide by this value. Then next one 2548 divide by this value. Next 2823 divide by this value. And we know that the set of arithmetic operations that we are doing is basically finding density. So what you have done is essentially calculated density for each row in the data frame. Finally, you have this series. We can now put this series in a new column in the data frame, which is what we have done here. df cars bracket density. This thing density doesn't exist. If it did exist, it will overwrite. Be careful. That's the whole point. When you're changing your data frame, be careful. If there was a column called density, by mistake, you will be overwriting it. Right? So since this column doesn't exist, I'm more than happy to create it. And these are my density values with the exact same indices as the data frame. Okay. So now I can just assign this as a new column to my data frame. Again, note guys, the index that I'm talking about here, this is the LOC index. We are working with DF data frame. That is why you may be thinking 0, 1, 2, 3, 4 looks like integer. The index I'm working with is LOC. So later, please try this for tempdf. Go to tempdf and try some of these operations. The LOC indices need to match. Then only the operations will be done element wise. Okay. If the LOC indices do not match and what you're doing, the operations will go wrong. Okay. So what's happening here is the LOC indices are being matched. All right. Yeah. So hope that summarizes this. Yeah. Okay. So as I said, quiz 2 and quiz 4. Quiz 2, you know, little bit of logic involved, little bit of GPT involved. Which command, Rajat? I have many commands here. In fact, I have used, you know, somebody's command here, Akash, I think. Yeah. Here, let me just give Akash command. This is the one Akash used. The one I am using, it's step by step. Here it is. I'll show you. Where is it? This one. Yeah. So this is the set of commands. Yeah, step by step here. You need to copy paste and, you know, put it in separate lines. Okay. So this is the one that I have used step by step. You can investigate each object. That's good if that's what your interest is. Great. So yeah, quiz 2, think about it a little. You know, it requires some math and logic. Quiz number 4 is a little bit more straightforward, I think. So you can try it yourself. We are going to move on with statistical operations. So we've seen some arithmetic operations, inter-series operations. Now we'll go to statistical operations. Okay. So again, I'm going with my DF data frame, and we have seen some of these methods before. Dot sum, dot mean. We have seen these methods. So suppose, for example, I do DF age. Everyone tell me? I have highlighted part of the code in my cell. Can you tell me what is this object? So DF age is series. Now we know that series has statistical operations like sum, mean, and all that. We saw that, right? So directly apply it. So now if I do DF age dot sum, and by the way, sum is not an attribute. Sum is a function, which is why we are putting the brackets. Okay. So if I do df age sum, what is it doing? It's giving me the summation of the age column, 318. Typically, can we say it as array? No, Pratim. I would like to call it a series. So the difference between array and series, I made it clear, right? Series is going to have these labels. Arrays only have integer index. So when you do data analysis, it's important to talk in terms of labels. Okay. So yeah, let's develop that, right? Which is why I have included the temp df in this workbook as well, right? Typically you will see that typically you will see, you know, some learning resources, they will use 0, 1, 2, 3 as the, you know, the row indices. And I told you that what numpy index 0, 1, 2, 3 is already there. If you don't specify the pandas index, this thing comes forward. Okay. So some learning resources will use that. And my sense on the matter is that we should know both and we should understand what's happening. So if I call this an array, I'm basically saying it does not have a pandas index, but it does have a pandas index. This 0, 1, 2, 3, you're saying this is the pandas label, not the numpy label. The numpy, not even label, numpy integers. Numpy integer index is there behind. Okay. but Pandas has made a copy of that. So now, the temp df data frame, if you see, the indices are A1, A2, A3, A4. So in fact, we can possibly even try with temp df. So temp df, now here, if I do like temp df, say age, right now, everyone, can you tell me what is the output of this highlighted thing? I've written temp df bracket age. And by the way, all series are array, but all array are not series. That makes sense, right? Yeah. So now if I do temp df age, are you able to see 0, 1, 2, 3, or are you able to see A1, A2, A3? Which one? You are able to see A1, A2, A3, right? Yeah. So we should refer to this as Pandas series. Each column of a data frame is series. Each row of a data frame is also series. Okay. They are arrays in the backend, but Pandas provides you additional functionality. Okay. Anyway, so now if I want the mean of the age, I just take the series age, I can apply the mean method. So the mean age of the, from room number A1 to A10 in my hotel is 31.8 years. So that's mean function. You can even find the mean expenditure. We've seen many of these methods before, right? So you can do df expenditure dot mean, and all of these are just series operations, right? So df expenditure dot mean, that's 17.69. That's the $69, by the way. So that's the mean expenditure of the people in the rooms in my hotel. Also, we have methods like max. So df age dot max gives me the max age in the age column. Df expenditure min gives me the minimum expenditure in my expenditure column. We also saw this idx min, idx max, right? So it gives me the index of the minimum age. So here it says 0. Let's go back to our data frame df. So minimum age is obviously 18, Shilpa, and the index is 0. Now, I think this method will make it very clear what index we are talking about, right? So here if I do temp df age dot idx min, please notice the output. What is the output? A1, not 0. So this is my point. So when we are talking about Pandas indices, we are talking about the non-numpy indices. We're talking about the labels. Okay, so you can see temp age dot idx min, it's not giving you 0, it is giving you A1. The only reason df is giving you 0 because we did not specify a Pandas label for that row index. Okay, so to summarize that question, we should call these series only, and these labels are Pandas labels. Okay, the numpy labels exist behind, they are there if you require. Okay, so if you saw, we spent way more time on LOC and not much time on ILOC. So yeah, so idx min gives you the index of the minimum value in the column. Idx max will give you the maximum, and I hope we all remember median. Median is like the middle value between the one, you sort the series and then get the middle value, right? So of course we all remember the median formula. So you can find the median expenditure, that is 17.93. Mean expenditure was what? 17.69, right? So almost median is little higher, right? So all of these things, all of these methods exist. There is one very interesting method called uh, df.describe. Okay, this is very interesting, and it's typically used a lot. So if you remember in the last session, I said that df info, df columns, df index, and probably df shape or something else, these are important methods to study the the structure of the data frame. df.describe is the best method to quickly study the numeric information in the data set. So if I do df.describe, here I'll get age is numeric, expenditure is numeric, and it says count, mean, standard deviation, min, blah blah blah. So some of these other things you will study in more detail later in exploratory data analysis. I don't like this way of printing, so what I usually do is df describe and then transpose. Okay? So then it looks a little cleaner. So basically what it's telling you, median age is 28.5. See, 50% means median. So median age is 28.5. Median expenditure is 17.93, which you can confirm here somewhere. Yeah, median expenditure is 17.93. It gives you the mean also, 17.69. Here it's 17.69. mean expenditure. So df describe actually gives you all, and count means how many values are there. Okay, so this is very useful for numerical data. Df.describe. Notice that it doesn't care about the other data, string, object. It will not even take it in the output. Obviously, what is the mean of name? There is no mean of name, right? For string data or categorical data like cuisine, it's Indian, American, whatever, there is a very interesting method called unique. So it will tell me the unique levels or unique values in that category. So df cuisine dot unique, if I do, it will show Indian, American, Chinese. Similar functions are available in Excel also. Microsoft Excel, whatever, you have similar functionality. So pandas essentially, takes that ahead further, and which is why we study this in detail. So dot unique gives you the unique values, right, in the categorical data. Now, if you also want how many Indian, how many American, how many whatever, right, then you can use this method called value counts. So if I do this, I'll get like this: Indian 5, American 3, Chinese 2. Okay. One thing to note is that keep checking the type of output. Okay, so df unique is giving me array, value counts is giving me series. Okay, but this series is a different series. This series is not having the indices same as the data frame. Okay, so here the index is Indian, American, Chinese, completely different series. Pratim, by using them, and don't worry, you will get there. Okay, as I said, now if you just scroll back up, and I'll scroll for a while because this is important. Please read this. You will work with all these methods throughout your data science learning journey and beyond. Does that answer your question, Pratim? I'm not expecting you to remember in one session at all. We will be using this again and again and again and again. Visualization, analysis, and a little bit of maybe stats, machine learning. Again and again we'll be using. Okay. So don't worry, nobody is expecting to memorize in one day. Not possible. Not possible. There are way too many methods. I agree. All right. So value counts is done. I think mean and median we spoke about. We know another statistical thing called mode, right? So mode usually it is applied to numerics. I think in school we were doing for numerical data, but typically speaking, you can apply to both. You can apply to categorical data like cuisine, Indian, American, whatever, or you can apply to numerical data also. No problem. This is max number of observations, correct. So if I do df cuisine mode, what is the answer? Indian. And I guess if you look at this, Indian is 5. Okay, so you can do this for numerics also. All right. Now there is a what you say, a generic method called aggregate. Okay. Now for example, if I just do df age dot mean. Okay. So what is the answer? 31.8. Correct. So what I've applied mean directly to age. There is a function called aggregate, which essentially what it's doing is all this mean, median, all these different aggregation functions. Those will be parameters of these functions. So here if I say df age dot aggregate, now instead of using directly the function mean, I can specify the parameter as mean to this aggregate function. So if I do this, I'll get the same answer, 31.8. Now it seems useless right now. It's more important later. Okay. Reason is, for example, here, if I want to aggregate more than one column in terms of mean, right? Now first let's do, let's just do this subset. df age expenditure. We all understand this. This is a subset of my data frame, right? It's also a data frame. My original df had more columns. Now I just got the age and the expenditure column. Okay. Now suppose I want the mean age and the mean expenditure, and let me do dot mean here. Correct? This is what we would do. But if I do that, right, you will get 31.8 on age and 17.69 on expenditure. Now here, if you do aggregate on these two, you will get the exact same results. The only difference is that you can change what you are applying to each column. So I cannot apply median and mean separately here. So here together, if I want to apply mean, no problem. this aggregate function, what it helps me is, here for example, it's a dictionary. See the parameter, okay? It's a dictionary. So take the complete data frame dot aggregate, then put a dictionary inside, okay? And here take the column age and specify that, look, I want to aggregate by median. Take the column expenditure and say, look, I want to aggregate by mean. So now if I execute this, you will get slightly different from here. Can you see? This value is slightly different. So these two are exactly the same because you've been using mean for both columns. Here, directly do df dot aggregate, and here of course you can take subset also. Nobody is stopping. Okay, the subset of the data frame will still contain the age and the expenditure column, so no problem, right? So if I do this also, I will get the same output. Typically, you can also just call the original data frame, which also has the column age and expenditure. So again, no problem, right? You can do this, or you can take the subset and do also. And since the subset is already being done inside the dictionary, why should I subset outside? That's the point. So this allows me to get the aggregate separately for different columns. So here I have median age and here I have mean expenditure. So these kinds of things will sort of be more useful when you do data analysis and things like that, because some features mean is a better representative, some features median is a better representative, some feature mode is a better representative, and so on, right? So you can choose which aggregation function you want to use. For example, price of car, maybe I want the mean, mileage, I want the median, right? To see my data set, what is the aggregate value. So that's where this aggregate function plays a role. Okay, to summarize, I think some of these are obvious, like sum, mean, median, all of that. IDX mean, IDX max, there was a little bit confusion between LOC, LOC. I hope that is clear. It is LOC. It is giving me the pandas index, right? IDX and all these things. And describe is something that we saw for numerics. Value counts is very useful for categorical variables, right? Like cuisine and things like that, which have fixed levels, Indian, whatever. Other type of categorical variable is what? Gender, male, female, right? Those kinds of things. So that's useful there. And aggregate is useful to choose, to pick and choose what kind of aggregation that you want for various features. All right. Are we ready for quiz? The first one. What is the price difference between the most and the least expensive car in the DF cars data frame? Let's try this quiz, quiz 5. How will I do this? Most and least expensive car. Of course, this is going to take a combination of commands. Step 1, find the row with the most expensive car. Step 2, find the row with the least expensive car. Okay, perfect. Let me check this. DF cars max, DF car price max minus the min. Yeah. So Ashish, I think this is the right answer. Really nice. DF cars price dot max. This will give me the maximum value in price. DF cars price dot min. This will give me the minimum value in DF cars price. Correct. Now I just need to subtract. So answer is $40,000. Okay. So just to make it clear, who is this DF cars price max? Let us see. I don't know who. So now, okay. Now how do I find out who this is? Which car this is? IDX max. Okay. So if I want to find out which cars this is, I have to first do IDX max. So here it's giving me the index, isn't it? Remember, is this the ILOC index or LOC index? Which one is it? Can everyone put in the chat? Is this the ILOC index that I'm getting here? What index I'm getting here? ILOC or LOC? ILOC. Oh, ILOC. I just showed you, no? Remember tempdf? So if I do tempdf age dot IDX max. Sorry. What is this A8? A8 is ILOC or LOC? What is A8? LOC. So IDX max gives LOC. IDX min also gives LOC. Now why are you saying ILOC? LOC only. So dfcars.idx max is giving you the LOC index. So I can just do dot LOC, isn't it? I can just do dfcars dot LOC dfcars price IDX max. Yeah, LOC, we all agree? It's LOC, okay? These methods are giving you the pandas labels, LOC, yeah. So dfcars price IDX max 74, which is the LOC index. Now I can do dot LOC with that index and subset the data frame. So you will get the row. And why does the row look like this? Can someone tell me this is one row? Can someone tell me why does the row look like this? What is this? Dot LOC. Yeah, it's a series. Exactly. It's a series. Even the row is also series. Okay. So pandas row is series, pandas column is series, right? And any combination of these is data frame. That's all. Okay. So here I just need the car name. So it's some Buick Regal Sport Coupe. I don't know what this is, but whatever. This is some car which has the highest price. You can see here 45,400. Okay. So you can see 45400, 45400. Okay. Is it clear? Confirmed? LOC. Okay. That's confirmed. Yeah. Great. Summarize DF using this main reading. You can do this later. I think you can do this later. Not a problem. I mean, it's similar to this, whatever I did here. So you can try this later. This is interesting. Can we try quiz number 7? Let's try quiz number 7. Are there more cars with 2 doors or 4 doors in the DF cars data frame? And note that the door number feature is actually a string. So one would expect the number of doors to be integer or something. But if you see the DF cars data frame, there is this thing called door number, but it has English values 2424. So what method can we use here? What do I need actually? I need to know, are there more cars with 2 door or 4 door? So I need the number of cars with 2 door and 4 doors. How to do that? I'll just scroll my screen to the hint. Here is the hint. Yeah, value count is a fast method to do that. Now of course you can do other method, right? You can do df bracket door number equal to what 2, and then df bracket equal to 4, subset, find the length. All that you can do, isn't it? We can do all that. But df cars, and then what is this thing called door number? If I just do door number and then I apply the value counts, just quickly gives me, right? 4 doors 115 cars, 2 doors 90 cars. Now the same thing if you want to do, of course you can do it using logical subsetting also, right? So you can definitely do something like this, right? df cars door number equal to 4, subset it, get the length 115. Okay. Similarly, same thing, df cars door number equal to 2, subset the data frame using the logical, get the length 90. So you can do this, but these methods are faster. Yeah, Pratham was trying that. Okay. The intention is to use the methods you recently saw. Okay. So here value counts directly gives you. Now imagine here door number we have 4 and 2. What if you had a categorical variable with so many levels, right? Suppose country, India, USA, France, China, and totally you have 10,000 rows or something. So it's probably more efficient to do dot value counts, right? Okay, so you can do dot value counts to answer this quiz. Yeah, please try. And I've shown you the logic method also. This is okay for this data set because it has only 2 levels. Okay, yeah, value counts is good here. All right. Yeah, this one is interesting. Okay, this one is very interesting. Let's do this. Use the mean function directly on the df movies data frame. Do this for both axes. First directly use it. Can everyone give me the command? So first let me print df movies. What is the command for applying the mean function directly on the data frame? Use your intuition at this point. Even if you have not seen it somewhere, what do you think the command looks like? Apply mean on the full data frame. Anyone? Yeah, df movies mean, correct. So I'm going to apply df movies dot mean. Now please execute this. So Akash, Ankita, you guys have given the correct code. Execute it. What is it doing? By default, it is executing for what? Columns or rows? What collapsed? Answer to me, what got collapsed? Rows or columns? Applies on the row or column. That's what you're saying. What got collapsed? Rows got collapsed. Correct. So axis equal to 0, isn't it? That's what happened here. Axis equal to 0. So if I just put that axis equal to 0, I will get the exact same result. Default is axis equal to 0. So if you do axis equal to 0 in this data frame, what are you getting? You are getting the mean rating for each movie. So Thor 6.5, Justice League 6.1, Spider-Man 6.65. Out of all these, now you can do something like .idx max to find out who is the most popular movie. Spider-Man. Okay. Make sense? That made sense, right? Now if I do axis equal to 1, suppose I do df movies dot mean axis equal to, what is going to collapse now? Columns will collapse, right? Look at the data frame. By default, row will collapse and you will get column wise mean. If I do axis equal to 1, columns will collapse. Columns will collapse, you will get row wise mean, right? Yeah. So here if I do axis equal to 1, look at the output. Columns have collapsed and now you're getting the row mean. What is this telling me? This is telling me which of these people actually like movies in general, basically, right? So I can, you understand, if I do axis equal to 0, it is telling me how good are the movies running. Okay, like which movie is not doing well? Obviously something like Annabelle 5.4, it's not doing that well, right? Now if I do axis equal to 1, what is it giving me? It is saying which user likes movies in general. That is the answer that I'm getting from axis equal to 1. So here I can do something like .idx max, and for example Ravi really likes movies. So if you go see Ravi, his average rating for all the movies is 8.6, which means he's liking all the movies. Correct. Okay. So these are some, of course, remember axis wise operations and all these can also be applied. Fine. Okay. So we have a few, like about 20 minutes left. We'll go through some additional operations. Okay. So first thing is sorting, and as I said, sorting is very common operation. I think we saw something for series. We can see it for data frame also. So the way this works in data frame is there is a function called sort values. Okay, so this is an inbuilt function for the data frame, and there is a parameter called by. And I hope by now we are understanding, Python is a very English friendly language, as in human language friendly. So if you see the parameters and everything and the function names, all of them are representative of what it is doing. So you can actually read this in English. You can just directly use the words and read in English. Sort the values in my data frame by expenditure. Isn't it? That's all. Okay. So initially Python seems a bit weird, but slowly you'll see that it's quite, easy to use. So sort the values in my data frame by expenditure. Sure. What is this going to do? It's going to sort the whole rows using the expenditure sorting. So if I just do this, as you can see, this is ascending now. 11.09, 12.23, 12.56, 14.43. This is now ascending. So expenditure is going in ascending. Do you think that the other columns will not be disturbed? Of course they'll be disturbed. If you don't disturb the other columns, then you are losing your index, you are losing the information. So it is sorting all the observations according to one variable, right? So that's what's happening here. Expenditure 11.9, 12.3. The rest of the information has to match with the same LOC. Okay. Now, just to make things really clear with this LOC business, can everyone tell me what is the LOC value for the first row that I'm highlighting here in this output data frame? Put it in the chat. What is the LOC index for this? Is what? No. Guys, see the index. Index is 6759. See, 6. 6. Do we agree it is 6? Is it a reading issue? Can't you see? Is it zoom? 6, right? Yeah. So 6 is the LOC. Okay, wonderful. So what I'm going to do at this stage, I'm going to just save this in some variable called temp.df. Okay, I'll save this data frame. I will print it. Okay, you all agree that this is the exact data frame you just saw, correct? And the first row is 6, correct? Now if I do temp.df.loc6, tell me the name of the person which I will get if I do .loc6. Monica, correct? Wonderful. So if I do LOC6, I will get Monica. Okay, very good. Now can you please tell me what is the ILOC for Monica in this data frame? ILOC, integer location. Room is a column, guys. Rajat, room is a column, not even an index right now. Room is a column. The index you are seeing is here. Okay, I'm getting 0 as the answer for ILOC. Yes. So if I do .ILOC0, I will get Monica. I hope this makes the difference between LOC and ILOC very clear. ILOC is immutable integer index. LOC is our labeling. So if you see in temp.df here, temp.df, see the LOC, na? 6759, it makes no sense. 6579, that is not in order. So how you can think these are integer indexing? No, these are labels. 679, these are pandas labels, LOC. Okay, the ILOC are integers. So the ILOC for this data frame is different for the ILOC for the original. Why? Because the observations got mingled up. But the LOC remains the same, even if you mess up the observations. Wonderful. Same thing for columns, by the way, guys. Exact same thing for column also. Okay. Yeah. Because what is the difference between row and column? Nothing. This also series, this also series. Okay. Okay. Anyway, so continuing with sort values, if you don't want ascending, what you can do is you can put ascending equal to false, right? You can do that. And that will give you descending order, right? There's also a very interesting functionality where you can give list of two variables or features for the sort values method. What it will do is it will basically try to sort with cuisine first, and if two cuisine matches, then it will sort with expenditure. So it's a 2-level sorting. Okay, so if I say df.sort values by equal to cuisine expenditure, as you can see, American. So A because string sorting will be alphabetical, correct? So American, Chinese, Indian. Okay, so it has string sorted within the same American. It will sort the expenditure next. As you can see, it is sorting by expenditure 12.23, 18.54, 19.54. Okay, so you can do 2-level sorting also. All right. Similarly, there is a function called sort index. So if I do df.sort index, what's going to happen? Where is my df? Okay, nothing happened because my df is originally also 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are my labels. So if I sort index, nothing will happen because they are already sorted. Now if I do df sort index ascending equal to false, what will happen? See, my LOC indices have changed. My ILOC will not change. This output data frame, if I do ILOC 0, I will get Gaurav. Okay. If I do LOC0, I will get Shilpa. All right, great. So we'll quickly go through some things here, some functions and some group by, and this might take maybe 5 minutes more, so I will need about 15 minutes from now. Is that okay with everyone? This is a little bit important part, maybe we should do that. Yeah, okay. So functions, now already I have showed you df.round, right? This is something I showed. Now I also told you that round will not affect things like room, name, cuisine. It will not affect, because round is a mathematical function. Pandas knows which data type to apply, which to not apply. Okay, so if you do df.round, it will only round the numeric values. Now there is this very interesting thing called apply. Okay, there is this function called apply, which is a built-in method for DataFrame. What it does is it generalizes functions and then you can apply to the DataFrame. So basically what I've done here is I've taken numpy round. So I did not import numpy. Please import, guys, otherwise this won't work. So let me import numpy as np. Okay, and then np.round, which is a numpy function. Okay, so I can apply this numpy function on my data frame. So if I do df.apply round, now what is the problem? What's happening here? It is saying it cannot support argument on type string. Basically, inbuilt method, if you use df.round, this is a pandas inbuilt method. Inbuilt means that is why you are able to apply directly from data frame. But if you apply from other, like not an inbuilt function, np.round is not inbuilt into df in that sense, right? The name of the function is from numpy.round. This round has already been built into pandas with the name round. So if I try to apply np.round, you're going to get error here. Okay, so now how do you generalize? That is the question. So if you take expenditure and round, and why this is giving error? Because np.round does not know that it should not apply round on name, room, cuisine. NumPy doesn't know that. Only pandas knows that. So here, if I use dot round, this is pandas obviously. So this is a pandas series and this is the built-in round method. It is rounding my expenditure. Okay. Now if I take that same expenditure series and I apply numpy round, it works. So when you're using an external function, not pandas, not inbuilt to the object, if you're using external function, it won't know. That function doesn't know whether you should apply to only one column, two column. That function doesn't. That you have to specify. Okay. So what's happening here is that this apply method allows for generalization. Okay. So if you are unhappy with the kind of functions that pandas have inbuilt, which is very unlikely because it has so many functions, but in case you need some general function, then you can define it and you can apply it. So for example, here I have df. Okay, and suppose I, for whatever reason, I want to get the first three letters of everybody's name, right? Suppose that's my function, obtain the first three letters of everybody's name in the data frame. So what I can do is I can define a function called first three letters, and this is very basic string operation. Okay, so and by the way, these functions will apply to the full row, so that's why we should be careful that we are applying single column at a time. I will show you what the issues are. So this, when you do the dot apply method, it considers whatever row available as your complete input. Okay, so that's why I'm calling it row here, and you can even call it x. If you don't like this, you can call it x, but yeah, you can just call it row because that's what it's applying on. So this is a simple string operation, right? So assuming that this row is a string, assuming that this row variable is a string, then string with indexing :3 will give me the first three letters 0, 1, 2, because string is nothing but it's a conjoined list of characters. So list accessing works on string. So let me define this function, and it is returning the new. Okay, so row equal to row up to 3. So I will get the first three letters. Let me apply this. Okay, now if I take df name dot apply, right, as you can see, I'm getting SHI, JS, DOM, AHM. All of these are the first three letters of the names in my data frame. So what I've done is I've defined a function, assumed what should be my input. What is the input? It is the row of the object that you're applying. What is the object I'm applying here? DF name, which is a series. What is each row of the series? Only the full name. So if I do DF name before this, these are my rows. These are my rows. Okay. So that's why I'm assuming that my row is a string, right? So then I'm applying this function on that and it is working. So you can do that for cuisine also, same function, you know. So Ind, American, Ind, Chinese, whatever, right? Now, what if you want to apply the function to two columns, name and cuisine both? So let's try it, right? DF, and this is the subset, isn't it? So if I just take this and print it, this is the subset. It has name and cuisine, Shilpa, Indian, Jasprit, whatever. Now, if I apply this function and see the result, it will not make any sense. Why is this not making any sense? It's not making any sense because now this apply function doesn't know what row means, because here the row is essentially a subset of the series, isn't it? And a subset of a series is also series. So when you're doing the indexing method in this function here, you are actually doing some indexing with the series, but your intention was to split the string. Okay, so that's the one thing you need to keep in mind with apply, that it works better with single column. Apply works better with single column. Okay. If you really want to apply same function on 2-3 columns, you can use for loop or whatever, but there is one method called apply map. Okay, so this thing applies the function correctly to the 2 columns and it gives you the result of the application of 2 columns as a data frame. Okay, and finally, and by the way guys, don't worry, as I think one of you pointed out, so many methods cannot remember. Don't worry, just take your time and practice. Okay, anyway these methods will come again and again later. So I don't know if you all have studied any lambdas, right? We don't know. Can you just put in the chat if you know what a lambda function is? Oh, you know lambda. Great. Okay, then that's easy. So then this should be very obvious, right? So what is my DF cuisine? DF cuisine is essentially Indian American. So these are my rows, right? I'm applying a lambda function. So what is the X in my lambda? It is this Indian American, right? This is my lambda. X is all this. I am saying return the value 1 if X is Indian, else return 0. Okay, return 1 if X is Indian, else return 0. So if I apply this, wherever it is Indian, it will return 1. Wherever it is not Indian, it will return 0. Okay, it is applying on the each row of your item basically. Okay, I won't go into the quizzes right now because of time constraints. I would like to discuss group operations. This is quite important. Quizzes you can try on your own, right? More or less all these methods, I think we are getting better. Just try. And in fact, I think next week, as I said, there's a doubt resolution session. So definitely you can take up your doubts there. Okay. I want to use the rest of the time to discuss groups. And then there's a bit of work, additional work that you guys will do later. So this is one of the most interesting methods in Pandas and one of the most powerful methods in Pandas. Sonal, basically, I mean, see, the thing is that many of these things, it is expected that you guys need to do it. Okay, which is why I think Abhishek also pointed out there's a price pulse assignment. So slowly in the program, the expectation is that you start getting more familiar with these things and you start doing these things independently, right? As I said, ample support is there. If there are doubts and everything, we have doubt resolution session. Still, if the the audience wants some kind of additional support, more than happy to discuss that and figure out, right? But the expectation is that learners also need to start putting effort from their side, right? So we will sort of enable you, right? We will enable you. We will tell you all this. Now, for example, if I ask the whole audience, are we comfortable with pandas to some extent? All of you will say, yes, I am comfortable. I know iloc, I know column, I know pandas loc, I know all of this. Yes, I am somewhat comfortable. Can you try things on your own? Yes, I'm ready to try things on your own, right? So that's the expectation that we have from the learners also. Okay. Having said that, if you guys are getting stuck somewhere and you need support, definitely there will be support. Okay, but the expectation is that you try it independently. Is that is fair, Sonal? Fair, na? Okay. Right. So yeah, the last one thing that we want to discuss is group by, and after that, I'll just discuss what the additional work is. So there's this function called group by in it's an inbuilt function to DataFrame. What it does is it creates a temporary object. So if I just do df group by and by equal to cuisine, you can see the output here. It says pandas core group by generic data frame group by object. Basically this data frame group by object. This is a temporary object. It has no output. Like as you can see, where is my data? Where is my expenditure? Where is all this? It's not there. So group by, what it's creating is it's creating groups. So when I say group by cuisine, what's happening is it's picking Indian and then creating a group of Indian, and then American, it's making group of American, and then Chinese, and then group of Chinese, right? And on the group by object, I can apply the mean function or any other type of function. And here I've written a parameter. Let me do without the parameter. So now if I group by cuisine and do mean, you will see that it says df group by mean is deprecated. In a future version, numeric only will go to default, whatever. These are just some updates. So here it is telling me, specify numeric only. Okay, then I'll just specify numeric only. These updates are very common. Okay, so if I do df group by and then apply mean, and then this parameter which Python itself told me that go ahead and apply it, as you can see here, it gives me the mean of the numeric variables for the groups. I hope that made sense. So from this, what I can see is that American mean age is 40. American mean expenditure is $16. So this is the American cuisine. So older people are preferring American cuisine and spending more money on it. Chinese 38.5, 12.76. So somewhat mid-age people are spending very less on Chinese. So we need to find out why the Chinese is not selling, for example, right? Or is it really cheap? And Indian young people are spending a lot of money on Indian cuisine. Okay, so this group by combined with statistical operations is one of the most powerful analytics methods in Pandas. Okay, so again, don't think that we are mastering group by and all this in this session. This will come up again and again in visualization, EDA, and all those. Okay, so I have applied mean here directly to the data frame, and it gave me some warning and all. So why don't I do something else? So for example, here if I say df group by cuisine, right, and this group by object, I will pull out the expenditure column. It says series group by now. Notice how Pandas is very clear in its output, right? Now it is saying that this is a series group by object. Why? Because I only took expenditure, which is now a series object. Now if I apply mean on the expenditure, I will get that. American people mean is 16.77 in the expenditure, Chinese is 12, right? So I'll get the mean expenditure for each of the groups. Now, even further, what you can do df group by cuisine, then expenditure. Okay, that's a series which is grouped series. Then I can apply external function such as np.mean. This also gives me the result. So group by plus apply, this combination can be used to achieve many things. So here what am I doing? For example, see here I'm doing df.group by cuisine and expenditure age. These two are numerics, right? These two are numerics. So the output of this is a data frame group by. Yeah, data frame group by. On that I am applying mean. Okay, very nice, right? And of course you can do the same using np mean, but here there will be some updates. Data frame mean blah blah blah. What's it saying? To retain old behavior, use frame.mean access equal to 0. If you want to go through all this trouble of using np mean, we can do that, right? But ideally I have a direct function called mean, so why would I do this? Okay, so there is always going to be some updates, but it is giving some answer, right? So why to use this method when I have this method? Finally, what I want to show is the combination of group by and aggregate. Okay, So here, for example, I'm doing df.group by cuisine. So this is a grouped data frame group object, which is grouped by cuisine. Then I can aggregate on this group by. So I'm using this aggregate function on group by, and I can aggregate. We all remember, right? Aggregate is where we had a dictionary, and you can specify column value, and you can say what you want to aggregate. So if I do this, right, it gives me the exact same result. American 16.7, Chinese 12.7, so on. But now if I want, and this one is obvious, right? Expenditure mean, age mean. So if I use aggregate on the grouped object with expenditure mean, age mean, I'll get mean of expenditure and mean of age for American, Chinese, India. But suppose you want different aggregation method, right? So expenditure, suppose I want median, and age I want mean. So maybe I want to change this to mean, suppose, right? So I have expenditure median, age mean. So what I'm doing is grouping by cuisine and then putting aggregate function on it. Expenditure I want median aggregate, age I want mean aggregate, print it. And now it will give me the mean ages of these groups, cuisine groups, and the median expenditure of these groups. Okay. So, I typically in data analysis, you might want to find the total expenditure. So if just think you are the hotel manager, and what do you want? You want to know the mean age group, mean age. What is the mean age of the people who are preferring American food? What is the mean age of the people who are preferring Chinese food? What is the mean age of the people who are preferring Indian food? That is one thing you want to know. Another thing you want to know is what is the sum of the money spent on American cuisine by the people in the hotel. What is the sum of the expenditure spent on Chinese, right? So on aggregate, you can now use expenditure sum, age, mean, group by cuisine. You do that, and this is what you get, right? You have the mean age of the people preferring American, Chinese, Indian here, and you have the total amount of money spent on these cuisines here. Okay. So just to summarize, right? We have spent a lot of time familiarizing ourselves with the behavior of pandas. We've done the fundamentals in great detail. Okay, I have introduced you to some methods which you should start exploring, and try to work it on your own, right? There are ample practice questions. So once you finish NumPy and all of that, you can do the pandas practice also. And please note that, again, I need to repeat myself, we are not mastering these techniques in one session. These are techniques that we will need and we will use in further topics also. Okay, so there are a few quizzes here. You can try them on your own. And so again, these are all using group by, using apply. Try to use the different methods. Okay, try to use whatever methods you feel comfortable, but try to use the different methods. Okay. And here in other data frame operations, here I've kept some operations which maybe you will not use too much, which is why I kept it at the end. So you have things like deleting elements from data frames, changing elements in data frames. When I say changing elements, I mean changing one by one, right? So some of these methods, I have given some examples here. You can try it on your own. These will be done in more detail when you do data pre-processing and things like that. Okay, so it doesn't make too much sense to study all of this in pandas, because anyway we will be using these methods when you do data pre-processing, exploratory data analysis, things like that. Okay, so adding new rows, columns, all of that. And finally, inter data frame operations, I just kept a very short bit here, and as you can see, I'm just showing two methods, join and merge. No need to worry too much about this right now, because it will become more important, as I said, in data pre-processing. The reason I've left it here is so that you guys can start exploring these things, and when we go to visualization, pre-processing and all that, we know, okay, we have seen these methods before, let us see it in more detail. All right, so just want to summarize this, that the whole section, right? We started with NumPy. We understood NumPy arrays, we understood indexing, the data types that are stored. Then we understood that pandas is built on NumPy, and pandas series is a very, improved version of array. It can store data of multiple type, and it has labeled indices. And now you can take these pandas series and put them together to create what we call a data frame. And data frames are typically the most common type of data structure used to read analyze, manipulate tabular data. And we have seen multiple tabular data in these sessions: car data, movies data, buffet data, so all those kinds of things. So of course we'll be seeing many different data now as we go into the next topics, visualization, all of that. We'll be seeing way different type of data. And the way you need to think about all of this is that fundamentals we have spent more time, and applications we have done introductory, and these applications we will be using again and again in the future topics. And second point, yes, effort from the learner side is definitely expected. You guys need to try out all these things. So we will sort of enable you to some extent that, okay, are you comfortable enough with these tools? Are you comfortable with these concepts, right? And then the learners are expected, okay, go and do some additional things on your own. Okay, so that provides for the best sort of learning experience, is what I feel.
So today we are going to expand the concepts which we have learned from the first two sessions, and we'll deep into the world of central limit theorem. We'll go much deeper into the world of central limit theorem, which I believe is one of the most powerful inventions in the world of statistics. Apart from that, we'll also understand how we can use actually z-score and p-value. So in the previous video, we have seen how to calculate z-score, and here we'll see how to use z-score and p-value. And in the process, we'll also understand the difference between population and sample. So population and sample, and this will pave the way for us to dig deeper into hypothesis testing. So let's get started with understanding the use of z-score and how is it related to p-value, and what is p-value and how is it so important. So let's get started. So in statistics, we do two major varieties. One is descriptive statistics and one is predictive statistics. That means we want to predict something, right? Suppose if I give you a problem, right, or I give you a scenario and I ask you what will happen next, which means essentially means that you have to predict something. Like for example, if I tell you, say, who will be the next president of, say, USA. As you know, the presidential elections are coming. So if I ask you who will be the next president of USA, and I hire you as a statistician and I ask you to make some predictions. Suppose we have candidate A. Suppose the two main candidates are candidate A and candidate B. Now, if I ask you, tell me what are the chances of candidate B being the next president of USA. Now what you can do is you can collect a lot of data. So you will collect a lot of data in the form of maybe opinions from different people, different agencies. You will collect all the data, do some analysis, and if you have to find out who will be the president of USA and what are the chances of candidate B being the president of USA, you will analyze this data, for example, and then you will come up with something called a p-value. So if I ask you, tell me what are the chances of candidate B being the president of USA. So you collect a lot of data, then you calculate something called p-value, and this p-value, in this case, if we just want to find out the chances of candidate B being the president of US, so we basically say, we ask different people and say, will you vote for candidate B? Will you vote for candidate B, right? And you get yes, no's and everything. Now, after doing all calculations, how to do all the calculations and everything, that let's just park it. We'll look at it. Suppose after doing all the calculations, we find something called a p-value. Now this p-value basically denotes the chances of candidate B being the president of US, because the entire analysis I am running on this particular hypothesis, that what are the chances of candidate B being the president. So we analyze the data, we calculate something called a p-value, and suppose if we get a say a p-value of 0.8 for example, now that means that the chances of candidate B being the president of USA is 80%. So we take the data, we take a hypothesis to start with, we collect the data, we do the analysis, we calculate the p-value for a particular incident or a particular question. So first is we build some kind of question or hypothesis. We'll look at in a bit more detail with hypothesis testing. So if you are already aware about hypothesis testing, some of these things may look as if a bit disjointed from that hypothesis testing. These hypotheses right now, don't worry about hypothesis testing. Just think of it like a belief at this point. So you should think like this, that we have a hypothesis, we collect data, we do some analysis, and then we get p-value. Now after doing all these things, so this is my hypothesis. This is my hypothesis with which I am working, and after doing all this, I get a p-value of 0.8, which means that the chances of candidate B being the next president of USA is 0.8. However, having said that, when we talk about null hypothesis and alternate hypothesis, we'll see a slight difference from what we had just said. I mean, we do it a bit differently, but the basic principle is this. I have hypothesis, I take the data, I do some analysis, I calculate the p-value. And here the hypothesis, as I said, is candidate B being the president of USA. Okay, so I am asked these questions. What are the chances of candidate B being the next president of USA? And my answer is, going by all the statistical analysis, the chances looks like 80%. Okay, so p-value gives me the chances of a particular incident being true. Here the incident is that candidate B will become the next president of USA. I guess it's clear so far. Now what we'll look at is how p-value is related to the z-score. Z-score is something which we have seen in the last lecture. If you have not watched the last lecture, please go and look at the last lecture and then come back to this lecture. So now let's look at how z-score and p-value are connected. So let's take a normal distribution. So this is a normal distribution, not a very well drawn normal distribution, but I think to some extent at least we are able to understand it's a normal distribution. Fair enough. So suppose this is my mean, and say my mean is 50 and my standard deviation is say 5. So simple one only. This one is 55, this is 60, this is 65, this is 45, this is 40, this is 35. So as you can see, I since the standard deviation is 5, I have gone up to 3 standard deviation to the right and 3 standard deviation to the left. Now suppose I ask you a question, that what are the chances, suppose this is a distribution, right? So behind the distribution, what is there? How do we get this distribution? So we have data. From this data we can draw this distribution, and this side is my actual data elements, and this side is my frequency. So from the actual data, which has got rows and columns, and the actual data can probably range from say 0 to 70, 20 to 70 for example. Suppose this is my data. From this data I have drawn this graph which looks like a normal distribution. Now I ask you that suppose from these data I pick up a random data point. Okay, these data, suppose here I have data, which is nothing but rows and columns, right? Any data is nothing but rows and columns. In this case, this is only it is only one column which we are looking at. Actually, I should not call it as a rows and columns. In this case, this is just one column, multiple rows, right? So now, if I ask you that what are the chances if I randomly pick up one row from this particular data, which looks like this, what are the chances that will be less than 65? Will it be very high? Will it be low, or what? So if I ask you that, hey, you know what, I have this data and I know that this follows a normal distribution, what are my chances that I will pick up a data point which is less than 65? When I say I pick up a data point, I can randomly choose a data point. I do not know what the data point is. I just want to understand what are the chances of it being less than 65. Similarly, say what are the chances of a random data point being, say, greater than 45? What are the chances of a data point being less than 30, say 32, for example? So let's look at these examples. Okay. So in this case, what are the chances of me picking up a random point which falls anywhere in this distribution? Think intuitively. Right now, nothing. Don't worry about anything. Intuitively, do you think the chances should be more or less? On a count of 3, 2, 1, the answer is the chances should be very high, because the entire distribution is on this side, right? So if the chances are high, it is very good. How high? How much? Just quantify. Let's quantify with a number. So what we'll do is we'll calculate first the z-score of 65. What is the z-score of 65? That is x minus mu by sigma. So in this case, x is 65 minus mu, that is 50, divided by 5, which is 15 by 5 is 3. And we also know that it's 3. So this is 3. The z-score is 3, which is okay. But how do I convert that into a probability, into a p-value? So for that, we use something called a z-table. This z-table you can just Google and you will find, you can download this z-table. It's not something which I have built. It's already there in the internet. You can download it and you can use it. So if I come to z-table, the way to read z-table is, so here we got a z-score of 3. So from z-table, what we get is p-value. So in z-table, what we can do is we can pass the z-score and get the p-value. So let's look at the z-table. So here the z-score is 3.0, and here is 0, 0. So that is fine. So 3.00 will be this point. That is 99.87, which is okay, 0.9987 or 99.87%, whatever. So let's come here. So what it is saying is, if this point is my point in question, which means if this point is 3, which in this case it's 3, here this is like 50 and this one is 65, the z-score is 3, which means the chances of anything picking up randomly from the left hand side of this point in question is 99.87 or a p-value of 0.9987. Now if I ask you what are the chances of picking a random data point from this distribution which is greater than 65, that will be 1 minus, which is this side. If the total is 1, then this will be 1 minus 0.9987, which is 0.0013, not 13%, 13, and then you can multiply it with 100 and you will get 0.13%, right? So let's rub this off. So let's look at few more examples. So the first answer what we got is now greater than 45. Greater than 45 means I want this side, right? The right hand side. And intuitively we can see that right hand side should be more, greater than 45. The chances of you picking a random sample which is greater than 45 is actually more. Now how much more? That's the question. So 45, we can clearly see that z-score of 45 will be -1. How? Because here it will be this will be, this is 45. If this is 45, then this will be -1. So here the z-score is -1. Now what that means? Now let's go to the same z table. When the z-score is negative value, then we come here. So here we got a z-score of -1, which is this point. However, here, which means the shaded region percentage is what I have got. So the number which I have got is 0.1587, right? How did I get there? Again, let's come back. A z-score of 1, and here this is 0, which means the value which you are getting is actually this side of the curve, and I want this side, which means if this side is 0.1587, then this side should be 1384, which means 84.13%. So the chances of we picking up a random point which is greater than this point in question is 84.13. So for a negative z-score, we get this side, which is this value, but we want this side greater than 1, greater than 45, z-score greater than 1, this region. In this case, this z-score, this is 45, so I want this region, and the chances is 84.13%. So let's come back. This is next one, less than 32. Less than 32 should be this side and should be very, very low. Just intuitively, if this is 32, for me picking a random point here should be very low. Intuitively we know that. So just let's look at 32. So if we pick up 32 here, we get -18 by 5, which should be -3.6, I guess. -3.6. So let's see if you can find -3. Oh, -3.6 is not even here. So let's pick up, say 34. Say let's do 34. So this 34 should be -3.2, which means the z-score is -3.2. So less than 34 means this region is what I'm looking at, and intuitively we can see that it should be very low. Let's see how much. So 3.2 is this much, is this value. So 3.200. Had it been like say 3.21, then we would have picked up this value. Say let's say, can we pick up -2.77? So -2.7 is here, and 77 should be this point. 2.7 and 77, and that should be this point. 2.7 minus and 7. Similarly, say -2.14, -2.14. That's how you should read the z table. Okay. So now -3.4, 3.2 is what we have got, which is 0.007, which means this side is 0.007, which means the chances is 0.07%. Very low. So 0.007 is the p-value which we have got. Now we have to multiply it by 100 and we get this. So greater than 70, let's do the last one, or maybe say yeah, let's do greater than 70 is actually a high number is what I feel. So let's do say greater than say 57. Greater than 57 means this point, this should be 57, and greater than 57 should be this region, which technically through naked eyes looks very small, but how much small? Let's figure out. So this is now 57. So this is like 7 by 5. 7 by 5 is 1.4. So now let's come to the z table. Let's take 1.4. So 1.4 is this much, which means region to the left is, so what I want is this point, right? This is my z-score of 1.4. I want this region. However, the value which we'll get here is actually this region. So this is this region, right? So this one is 1 minus 9192, which ideally should be 08.08, which means if I just multiply it, it should be around 8%, a bit more than 8%. Okay, I hope this part is clear now, because this is the foundation, this is the base which will help us to solve a lot of problems. So we have completed now understanding z-score and p-value. Now we'll understand what is a population and what is a sample before we go to central limit theorem. So population and sample. So in very simple terms, population is my superset and the sample is my subset. So population is a superset and sample is a subset. Now let's get some examples. Suppose I ask you what is the population of India, which means it like contains the entire population of the country, which should be around approximate say 130 billion, 130 crores, right? 130 crores population of India. Now suppose if you have to do an exit poll, right? If you want to do an exit poll, do you think it's feasible that we go and ask all these 130 crore people that whom did you vote for? It's impossible, right? So what we do is we create subsets. We create subsets where we divide people by age, gender, occupation, mother tongue, and so on. Lot of criteria, not only these four. And then we pick up few people from here. We pick up few people from here. We pick up few people from here. We pick up few people from here and ask them. So suppose here we have got say multiple age groups. So suppose for age group 60 and 70, we have say 5 crore people. So we'll not ask all those 5 crore people. We'll go and ask say 2000 people who will represent this 5 crore people. That's something which we assume. Now, while sampling, a lot of errors can come if the sampling is not done correctly, right? So by age, gender, occupation, mother tongue, and so many other criteria, that's the statisticians uses, and then chooses a subset from the superset and does the statistical analysis on the subset, because it's impossible to go and ask 130 crore people whom did they vote for, right? So maybe out of these 130 crore people, they will ask say 1 lakh people, and with good statistical agencies, they can, if they do the sampling correctly, if they choose the right set of subsets, then 1 lakh 50,000 or even less. I mean, the more expertise you have, the less subset is what you require. And then based on that, based on these 1 lakh, we make decision for these 130 crores. That's the power of good statisticians. In some agencies, it's even less. I have seen agencies who have done exit polls for just by selecting 50,000 people out of a population of 130 crore people, and their prediction was like very, very close, right? So it's not possible that we go and talk to everyone. So we choose a sample, we choose a subset from the entire data set, and then we do the analysis on that, and we assume that this subset represents the superset. Like for example, suppose all these are my data points. All of them are like one individual, and dot dot dot. Now we can choose subsets like this, and it's important that the same subset can be repeated, which means the person who represents a certain age can also represent a certain gender. There is no hard and fast rule that for each experiments or while choosing each subsets, we only choose the unique set of people. Not necessary, right? So we can choose like this. Here we are just choosing 4, one set with 4 people. So for each sampling criteria, we are saying say pick 4 people. Though in exit polls they do not pick 4 people, so don't mix it up with that. This is just for representation and for this purpose, just for understanding purpose. Suppose for example we pick up 4 people each, and we choose from here, say here also I say choose 4 people, and then we do the analysis independently on these guys. We do some calculations, and then whatever result we find, there is something which we can tie back to the main population, and we can say that the results which we have got from these samples or this subset is a representation of the entire population. So now I think we have got a fair idea on population and sample. Now keeping this in mind, we are going to understand central limit theorem. So let's look at central limit theorem through an example. Say I have a data set where I have around 20 records. So here as you can see, I have got 20 records, around 20 records. Now what I'm going to do is, I'm going to randomly choose, by the way here the word which is very important is random. I cannot pick and choose at my wish. I cannot say, okay, I want this, I want this, I want this, I want this. No, that will not work. I have to randomly just close my eyes and pick up 4 people. Similarly, in the previous example when I was showing is, when they sample, when they create subsets, suppose they have created a subset where all the occupation is say IT professional, right? Now they know that these 20 crore people are IT professionals, and I know that okay, I want to choose say 50 people from there. I cannot make bias in my mind and say okay, I want these people, this. I suppose think like this, as if I am closing my eyes and I say okay, number 1000, okay, number 15, okay, number 30. So it's like randomly I'm choosing, because if I do not choose with random or randomness, then the entire purpose gets defeated. The tests cannot be done on bias. It has to be random. So suppose I have randomly picked up, this is something which I have already done before, so that I don't lose time in doing that. So just assume that okay, I have not done any cheating and I have randomly picked up. So suppose I have picked up these four numbers randomly from here, 5, 7, say 32 and say 11, last one. And once I have picked up these 4 people, what I have done is I have calculated the mean and the standard deviation. So this is like a mini distribution. This is the main distribution. Main distribution I call it as a population, and say this is a mini distribution. So I pick up these 4 numbers. After picking up these 4 numbers, I take the mean and I take the standard deviation of just these 4 numbers. Again, I pick up again 4 numbers from here, which are these ones. Again 4 number picked up from here. I calculate the mean. I calculate the standard deviation of these 4 numbers. Again 4 numbers here, the mean and the standard deviation. 4 numbers, the mean and the standard deviation. Okay. Now what we shall do is, let's come here. Standard deviation is something which we do not need. We'll work with the means. So for all these subsets which we have taken, for all these 4 number subsets, we have got the means for all of them. We have also calculated the standard deviation, but we do not need it. So we have taken all these means. So as you can see, these means. So we have formed another data distribution where we have taken all the means. So these ones and these ones, all these means, and we have formed another data distribution, because the collection of data is a distribution. So here we have created a distribution of means. So we have taken all the means and created another separate distribution. Now what central limit theorem says is that when we have formed this distribution of means, if I plot them, then if I plot them of plot of frequency, what I get is a normal distribution. Of course, I have to do some some amount of sampling, which means if I just take 2 samples, if I just take this one and this one, I'll of course not get a normal distribution. So we have to do substantial amount of sampling, and it depends on how much data you have. The more data you have, the more number of sampling you need to do. So central limit theorem has got three distinct and very important formulas. First formula is when you form a distribution of means, if you plot them, if you plot their frequency, you will find that they are following a normal distribution, which is, that means these particular distribution, if we plot, we find that it follows a normal distribution. That's the first hypothesis. Second hypothesis is, since this is also a distribution, I can take its mean also. I can take the mean of all these numbers, and suppose I have done that, and I can see that this is 44. So this mean is 44 is what we have found. Ignore all this right now. I'll talk about it in a moment. So all these numbers, all these particular numbers, like for the distribution of means, if I calculate the mean, which means mean of the distribution of means, if I calculate, I get it as 44.86. Now if I call this as a mu bar, this mu bar is 44.86. Central limit theorem says that these mu bar and the mu, which is the mean of the population, right? After some time, these two will come very close and can be equal also, or even if it does not come, even if it does not equate, it will like come very close. So these mu bar will come very close to mu. So here this is 44.86. Let's look at what is the original mean. It's 45, and we can see that after 20 iterations of randomly picking up numbers, what we find is that the mean of this distribution of means, they have come very close to the original population. That's the second hypothesis. So we have learned two things from central limit theorem. One is distribution of means when plotted will form a normal distribution. This mu bar is mean of distribution of means, and this is population mean. Point number 3, third hypothesis is sigma x bar is equal to sigma by square root of n. Sigma x bar is standard deviation of distribution of means. This is standard deviation of the population, and this n is number of samples. So in this case, if I have to run the central limit theorem, I have to ensure that this n is constant, which means every time I have to pick only 4 or only 5. For one iteration, if I just pick 4, second one I pick 5, then I will not be able to apply central limit theorem. So here also, if we see, if we calculate the standard deviation, this is 14.34. What is the standard deviation of the population? 25.5. If I divide it by square root of 4, which is 2, it should come to 12.77, and we can see that here we are 14.34, and it's coming very, very close. So you must be wondering what is these numbers. So when I had taken the first two data point, first two means, this was my mean of the distribution of means. Then first 3, this, then first 4, this. And as you can see, with time and time, the more iterations we do, this is coming closer to the original distribution. Here also we can see that this is decreasing and coming close towards this 12.77. Ideally this should be 12.77, right? Because if you look at the formula, sigma is 25 and we have taken 4 samples, so 25 by square root of 4 is 2, that comes to 12.77. so this side is 12.77, and after a few iterations this is like 14.3, and it's coming closer. If we take few more iterations, it will eventually go and come very close to 12.77. So in essence, these are the 3 formulas of central limit theorem. Now, couple of things which we have to understand, which are the assumptions. So number one, the population can be of any sample, or sorry, the population can be of any kind of distribution. Does not mean that the population has to also be a normal distribution, not necessary. So the first assumption is population can be any distribution, can be skewed, can be normal, can be anything, can be any kind of distribution. Number two, when we choose the sample, we have to choose them randomly. So random selection, that's important. Number three, samples should be independent, which means if I pick one sample, the selection of other samples should not have any impact. So let me independent, which means, for example, if I choose 5, this 15 has no impact. So I have chosen 5, then I've chosen 15. A 15 has no impact whether the previous number we chose was 5 or not. It's independent, it got independently chosen. So we have closed our eyes and said, okay, 5, 15, 12, 14. So 15 has no relationship whether we chose 5 before it or 32 after it. So that's another assumption. So the next assumption is the sample size which we should choose, that should not be more than 10% of the population. Should not be greater than 10% of the population. And number 5, if the population is like asymmetric in nature, like right skewed or left skewed, this is not left skewed by the way. If they are asymmetric, which means say this one or this one, then we need to choose more samples. And if they are symmetric, then we need to choose less samples. So for symmetric population, or in simple terms, things, if the distribution is like more or less normal, then we can limit the sample size to less than 30. We should choose sample size which is less than 30. For asymmetric population, we should choose more samples. Okay, I hope these assumptions are clear. Now what we'll do is we'll run through a quick simulator where this concept will be even more clear. So this is the link of the simulator. You can also go and practice yourself. And when I learned central limit theorem for the first time, I got very confused initially. And then I used this simulator and everything started to make sense very quickly. So let's look at the parent population. Say parent population. We say that it doesn't matter what is the parent population. It can be normally distributed, non-normally distributed, can be anything. Now what I'm going to do is, so I just distorted the population as much as possible. So for this population, I know the mean and I know the standard deviation. Now what I'm going to do is I am going to pick 5 samples here randomly. So these here, as you can see, 5 samples I am picking randomly. This n is equal to 5. And then once I have picked up these 5 samples, I calculated their mean, and that is my distribution of means. And as you can see here, since the points are more or less here, the mean has to be here, right? This is only one point here. So this mean is like very close to these data points. So again, I choose randomly 5 points. I get a mean, which means like I'm here. I've got these 2 points. And I have started forming my distribution of means. I've got 2 points. Here I've got 2 points. Again, one more. I've got 3 points now for my distribution of means. And as you can see, I've done like 3 repetitions. Now what I'll do is I'll like fast forward. I'll do it 10,000 times. Now it's like 10,003 times because I did 3 times before and now it's 10,000 times. Now for this distribution of means, if I want to feed it to a normal distribution, I can see that it's more or less fitting like a normal distribution. So my hypothesis 1 is proved and we can see that it works here. What was the second hypothesis? That this distribution of mean and this mean will be coming very close to each other. And if I look at it, it's like 15.47 here and here it's 15.5, very, very close. If I do it say 10,000 more times, now I have done 50,000 times and as you can see, this mean is like 15.49 and this mean is like 15.47, very, very close. If I take one place of decimal, then it has already merged. My third point was standard deviation. So standard deviation for the formula was sigma x bar is equal to sigma by square root of n. So in this case, sigma is my 9.96, which is this, divided by square root of n. N is, I'm taking 5 samples, so square root of 5. So now let's just calculate and see how much it should come and how much it has come. So square root of 5, I guess, should be 2.23. 9.96 divided by 2.23. That is 4.46. And you can see here it's 4.45. Very, very close. So let's do one more. And it doesn't matter how many number you choose. It will still stay the same. Another distribution. Animated. I'm now taking 10 samples and then I get my distribution of means. So here my standard deviation is 9.14. So first let's do 10 square root. 10 square root is 3.16. So 9.14 divided by 3.16 is 2.89. So here my sigma x bar should be 2.89 after few iterations. We'll see. So animated again, 10 samples and I get their mean. So fast forward 10,000. I tried to fit the normal distribution and I can see it's almost fitted, or it's fitted quite well actually. Here the mean is 14.38, the mean is 14.41, almost merged. The standard deviation is 2.93 and we should have got 2.89, again very close. Let's do few more rounds and see. Now after 60,002 rounds, we can see now the standard deviation is 2.9, here this is 2.89. Here we see that the mean is 14.39. Here you can see the mean is 14.38. And now it fits the normal distribution even better. So you can play around this tool and get a very good idea about central limit theorem. And in the next lecture, what we'll do is we'll look at hypothesis testing. We'll understand what is a null hypothesis, what is an alternate hypothesis. Then we'll look at false positive, false negative, type 1 error, type 2 error, and then we'll look at some problems. So in order to do hypothesis testing, which we will learn later in the next series, the basic building block is central limit theorem. So we apply central limit theorem and get answers of hypothesis testing. So here, this analysis, under a lot of scenarios, we use central limit theorem. Not that for this case we will use central limit theorem, but just assume that if we go this path, central limit theorem, and there are other techniques as well, not only central limit theorem, but in this context, so we establish a hypothesis, we collect the data, we do some analysis by using central limit theorem and or some other techniques, and then we calculate the p-value, and then we make some inferences. And central limit theorem, as I said, is one of the most powerful techniques in statistics.
Congratulations on completing the business dashboard using Excel course. Ready to elevate your career? Join our postgraduate certificate in data science and AI and gain exclusive benefits like a complimentary Python programming bootcamp, 7+ case studies, dedicated student support, and access to our job opportunities portal. Don't miss out on this chance to transform your career. Invest in yourself today and join our program. Click on the link in the description to enroll now and take the next step in your career journey.
Welcome friends to another exciting episode of statistics. So today what we are going to do is going to be very exciting, because today we are going to solve few statistics challenges. These challenges are based on the learnings which we have acquired over the last few videos. So I assume that you have watched our last few videos, as this video is an extension of those videos. So today we will solve statistics challenges using central limit theorem, using the concepts of normal distribution, and using the concepts of hypothesis testing. So this is central limit theorem, normal distribution, hypothesis testing, and of course central tendency like mean, standard deviation. So let's get started with our challenge. So let's look at the first problem. So the problem says that batsman A scores 50 runs on an average with a standard deviation of 5. So in this case, the scores of batsman A has been compiled and it has been found that he scores 50 runs on an average and his standard deviation is 5. Now what we want to find out is what is the probability that he will score less than 40 in a given match. So he scores 50 runs on an average with a standard deviation of 5. So if for any given match we have to predict his score, or in this case we want to predict that he will score less than 40, we want to find out what is that particular probability, what are the chances. So let's get down to work. So let's first write down what are the information we have. That's very important for problem solving. So in this case we know, so this is problem 1, we know that the mean is 50, we know that the standard deviation is 5. So now since in this problem nothing is mentioned that what kind of distribution does the runs of the batsman is plotted against, let's assume that these 50 runs with a standard deviation of 5 follows a normal distribution. Since nothing is mentioned, let's assume that it is following a normal distribution. So let's draw a normal distribution. So this is 50. So if standard deviation is 5, then one standard deviation to the left is 45. So 2 standard deviation. So what we want to essentially find is the probability of the batsman scoring less than 40. So friends, one thing which I want to tell you is statistics is a subject which mixes numbers with intuitions. So you should not look at just dry numbers. You should always try to visualize the problem and apply a lot of intuitions. This is, by the way, not a very good normal distribution. Let me just, yeah. So essentially, if we look at the problem is the probability of the batsman scoring less than 40. So what are we trying to find? We are essentially trying to find the region shaded in red. No, I mean, in this case, before you even apply the formulas and crunch numbers, just look at the graph. If you look at the graph, what you will see is that intuitively the chances of the batsman making less than 40 is very less, right? So it's more likely the batsman, if this is a normal distribution, the more likely is that the batsman is going to score mostly in this region, the region shaded in green here, right? Now let's find out what is the probability. So the first step, what we'll do is we'll try to find the z-score of 40. Now z-score, as you know, just a quick recap, z of x is x minus mu divided by sigma, which means 40 minus 50 divided by 5. Though intuitively we can see that it has to be minus 2, but still let's calculate. This is minus 10 by 5 equals minus 2. So now we know the z-score of 40 is minus 2. Now what we are going to do is we are going to look into the z table and find out the p-value. So this is step 2. Step 3 is use the z-score to calculate p-value. So let's come to the z table. Here we can see that the z-score is 2, which means the p-value is 0.0228. So the p-value is, now what is p-value? In this case, if you remember our previous videos, p-value is the probability of picking up a random sample from this shaded region, this region, right? Which means the chances of scoring, if this is 40, the chances of scoring less than 40 in a given match is 0.0228. If I convert that in terms of probability, I just multiply this number with 100 and we will get 2.22 or 2.23%, right? So this p-value of 0.228, we can say that the chances of the batsman scoring less than 40 is 0.228 multiplied by 100. Just to calculate it in terms of percentage, it's 2.23% up to 2 places of decimal. I hope this problem is clear. Now let's just slightly tweak the problem. Suppose this is not 40, or rather this is 40. This is fine, this is 40, and suppose we want to find this place, say 39. In that case, this part is not what we are looking at. We are looking at only this part. So z score of 39 is 39 minus 50 divided by 5, which will be minus 11 by 5, which will be minus 2.1. So here if we come, 2.1 is 1.79%. Now if I ask you what is the probability of it scoring, say, greater than 40, since this part is less than 40, if I ask you what is the probability of the batsman scoring greater than 40, it's not very difficult. So 100% minus 2.23, and that is 97.77%. All right, I hope this is clear. So now let's move to the next problem. So let's look at problem number 2. So let's read the problem. You're a businessman doing grocery business. The supply of your stock is sporadic at times. Maybe you are not getting the supply from the vendors or the suppliers which supplies goods to your grocery store. You do not receive it very regularly. It's sporadic. At times you receive it on time. At times you do not receive things on time. So you even suffer losses at times if the goods are not sold within a certain period. Probably they cross expiry periods, which is very regular, especially with dairy products, right? Milk and all those stuff. If they are not sold within a certain period, you cannot sell it again because that's harmful. So you suffer losses at times and you make profits also. So profits have a mean of 2000 and a standard deviation of 1000, which very clearly shows that the business is very topsy-turvy. Though you make profits, but at times you do make losses because the standard deviation, if you look at it, it's 1000, quite high. So your team makes 100 trades per week. So you do 100 transactions. Actually, transactions will probably be the right word. So your team who is running your shop, they makes 100 transactions per week. Now, what is the probability of your team, or rather your shop in this case, because your team cannot make profit, making a loss or making a profit of more than 20,000 in a given week? So let's dissect the problem. Let's first look at what we have. So we have a population data, which is the mean of 2000 and the standard deviation of 1000. So let's write down mean of 2000 and standard deviation of 1000, right, for each transaction. So your team makes 100 transactions per week. Okay. Now the probability, what we need to find out, the probability that you make a loss and the probability that you make a profit greater than 20,000. So here, when we look at a profit of 20,000 in a given week, considering that we are making 100 trades, you can actually say that per trade, if you want to look at, it should be, because this is for the entire week across all the trades, we want to find out per trade, because mean and standard deviation, all of them signifies per trade. So we want to find out the probability of making a profit greater than 200 Actually, let's make the problem a bit complicated. Let's make this, say, let's make this, actually this is fine. Let's go with this is okay. Or let me just change these numbers a bit, maybe. So let me make this, say, profit of greater than 50,000, for example. Or rather, let's make it 5 lakhs, so that it becomes more interesting. 1, 2, 3, 4, 5. Yeah. So 5 lakhs, or rather, let me make it 3 lakhs actually. So here now we are looking at a profit of greater than 3,000 and a loss. Loss is less than 0. So let's draw the normal distribution. So this is my mean, 2000. This is my standard deviation, which is 1k per 1000. Just to avoid a bit of space, 2 standard deviation will be 0. And in this side, I'll just call it 3k just to save space. So now what do we need to find? Let's look at the problem. Probability of you making a loss, which means this particular region, and probability of you making a profit greater than 3000, which means the region. Actually, let me draw profit with a good color. It's profit, so let's use green. So we want to find out the probability of a random sample being picked up from the green zone and the red zone. Eventually that's what we are trying to find, right? If I pick a random sample, what is the probability that it will be from this green zone and it will be from this red zone? Now again, as I said, first visualize the problem intuitively. That makes life very easy. So it's intuitively very clear that the chances of you making a loss is less, and the chances of you making a profit greater than 3000 is not very high, but at least it's more than you making a loss. So let's quickly crunch the numbers. So for the first problem, let's find out z is equal to 0, and we want to find this region. So loss means less than 0. That's what we wanted to find, a loss and a profit of 30,000, right? So loss is 0 minus the mean is 2000 divided by standard deviation 100, which is minus 2, and a z score of 3000 is 3000 minus 2000 divided by, it should be 1000. So now from the z score, let's figure out the p-values. So just to make the problem interesting, I will make a bit small changes here. I will say, suppose this is 3200, say this is 3176. So this is, the reason is I just want to show you how to look at certain decimal places in z score. So this will be 1.76. all right. So here we are looking at not this region, not greater than 3000 fully. Probably I'm looking at this region. This is 3176 and this is the shaded region. So now let's come here. Minus 2, same 0.228. So the p-value is 228, which means less than 0 is 2.23%. Now this one is 1.76. So let's come down to the positive side. So this is 1.7 and 1.76 is this one. So 1.7 and 0.6. This is 1.7. This is 0.6. So this is the p-value when the z-score is 1.76, which means this particular region is 0.9608, which we found from here. However, we need this region because we are looking at greater than 3176. So this region is 0.9608. So this region is 0.0392. So this part is 3.92% because I am looking greater than z, and less than z is 96.08%. So let's go down. So here the p-value is, because I am looking at this side, and the value which we get from the z table is always on the left hand side. So the p-value in this case is 1 minus 0.9608, as we are looking for greater than this 3176. Here is my 3176, right? The z-score the p-value which we get is always on the left side, but I did on the right side. I did more than greater than 3176. So in this case, this is 0.0392. So this one is 3.92%. Now from this, if you want to further derive that, if I ask you what are the chances that the shop will make profit, which means I am looking at this, and from here this should be 100 minus, let me use the same ink for calculation. So it's 100 minus 3.92%, which is 0896. No, my bad. We should take this one, not 3.92. 100 minus 2.23. My apologies. So it should be 97.77. We are looking at this number. I hope this is clear now. So now we have solved two problems using z-score and p-value. Now let's take one step further and let's look at hypothesis testing. The steps are not going to be much different, only some small tweaks here and there. So let's start by looking at a problem of hypothesis testing. A quick recap before we start hypothesis testing. H0, H1. H0 is my null hypothesis, which is my anti-belief, which is something which I don't believe. H1 is my alternate hypothesis, which is my belief, which is something more likely to happen, right? Also, what we know is that we cannot test this directly because there are no statistical tests available to test the alternate hypothesis. So this can't be tested directly. So we test this, we test null hypothesis. When we test null hypothesis, we get a p-value. And what we want this p-value to be low. How much low? Ideally less than 5%. If that is the case, then we reject H0 and accept H1. So this is the high level flow of hypothesis testing, which I have already explained in deep detail. This is just to warm you up and a quick recall. So now let's start looking at the problem. So in 2015, kids were watching 26.5 hours of TV with a standard deviation of 8 hours. So in 2015, you did a survey and you found that kids were watching 26.5 hours of TV with a standard deviation of 8 hours. Since nothing is mentioned about what kind of distribution does it follow, we will assume that we are talking about normal distribution. So today, you randomly surveyed 70 kids and you found that they are watching 24.5 hours of TV. So in 2020, you randomly surveyed 70 kids. By the way, here the word randomly surveyed is very, very important. While doing any survey, it's very important that you do it randomly. Okay? Else you can just ask your kid, their friends. That doesn't work. You have to randomly pick up 70 kids and then you have to do the survey. And you found that they are watching 24.5 hours of. So now the question comes is, are the kids watching less TV these days? So in 2015, they were watching 26.5 hours of TV. Probably we are talking per week average. So today in 2020, which means after 5 years, you randomly surveyed 70 kids and found that they are watching 24.5 hours, which is less than 26.5. So the question is, are the kids watching less TV these days? So here, let's break down the problem one by one. So what is the information we have? This is problem number 3. So in 2015, kids were watching 26.5 hours of TV and standard deviation is 8 hours. So we assume that this is my population. Since we have not mentioned anything, always assume that this is my population. Now in 2020, you randomly surveyed 70 kids and you found that these 70 kids are watching around 24.5 hours. Now mind it, you have only surveyed 70 kids. Is that enough for you to say that the kids are watching less than 26.5 hours of TV? So in this case, what we want to find out is the probability of the kids watching 26.5 hours of TV, right? Given this arrow, this vertical bar represents given, means what is when I am looking at another condition, which in this case is n is equal to 70 and x is equal to 24.5. So what do we want to find out? The probability of x being less than 26.5 when I found that n is equal to 70 and x is equal to 24.5. N is the number of kids I surveyed and x is how much TV they want. So this part I know that this is true because I have done it. I want to find out if this is true, what are the chances that this is true? We want to find. Okay. So we want to find the chances of this part being true given this particular condition. So let's go step by step. Let's first write down what is our belief. From the initial indications, our belief is that kids are watching less TV, less than 26.5, because this was my benchmark. So if you look at the problem, we are saying, are the kids watching less TV compared to this 26.5, because this was my initial population. Here I have not mentioned what are the number of kids we have surveyed, so always assume that this is the population, and any hypothesis is always done on the population, not on the sample. Like what we do is, if you think of a real life scenario, we say that the average literacy rate of, say, India is 75%, for example, right? Now suppose you randomly surveyed 100 people and you found that out of those 100 people, 90 are literate, which means the literacy rate is 90% for those 100 people, right? So you get an intuition that probably the literacy rate has increased. But is it enough? Because you have only spoken to 100 people, you have not spoken to a lot of people. But is it enough for you to make an assumption that probably it is greater than 77%, right? So in this case, you have to think like this. You have to think intuitively first. Is it enough for you, by surveying 70 kids, that the population data, which in this case is 26.5 hours, has dropped? So what is my belief? What is more likely to happen? That is my alternate hypothesis. What is less likely to happen? Now you may ask me why this is not greater. Why it is not greater or equal to 26.5? The reason behind very simple is, it's very evident that the numbers have dropped. It's very unlikely that this will be greater than 26.5. At best, it can stay at its current position, because we can clearly see that there is a drop here. But is the drop substantial enough, or have we spoken to enough people to make a conclusion about the population of 2020, right? That's what we want to find out. So always think that in this case, the two questions which are important is the drop enough? Is the drop enough for me to conclude that it has actually dropped? Drop enough means this and 24.5, right? Is it an enough drop? The second is, have we surveyed enough people? right? So now let's try to solve the problem. So according to central limit theorem, what do we know? We know that mu equals to mu bar. This mu bar is the sample side. This mu is from the population side, right? So this mu bar belongs to the sample side. This I'll call the sample side. This is the population side. So according to central limit theorem, mu is equal to mu bar, which means in this case the mu bar is 26.5. The standard deviation of the sampling distribution, sigma x bar, is equal to sigma by square root of n. So sigma, as you can see, it's 8. 8 by n is 70, and that comes out to be 8.36. So 8 divided by 8.36 is 0.95. So the standard deviation is 0.95. So now let's draw this graph and let's try to mimic this condition here. Remember, this is not, I do not know whether this is true or not. I'm just trying to mimic it and see the chances of this statement being true. So this is my, according to this scenario, this is 26.5. So that's my mu bar, and my sigma x bar is 0.95. So 26.5 minus 0.95 is 25.55. One standard deviation to the left. So this is 25.55 minus 0.95 is 24.6, which means this is 2 standard deviation away, and our candidate is 24.5, which is here. This part is 24.5. So now we have mimicked this in the graph. Now we have to understand one concept of rejection region. What is a rejection region? In very simple terms, rejection region is the region which does not contain 24.5 and 26.5, which means in this case, this is my rejection region, the region shaded in blue, because this part does not contain 24.5 and 26.5. This region, the region on the green, that has both 26.5 and 24.5, right? This region. However, the region shaded on the blue does not have 24.5 and 26.5. So this portion is called the rejection region. Now logically, if you think, the closer this 24.5 and 26.5 come, right, that will increase the rejection region, isn't it? Like for example, suppose this is 10, there's a number 10, there's a number 8, there's a number 6. So if we want to compare 8 and 10, the rejection region is higher. This is the rejection region of 8 and 10, right? Why the rejection region is higher? Because 8 and 10 are closer. The closer these 2 points are, the rejection region becomes higher, right? So in this case, it's very evident that these 2 points are not very close, which was also which is something which we also saw. This is 26.5 and this is 24.5, right? So they are not very close. What we want to find out is the coexistence of these 2 things. We do not know whether it's less than 26.5 or not. That's what we want to find out. When this part is true, this part is what we want to find. What is the probability, right? So the probability of this thing happening, this particular phenomenon, this particular probability happening should ideally be low, right? Should ideally be low if the rejection region is less. The rejection region, if it grows higher, then we get a higher chance of these 2 statements being true at the same time, isn't it? So logically think, in this case, the chances of 8 and 10, since they are closer to each other, the rejection region is higher, which means, for example, if I say that what are the chances, what are the probability of mu being 10 if I pick up a random sample which is 8, right? And the chances of mu being 10, suppose if I pick a random sample which is 6. In this case, this chance is higher because these 2 points are closer. And a closer point means a higher rejection region. The lower rejection region indicates that probably the chances will be very, very low. How much low? Let's figure out. So z-score of 24.5, you already know, it will be 24.5 minus 26.5 divided by the standard deviation 0.95, and that is minus 2 divided by 0.95 is minus 2.10. So the z-score is minus 2.10. So from the z-score, I will get the p-value. I want to get the p-value of this region, and we know how to get that. So minus 2.1 is, sorry, this is the positive side. Minus 2.1 is 0.179, which means the probability of us, or the rejection region probability is 0.179, which is 1.79%. So the p-value here is 0.179, and this p-value what we get is for the rejection region, right? So now the formula is very simple from here. The p-value which we calculate, if it is less than rejection region, we can say that reject H0, right? In this case, what is my H0? My H0 is this. That is very, very, actually, you know what? This is not correct. This should be the ideal formulation. That it is 26.5. The total, actually, even this is not correct. Yes. So the probability that the mean is 26.5, given that this particular thing is true, right? So the probability that this is 26.5, which means the probability of these two statements coexisting, co-occurring, and this can only be high if the rejection region is high. When the rejection region can be high? If these 2 points are closer. If these 2 points are closer, what will happen? The z-score will be lower, right? So think about this sequence one by one. So p-value is less than rejection region, I reject H0. Why? When the p-value can be less than rejection region, when the p-value can be less, actually you should know, it should not say like this, and this rejection region ideally should be 0.05. Now it's complete. So the p-value what we calculate, if it's less than the rejection region where which should be 0.05, then we reject H0. When the p-value can be less, if the z-score is high, isn't it? When the z-score is high, if chances of two statements coexisting is high. Now what do I mean by that? Like in this case, we are looking at the coexistence of the statement that the mean of the distribution is 10, but we picked up a random sample which is 8. There are a lot of numbers. I pick up a random number, there is 8, and I know that in this case my mean is, say, so I'm looking at a distribution where mean is 10 and standard deviation is, say, 2. So I pick up a random sample which is 8, where I got 8, right? What are the chances that the probability, or what are the chances that the mean is 10? So the mean is 10 and I pick a random sample that is 8. Now this one I know is true because I have done it. What are the chances if I pick a random sample which is 8 and the probability is 10? sorry, the mean is 10. The probability of the mean being 10 when I have picked up a random sample which is 8. That's what we want to find out. So if the z-score is high, then this happens. If the z-score is low, then the probability of coexistence, two statements coexisting, will be low, right? So if the z-score is low, means 2 points are far apart, the p-value will also be low because the rejection region will be low. So lower, if the 2 points are far apart, the z-score will be high, the p-value will be low, the rejection region will be low, and we can reject the null hypothesis, right? So in this case, what p-value did we get? 0.179. So this is what we have got, that is less than 0.05. So we can reject the null hypothesis. My null hypothesis is this, which is rejected, means the chances of this statement being true is only 1.79%, right? This one multiplied by 100 is 1.79. So this one has a chance of, this has only 1.79% chances, means this one has a chance of 98.21%, and we accept the alternate hypothesis. Or rather, we can say that we are 98.21% sure that people are watching less TV, but this number is so high, we can actually pass it as a judgment. We can say that people are watching less TV. I hope the entire understanding of the problem is clear, because now we are going to just extend the same thing for other problems. So let me share a small tip with you. So far we have been trying to calculate the p-values, and going forward also we'll keep on doing that because that's a good practice. But let me also show you a shortcut. Do we really need to take the z-score every time? Sorry, do we really need to take the p-value from the z-score every time? I'll tell you a shortcut so that I don't even need to look at the p-value. And just by the z-score, I should be able to make a conclusion. So what is that concept? So what I want the p-value to be less than 0.05. How do I get the p-value from the z-score? Right? So now what we'll do is we'll learn a shortcut. So in order for the p-value to be less than 0.05, let's find out what is that z-score. So let's come to the z table. So let's look at a negative z table where the value, where can I find a good p-value where it is just less than 0.05? This part. This is my cutoff. So which is like minus 1.65. As you can see, this is just below 5%. So let's write down minus 1.65, and from the other side I will try to find out where exactly it is just crossing 95%. And if we see this again, 1.65, which means the rule is if the z-score lies between minus 1.65 to 1.65, you cannot reject a null hypothesis. If it's beyond this range, then you can. So if the z-score is greater than 1.65, or if the z-score is less than minus 1.65, if these two scenarios occur, then you can reject null hypothesis, considering that my confidence interval is 0.05. If this is 0.05, which is generally the norm. The general norm is that the confidence interval is 0.05. If that is the case, if this is the scenario, then a z-score greater than 1.65 or a z-score less than 1.65, I can reject the null hypothesis. Okay. Now suppose, for example, if your z-score is, suppose I say, okay, now I want to to have a confidence interval of say 0.09, which means suppose it's a very mission critical, so I want a confidence interval of 0.01, which means I want to be 99% sure of my alternate hypothesis. So in this case, the p-value has to be less than 0.01. So in that case, what we'll do is, let's look at the positive side, which means I have to find where it is just greater than 99, which is this point, 2.33. 2.33. So in this case, a z-score greater than 2.33 or a z-score less than minus 2.33. If either of these scenario occurs, then you can reject H0. Else, we fail to reject H0. So this is a small tip which you can use. We will continue to use p-value because that gives a more intuitive understanding. But this is also a shortcut which you can follow to quickly do your calculation. Okay. So now let's look at the next problem. So if you can see, let's solve problem number 3. So average IQ of all kids, and here when I say kids, I mean all kids of the country, say is 110 with a standard deviation of 5. Fair enough. So we visited a particular school whom we are calling school A, and we randomly surveyed 50 kids within that school and found out that their IQ is 120. So what we can infer about school A kids? So what we see is that the national average is 110 with a standard deviation of 5. However, when we visited a particular school and randomly surveyed, by the way, we have to emphasize on the word randomly surveyed. We cannot survey our known people and say, okay, I'm done. We randomly picked up 50 kids and we found out that their IQ is 120. So my first impression is that probably school A kids are having a higher IQ. That's my intuition. But is it true? We'll find out. I have surveyed 50 kids. Is it enough? We'll find out. Initial impression looks like it is high. But is it really high? Let's find it out. So let's write down the problem. So for population, we have a mu or a national average of 110. Sigma is 5. As far as sample is concerned, we know that n is equal to 50 and x is equal to 120, right? Now if I apply central limit theorem, so mu is equal to mu bar is equal to 110 and sigma x bar is equal to sigma by square root of n. So sigma is 5 divided by square root of 50. So we'll first find the square root of 50, which is 7.07. So 5 divided by 7.07, and that is 0.7. Okay. Now what is that we want to find out? We want to find out the probability that even before finding out the probability, let's write down the important step. That is the alternate hypothesis and null hypothesis. So alternate hypothesis is that mu equals to, or rather mu is greater than 110, and alternate hypothesis is mu is equal to 110. Now I have said before, there is no point in doing less than, right? At best it can be equal. It's very unlikely that it will be less than, for these kids it will be less than 110, right? So now what we are trying to find out, we are trying to find out the probability that the average IQ of school A kids is 110 given for randomly surveyed 50 people it is 120. This is what we want to find out, and this is nothing but the probability of my null hypothesis. So now let's draw a normal distribution. So if we assume that this is 110, so 110 with the standard deviation of 0.7. So 0.7 is 110.7, then 112, right? And somewhere here it will be 120. Let me draw it a bit nicely, right? So this is 110, this is 120, and this is my rejection region. The region which does not contain 110 and 120. Always that is my rejection region, remember it. So let's find out the z-score of 120. So z-score of 120 is 120 by 100 minus 110 divided by 0.7, and that turns out to be 10 divided by 0.7, and this number is a very large number, very large, which means we'll get a p-value which is very low, which means that we can perfectly reject this and we can accept this. Okay, now if you intuitively also see, if the new average, right, the new average should be actually not 110 but maybe 115 or maybe something else, but it cannot be 110. These 2 points are like so far ahead, away from each other, and the z-score is so large. As you can see here, the z-score will be like 10, 11, 11, 12, maybe 13, 14. Z-score will be like 14, which is a very low p-value. So we can comfortably reject this null hypothesis and accept this alternate hypothesis, that there is hardly any chance that the IQ, the average IQ of the kids in the school is less than or actually equal to 110. It has to be greater than that. Let's tweak some parameters and see if we can make any difference. Suppose let's increase the standard deviation. Say the standard deviation, let's make it 20. Let's see now if it makes any difference. So in that case, this becomes 20. So 50 square root is 7.07. So 20 divided by 7.07 is 2.82. So this is, does that make any difference? From the naked eye, it doesn't look like. So if this becomes 2.82, still it's not, it's like the z-score is still very high. So 10 divided by 2.82 will be close to 3 point something. 2.82 is 3.54, still very high. It doesn't make much of a difference. Okay, now let's make some changes. Say this is not 120, say this is 115, or say 112. Now let's see if that makes any difference. Actually, let's make it 115. So in that case, this is 115. So this is 5 by 2.82. So 5 divided by 2.82 is 1.77. So this value now becomes 1.77. Now if this becomes 1.77, then let's try to figure out p-value from the z table. So this is the z table. So 1.77. So 1.77 will be, no, this one. So this is, so 96.16. So this side is 96.16 and this side is 1 minus 0.9616, which equals to 84, which means here the p-value is slightly better, slightly respectable. We were getting absolutely no p-values at all. Very low p-values we were getting. So this is 3.84%. Still lower enough for me to reject the hypothesis. I hope this makes sense. Now let's look at the next problem. So the problem says, in a survey conducted 2 years back, we found that 60% of households had got tablets. Today you surveyed 200 random households and found that 68% use tablets. So what we can infer? Interesting. So today we can see on serving 200 random households, we found that 68% is using tablets, which is higher than a survey conducted 2 years back. So we can clearly see that it's higher. But is it enough that we can say that today people are using more tablets? Let's figure out. So let's first write down the population information we have. The population information is 2 years back, 60%, right? 60%. And the standard deviation is, oh, we don't have any standard deviation. Also, the problem looks a bit new. So far, we have been dealing with whole numbers. Now we have suddenly got percentage. Neither we have any standard deviation. So we have to do something about this. First, let's convert it into decimal. And in this case, the standard deviation is 0.6 multiplied by 1 minus 0.6. So square root of mu. So the formula is mu into 1 minus mu. So which is 0.6 into 0.4. Square root is 0.48. This is my sigma. Now when we talk about sample, we have surveyed how many people? 200 households, and we found 68% are using tablet. So this is 200, and we found that 68% are using tablets. Okay. Now, according to CLT, central limit theorem, mu equals mu bar equals 0.6, and sigma x bar is equal to sigma by square root of 200. Actually, let's try to make the problem a bit interesting. Suppose this is not 6.8, say this is 6.3. That will make the problem a bit interesting. So 0.48, first let's take square root of 200, 14.14. So 0.48 divided by 14.14 is 0.03. So according to central limit theorem, we find this as 0.03. Now let's look at the null and the alternate hypothesis. So my alternate hypothesis is that mu is greater than 0.6. Very evident. Here this is 0.6, 0.63, and null is 0.6. Now what do I want to find? The probability of mu is equal to 0.6 given n equals to 200, x equals to 0.63. So now let's find out the z-score. So z-score of 0.63 is 0.63 minus 0.6 divided by 0.03. 0.63 minus 0.6 divided by 0.03, which is 1. So the z-score is 1. So now if this is 0.6, this is 0.63, and this side is my rejection region. So let's find out the z-score. 1 is 0.8413, which is this side. My rejection region is this side. So I have to do this 0.8413, and that is equal to 8715, which means my p-value is 0.1587, which means this one is 15.87% p-value into 100, just to take it in terms of percentage, which means, sorry boss, I can't reject I do not have enough evidence to reject the null hypothesis. I cannot accept alternate hypothesis. I do not have enough evidence to reject the null hypothesis. I cannot say that mu is not equal to 0.6, or I cannot say that mu is greater than 0.6. So that's it for today. We'll continue with few more variations of this problem.
Congratulations on completing the business dashboard using Excel course. Ready to elevate your career? Join our postgraduate certificate in data science and AI and gain exclusive benefits like a complimentary Python programming bootcamp, 7+ case studies, dedicated student support, and access to our job opportunities portal. Don't miss out on this chance to transform your career. Invest in yourself today and join our program. Click on the link in the description to enroll now and take the next step in your career journey.
So today we are going to start with a small, I would say, description, a small table which we will try to build, where we will try to show what kind of tests to be applied when. So there are a lot of hypothesis tests. So we'll look at what kind of tests to be applied when, and then we'll also look at few of the tests. So let's start writing hypothesis test here. What we already know is that hypothesis test is where we test a hypothesis which we call as an alternate hypothesis, and we try to form a null hypothesis. Then we try to find out the probability of the null hypothesis, and if the probability of the null hypothesis is low, we reject the null hypothesis and we accept the alternate hypothesis. Second scenario is we may not have enough evidence to reject the null hypothesis. So let's look at the hypothesis tests which can be done. So first division is between continuous data, and here we have categorical data. So when it comes to categorical data, we use a chi-square test, which we will see in one of our lectures, maybe in this lecture as well. And then we have continuous data. So within continuous data, we have normal distribution, continuous data which follows a normal distribution, and non-normal distribution. So there are certain tests which only works with normal distribution and certain tests which works with non-normal distribution. So let's look at these tests, and here within normal distribution we can further subdivide these tests. Actually, let's do it in the next slide. So we'll continue with this thread. This thread will look at normal and non-normal. So let's start with normal distribution. So within normal distribution, if we want to test with mean or if you want to test with variance, that decides what kind of test we actually want to use. So if we are testing with mean, then we have some tests. If we are testing with variance, then we have some test. So the test with mean are z-test, which we have extensively done in our previous videos, t-test, which also we have extensively covered in our previous videos. So if you have not watched them, please go ahead and watch. Then we have ANOVA, which we will cover. When it comes to variance, we have something called an F-test. We'll have a test called Berlet's chi-square. We are not going to cover these tests, at least in these videos. They are not much used because when we are dealing with normal distribution, mean generally suffices. Now when we deal with normal distribution, as I said, mean tests generally suffices. Now let's look at non-normal distribution, which is this side. So we have covered this, we have looked at this. Now non-normal distribution, if we look at it, so here we deal with not mean but median, right? And that's makes a lot of sense because non-normal distribution, the data is going to be skewed left, skewed right. So mean may not be the right metrics to deal with. So we deal with median, and we also have some test with variance. So here, if we want to test for variance, we use something called a Levene's test, which we are going to see. And the other scenario is if we want to test with median. So if we want to test with median, we have tests like sign test, then we have Wilcoxon, then we have Mann-Whitney. Wilcoxon and Mann-Whitney we are certainly going to discuss, and there are a couple of other tests as well. So one is called Kruskal-Wallis. So it's called Kruskal-Wallis. We are not going to discuss this test, but just good to know. Then we have a test called Moore's median. This is all for when we want to test with respect to median. And last but not the least, if we want to test with median, we can also do a Friedman test, or I would say Friedman test. So a quick recap. From hypothesis test, we can do it on continuous data, we can do it on categorical data. Within continuous data, we can have normal distribution, we can have non-normal distribution. For normal distribution, if you want to test with respect to mean, then we can do these three tests. If you want to test with variance, then we want to do these tests. For non-normal data, if you want to test with median, then we can do sign test, Wilcoxon, Mann-Whitney, Kruskal-Wallis, Moore's median, Friedman. For variance, we do Levene's test. Now you may ask, okay, why so many tests for median? Because they are tested, these tests are useful under certain scenarios with some other conditions as well. It's not only mean or median. Like in this case, as you remember in the last session, I had said that there are certain scenarios where we can do Z test, there are certain scenarios where we can do T test, and there are certain scenarios where we can do ANOVA. However, all of them are related to mean. Okay, so though we are testing for mean, but still these tests work for different purposes. The purpose is very, very different. So having said that, let's start the series of tests which we are going to discuss. So a quick recap on Z test and T test. So Z test is used when the number of samples are greater than 30, when the population distribution is normal. And how do I know whether the population distribution is normal? We'll use something called a Shapiro test, which we'll see. Number 3, when the population standard deviation and the population mean are known. And number 4, when the observations are independent of each other. So in order to do a Z test, these 4 prerequisites must be met. What are the prerequisites for a T test? Population should be normally distributed. For that, we'll use Shapiro test, which we'll see now. The variances should be comparable. For that, we use Levene's test. And yes, you're right. It's the same Levene's test which we are talking about. So we'll see what this means. And number of samples are less than 30. If these 3 scenarios are met, then we can do a T test. We can also do a T test in case population mean and standard deviation are known or can be derived. For Z test, we cannot do a Z test if the population standard deviation is not given, right? Even if the number of samples are greater than 30, but if the population standard deviation is not known to us, you cannot do a Z test. So now let's take our hands at a Shapiro test. So we are going to remove everything and we are going to do it from scratch. So let's start. So now we have Shapiro test. So here what we want to do is we want to find out whether the weight of apples in grams, what we are seeing, do they follow a normal distribution or not. As we have seen, normal distribution is a must have prerequisite for both Z test and T test. So now we are going to check how to actually ascertain, how to determine if a particular distribution is normal or not normal. So here we have taken weight of apple in grams. So here I have sorted them in ascending order. So first let's look at it in a crude way, which we have done it previously as well. Just a quick recap. So what we are first going to do is we are going to calculate the standard deviation, as you can see, for all these 55 samples. And then we are also going to calculate the mean. So we have a total observation of 55 and we have standard deviation and mean. Now, in order to adhere to normal distribution, between one standard deviation to the left of mean and one standard deviation to the right of mean, we should have 68.2% of the data. So out of 55 records, 68.2 is 37.5. So between 13.53 and 20.97, we should ideally have 37.5 records. In this case, this has to be a whole number. So let's say take 38. So 38 records should be between this range. In our case, we find that 13.51 is this to 20.97. If we go, it's up to this. And we find 35 records, which we see here. Now between 2 standard deviation to the left and right of mean, that's what we have done. 2 standard deviation to the left of mean and 2 standard deviation to the right of mean. If that is the case, we expect 52.5747. And if I take an absolute value of this, absolute value will not give me the whole number. I was trying to find the whole number. absolute value will only remove the signs. It doesn't matter. That's fine. So here 52.47, which approximates to 52. In our case, we have 54 records. So 9.81, this first record gets excluded. And then from 9.41 to 24.69, here in this case, it stops in 23.9. So we expected around 52 records, we got 54. And between 3 standard deviations, 6.09 to 28.41, we expected 55 records and we have got 55 records. Fair enough. Now, can I say that this distribution is normal? Here we can see that there is slight variation. But is it okay if I say that the distribution is normal or not normal? So for that, we are going to run a test called Shapiro test. So let's run this Shapiro test. So now what we are going to do is, we are going to copy these comma separated values and we are going to calculate the Shapiro test. So first let's look at the histogram. If I look at it, it looks more or less like a normal distribution only, more or less. So now let's decode this slowly and steadily. Here we have got the mean, we have got the standard deviation, we have got the variance, we have got the kurtosis, all are okay. Now let's understand these 3 particular statistics in detail. Okay. So now what we are going to do is, let's understand these things in a bit more detail. So let's come here. So first, since this is a hypothesis test, what we are going to do is, we are going to form the null hypothesis and alternate hypothesis. So as I have said before, null hypothesis indicates stability. So it says data is normally distributed. Alternate hypothesis is that the data is not normally distributed, which is a state of some change, right? So whenever we observe change, we test that hypothesis, we form an alternate hypothesis and we test that hypothesis. So here my null hypothesis is that the data is normally distributed. My alternate hypothesis is that the data is not normally distributed. So for Shapiro test, we use something called a W statistic, and the formula is that we get a W calculated, which we calculate from the data, and we get a W critical, which is a standard value. So for other subsequent tests, we are going to do this calculation by hand. So all the subsequent tests will follow this same formula, calculated and critical, calculated and critical. Okay. So we want to calculate this by ourselves, and this critical value is as per the standard. In this case, the tool has done the calculated for us. So the tool has done the calculation for us, and the calculation is 0.97. So I'll copy this calculated Shapiro-Wilk statistic W, that is 0.97. Here the tool has already calculated it for us. So this is 0.97. And then what is the critical value? The critical value is 0.95, right? So the critical value is 0.95 and the calculated value is 0.97. Okay. So what is this critical? What does this critical value means? That if I have to get a p-value of 0.05, what should be this value? I repeat, if had my p-value been 0.05, what would have been this value? Now, according to this formula, here it says if wcal greater than wcrit, then we cannot reject h0. If wcal is less than wcrit, then we can reject h0 and accept h1. So in this case, my wcal is greater than wcrit, so we cannot reject h0. We do not have enough evidence against the null hypothesis. If we want to be 95% sure for our alternate hypothesis, we cannot do that, because the chances of the null hypothesis being true here is more than 5% for sure, because the p-value should have been the critical value for p-value is equal to 0.05 is 0.95. If the calculated value was less than this, then I would have said that the p-value will be less or equal to 0.05. If the calculated value was 0.95, I would have said that the chances of the null hypothesis being true is 5% and this is 95%. This is my critical value for my p-value to be 5. But in this case, it is certainly more. Ideally, it should have been less. But if that is not the case, then we do not have enough evidence to reject the h0. What is my h0? That the data is normally distributed. I cannot say that the data is not normally distributed, at least from here. Okay, I do not have enough evidence to say that the data is not normally distributed. So probably I'll tend to believe that the data is normally distributed, right? Now what I want to understand is that what is this actual p-value? Here we calculated against 0.05 and we saw that the calculated value is 0.97. But if it is 0.97, right, then what is the p-value? That I do not know yet. I just know that this is greater than 0.05 for sure. But what is that exact value? That I do not know. So let's try to figure that out from this calculator. So from this calculator, it's the same thing actually. So if we just put this value once more and calculate this test, right? So here, from here, we can try to test the p-value. Let's try to calculate the p-value. So in our case, the W is 0.97 and number of samples is 55. So the p-value is 0.18. That means there is at least 18% chances. So here the p-value is 0.18. So in this case, I will tend to believe that it is normally distributed. It is having 18% chance, which is not very high, but certainly I cannot say that the data is not normally distributed. That is for sure. I have enough evidence against this fact. This is 82%, right? But I have to be at least 95% sure. And I am 82%, which is way less than 95%, right? So there's a fair enough chance that the data is normally distributed. And we also saw that. We saw that it's not perfectly normal, but like there's a fair enough chance, right? So there's an 18% chance of this data being normally distributed, and there's 82% chance that this data is not normally distributed. But in order to pass as a judgment that the data is not normally distributed, this is definitely we cannot say that for sure. Okay, so we can take this assumption and we can say that probably I'll somewhat lean towards the null hypothesis because this is way less than 95%. Okay, very less, right? So this certainly cannot be true. That is for sure. So that's how we test normality of a distribution. This is something which we have done before. Just a recap: if the distribution is not normal, you can use log transformation, feature scaling, box-Cox transformation to turn a non-normal distribution into a normal distribution. Though it does not work always. Feature scaling does not work always. In fact, in most of the scenarios, it will not work. So mainly we use box-Cox transformation to turn a non-normal distribution into a normal distribution. Feature scaling is something which we will take a look at it later, but this is a footnote which we need to understand. Okay, now we'll go to the next test called the Levene's test. So it's a test of equal for equal variance. So between two distribution, if I want to check if the variance is comparable or not, that's where we use the Levene's test. So here we have two groups, right? So group 1 and group 2. Now what we want to find, the variance which group 1 has. Does group 2 have got the same level of variance? Like for example, suppose in country A, okay, I calculate the variance between the people for education. Suppose for education, or actually not education, let's do income, right? So if I take the variance between income in country A, so this is what I want to find out, and I want to take country B, their variance in income. Can I compare these two? Are these comparable? Which means, suppose for country A, rich is say at 10, suppose an index 10, and poor is at an index 2, which means my gap is 8. In country B, suppose rich is at 15 and poor is at say 6, which means that the gap is 9. And I can say these 9 and these 8, they are like very close. The variances are comparable. The variation within country A and the variation within country B are comparable. That's where we use Levene's test. So let's look at this test. Here in group 1, we have got 9 samples. In group 2, we have got 8 samples. But that's perfectly fine. It doesn't need to be the same. I just want to understand the variance. That the variation which group 1 has and the variation which group 2 has, are they comparable? So step 1, I'm going to calculate their mean. I'm going to calculate their average. So as you can see, this is the average for group 1 and this is the average for group 2. So now what we are going to do is we are going to calculate the variance. So how to calculate the variance? So group 1, so each individual observation of group 1 minus the group 1 mean, and we'll square it up. So for this case, I take this minus this and then I square it up. Then I take this minus this and I square it up. So these are the numbers which we have got for the first one, for the second one, and so on. So as you can see here from the formula, this minus this and square it up. This minus this and square it up. This minus this and square it up. Right? For each observation, I am subtracting the mean, I am squaring it up. Now I do it for all the records for group 1, and I similarly do all the records for group 2. So for group 1, I am done. For group 2, I am done. Very good. Now what we'll calculate is the degrees of freedom for group 1 and group 2. So we have calculated that. This is n minus 1, and here this is also n minus 1. So we have calculated the degrees of freedom of group 1 and group 2. Now we are going to calculate the variance. So the variance is this sum divided by the degrees of freedom. Here we are working with some samples, so we take degrees of freedom, and in fact in Levene's test you have to use degrees of freedom. And here we calculate variance, this sum, where we have calculated the sum by taking the difference between two data points, the individual data point and the mean, then squaring them up, then adding them up, and that gives you the variance when I divide it by the degrees of freedom. Now what we are going to do is, we are going to divide the bigger variance by the smaller variance. And if I do that, so this is 17.94 divided by 17.07, and this is 1.05. Just by the intuitive look of things, we think that they are related. They looks to be related, right? The variances looks to be equal, because the closer the F statistics is to 1, the better it is, right? The closer the F statistics is to 1, the better it is. That means the two groups are comparable. Now we are going to look at the F table. So we'll open the F table. So here is our F table, and now as I had told you that we have to look at into the degrees of freedom of the numerator and the denominator, right? That's why we were calculating it, because that's required. So in this case, degrees of freedom is of the numerator, which is the bigger variance, which is this one, is 8, and the smaller one is 7. So numerator is 8 because the bigger variance is the numerator, and in this case the bigger variance is this one, group 1. So it's 8 and group 2 is 7. So 8, 7. So this is 8 and this is 7. So 8 will be this one and this is 7. And if I go right up, I will see 8 is the second right. Yes, second from the right. So what we have done is correct only. Now we are going to look at the critical value for a p-value of 0.05 for the null hypothesis. So if the null hypothesis had to be true, right? The critical value, what is the critical value for null hypothesis? When the null hypothesis does not need to be true, sorry. If the null hypothesis has to have a p-value of 0.5%, then the critical value is 3.73, not 0.5%, sorry again. It's 0.05 or 5%. So the critical value is 3.73. So let's take 3.73. That's my critical value. So here my critical value, which I found from the F table, is 3.73, and my calculated value is 1.405. So let me just remove all these things. We'll do it fresh. So my critical value is 3.73 and my calculated value is 1.05. Now what we are going to do is, we are going to look into this formula, and what we see is that the critical value is greater than the calculated value. If that is the case, then we cannot reject H0. What is my H0? So the variance of two groups are equal. And what is my H1? Variances of two groups are not equal. So in this case, I cannot accept this hypothesis, because for that to be true, my calculated value should have been greater than the critical value. If that was the case, then only I could have rejected it. But in this case, I do not have enough evidence to reject it, which is all good. But I still am curious to know what is the exact p-value for this 1.05. I want to know that, right? I know that it is certainly much greater than 0.05, because that if you see the difference is certainly greater than 0.05. But what is that exact value? This one I am not able to, I cannot accept. This one I cannot reject. But I am still curious to know what is the probability of this statement being true. So let's do that. Let's pick up this test, this online Levene's calculator. We'll pick it up and we'll try to see and derive the p-value. P-value belongs to the null hypothesis, as you already know. So here my degrees of freedom of one is 8 and the other is 7. We know it. And we are calculating against 0.05. And we saw that it's 3.73, which we have already seen before. Now what I'll do is I'll try to play with the probability value and see if I can get close to 1.05. What is that p-value which takes me close to 1.05? So if it is 1, it is 2.75. So I still need to reduce. I'm still quite far off, say 0.2, 1.93, which means the p-value will certainly be more than 20% or 0.2. So let's make it 0.3. 1.51, in our case it's 1.05. So we still need to do more, say 0.35, 1.35, no. I am at 1.05. As you can see, my calculated value is 1.05. I want to find out the exact critical value. So the exact p-value. So let's keep going. So 0.4, 1.22, which means okay. We still need to go further. Say 0.5, 1.01. So it has to be between 0.4 and 0.5. So in this case, this is 1.05 and this is 1.01, right? And which means I have now gone below that critical value. So now I have to go back, say 0.46 or 0.45. Let's start with that. 1.11. Okay, let's go slightly higher. 0.48 is 1.05, which means here my p-value is 0.48. Okay, that means the chances of this statement being true is 48%, which is a good enough number. For me, for a null hypothesis, this is a good enough number. So we certainly cannot reject this. The chances of this statement being true is 52%, right? So the chances of the null hypothesis being true is 48%, which is a good enough chance because it's as simple as, tossing a coin. When we toss a coin, the chances of a head is 50% and the chances of tail is 50%. So in this case, what are the chances of the variance, that the variance of two groups being equal? As high as the chances of getting a tail when you toss a coin. So it's quite high, right? So we have looked at Levene's test, we have looked at Shapiro test, and we have also understood what test to apply where. We have looked at the conditions, the prerequisites of Z-test and T-test. Now we will look at some other non-parametric tests, which are Wilcoxon test and Mann-Whitney test. So we'll now look at Wilcoxon and Mann-Whitney test. If you come here, it's a non-normal test. We test it when the distribution is non-normal and we want to test for medians. So we are going to look at these two tests now, Wilcoxon and Mann-Whitney. Okay, so let's start on Mann-Whitney and Wilcoxon test. So as I have mentioned before, these tests are non-parametric in nature and mainly they are using median as the evaluation parameter. So what is a non-parametric test? So a non-parametric test is a test where the test can be applied to any kind of distribution. So far we have looked at Z-test and T-test, which can only be applied for normal distribution. So let's look at Mann-Whitney and Wilcoxon test and the difference between those tests. So we have completed up to Levene. So let's look at Wilcoxon test. So Wilcoxon test is used if the population distribution is not normal. But does that mean that it can't be used when the population distribution is normal? It can be used. But generally, when the population distribution is normal, we use Z-test or T-test. It is called a non-parametric test, which means that it does not depend on the underlying distribution, whether it's normal or not normal. So when it's normal, we use Z-test or T-test. When it's not normal, we use Wilcoxon and Mann-Whitney. But having said that, Wilcoxon or Mann-Whitney tests are generally used if the distribution is not normal. Third assumption is that the observations have to be ordinal, which means the observations which we are going to use as part of our experiment that have to maintain some order. Fourthly, and most important, that Wilcoxon tests are done on the same group before and after an event. So, for example, I want to build a drug, and I want to apply the drug on a human being before, or rather, what I want is, I want to measure the impact of drug on the height of a individual. So I will measure take their measurements of few individuals before applying the drug and after applying the drug. However, that does not work with Wilcoxon. Wilcoxon is always on the same group. So generally, a same person undergoing multiple experiments, right? Like, for example, let me give you an example. Say here, we are looking at the performance of students before joining a tutorial and after joining a tutorial. So we have recorded the marks of the students across 13 subjects. As I said, it has to be on the same group. A common mistake what I see is people apply this test on different groups. That cannot work with Wilcoxon. For that, we have a different test. So here, it's on the same group, but before and after a certain event. So here, who is the group? Group is my student 1. He is the focal point in this case. So we want to measure his metrics before and after an event. What is the event here? During the tutorial. So, and after joining the tutorial. So before joining the tutorial and after joining the tutorial, we have recorded the marks. Now what we want to find out? What we want to find out is, has there been any significant difference in the score of student 1 after joining the tutorial, right? Can we observe any difference which we can call as statistically significant? So here are the scores before joining the tutorial and after joining the tutorial. So on a naked eye, what we can see is mostly the scores have increased. But is it statistically significant enough for me to say that yes, probably the tutorial is having an impact? So let's find out. So it's a very simple test actually. The calculation is not very complex. So first step, what we are going to do is, we are going to calculate the difference for each line item. In this case, these subjects. So here, for each line item, we calculate the difference. So as you can see, we have calculated the difference before and after. So after minus before is what we have done. And we have seen that in these two cases, in these three cases rather, it's negative. Rest are all positive. So in these cases, we have seen that the marks of the student has increased. In these subjects, the marks of the students has decreased. So the next step, what we are going to do is, we are going to calculate the absolute difference. So here, as you can see, we have a sign, but now we are getting rid of the sign. We are taking the absolute difference. So this is the absolute difference. So in the next step, so here, as you can see, this is the difference and this is the absolute difference. Now what we are going to do is, we are going to create a rank. So as you can see, the lowest one is 0.1 as far as absolute difference is concerned. So we have given it a rank 1. Then 1 is a difference where we have given it a rank 2. 1.2 is rank 3. Difference of 2 is rank 4. 2.2 is rank 5. 3.1 is rank 6. 5.3 is rank 7, and so on. Now, in the next step, what we are going to do is, we are going to identify where the difference was negative, and we are going to add their rank. So as you can see here, we have added the rank where the difference was negative. And we also add the rank where the difference is positive. So from here, it's positive. As you can see that the sum is 75. And here, this is 75 and this is 16. 16 is the three negative ones. Now what we are going to do is, we are going to take a minimum value of these two. So the minimum value, as you can see, it's 16. So we are going to take that and we are going to call it as W calculated. So here is my formula. So I have put W calculated as 16. Now, so let's remove this, because let's keep that as a suspense. Let's also remove this. Okay. So now we are going to find the critical value. So let's look at a critical value from the Wilcoxon sign rank test. So here, what are my number of observations? It's 13. So am I doing a one-tail or a two-tail test? So let's start with a two-tail test. So if it's a two-tail test, then the critical value for alpha is equal to 0.5 is 17. So for alpha is equal to, so critical value is 17 for two-tailed test. So we just want to know whether there's a difference or not, right? So now we are going to follow this formula. What does this formula says? if W calculated is greater than W critical, in that case we cannot reject H0, which means there is not enough evidence to reject, or there is not enough evidence against the null hypothesis. However, if W calculated is less than W critical or equal to, then we can reject H0 and accept H1. So in our case, this is true. So W calculated is 16 and W critical is 17. So we can reject H0 and accept H1. Now, what is H0 and H1 here? H0, as you can see, it's a state of equilibrium. So which in this case is that median 1 is equal to median 2. What is H1? Median 1 is not equal to median 2. That means the performance of the student has changed after joining the tutorial. So here we are doing a two-tailed test to start with, right? So what we'll also do is that we will look at an online calculator and see how that behaves for Wilcoxon. So this is a test. It's a two-tailed test. We are starting with a two-tailed test, and the significance level we have kept at 0.05. So we have kept the values before and after, and let's calculate. Let's see what do we find. So what we find is that the p-value is equal to 0.039, which means only 3.98% chances are there that the null hypothesis is true. So the chances of this incident to be true is 3.98%. That is less than 5%. So which means we can reject this hypothesis and we can accept this hypothesis. Now let's make some changes. So what we'll do is, say, let's make some changes to the score. Say I make it as, say, 14. Say this one as 12. I'm just trying to bring the scores closer, or say 12.5 rather. Say this is 18. So I have made some changes to the score. Does it make any difference in this case? So let's also make this as 8.5. Okay. So we have made some changes to the score. Let's do a couple more. Okay. So now we have made certain changes to the score. So let's see the impact of that. So I'll copy this entire thing from here and I'll paste it here. Now let's mark all the yellow ones where I have negative difference. Any other negative differences? Okay, I actually need to copy this as well. All right. So here is one more and here is one more. So we have taken all the negative differences. Now we have converted them into absolute differences. Now let's try to do the ranking. So we have to be very careful here so that we do not make any mistake. So this is 1, this is 2, this is 3, this is 4, this will be 5, 6, this should be 7, 8, 9, 10, no, this should be 9, 10, 11, no, I'm again making mistakes. So let's do it. After 5.6, oh, there's a 4.6 also here. See, this is very confusing. So 1 is this, 2 is this is 3, this is fine, 4, 5, 6 is fine, 7 is fine, this will not be 8, this will be 8, this will be 9, 10, 11, 12, 13. So now I think it's correct. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Fine. So here we have got the sum of positive negative differences as 19 and positive as 72. So let's do 19 and 72. Now we can see that we cannot reject H0. We have come into this zone now. We cannot reject H0. And if I want to know that what is the exact probability for null hypothesis, so what we can do is, let's try to copy this and try to paste it here. So this is before and this is after. So now let's do the calculation and see what do we find. See, as you can see, H0 is accepted. Why? See the probability, 14.65%. Though I have hesitance to say that we'll accept H0 until the p-value is very high, I think the safer bet is to say that we do not have enough evidence to reject H0. So in this case, my H0 is 14.65, which means my chances that this statement is true is 14.65, which means there has not been any change in the performance of the student. Now, if I have to do a one-tailed test on the same thing, say I'll say median 2 is greater than median 1, right? So if I have to do that, So what I'll do is I'll just make it a one-tail test. Let's say do before and after. It's obvious that it cannot be before, cannot be greater than. At least from this data set, we cannot say that before is greater than. Actually, I have given before greater than after, so it should be before less than after. Yeah, at least on a naked eye we see that the after one is better. But is it good enough to say that it's statistically significant? Let's see. In that case, what is the p-value? Around 7%, around 7.32% chances that, right? Around 7.32% chances that we can not reject H0. And as you can see, the larger the p-value, the more it supports H0, because p-value always represents H0, which I have been telling throughout my lectures. Okay, so here the chances are that 7.3% chances are there that it has increased, or rather it has not increased, it has stayed the same even after joining the tutorial. Okay, so not only you should look into this table, at the same time you should also look at these online calculators just to find out what is the exact p-value, and that will make the subject even more interesting. Else just doing this calculation from here, putting in this formula, it's not a big deal. The fun starts when you start exploring and understanding what are the chances of the null hypothesis being true. So if you have followed my previous lectures, previous series, even this particular video, you have seen that I always stress on also finding the p-value. That makes it very, very interesting. Okay, so in this case, if median 2 is greater than median 1, the performance of the student has increased after joining the tutorial. That's the interpretation. But has it actually increased? Statistically, we cannot say that. We have to be at least 95% sure. In this case, we'll be probably 85.35% sure. So the chances of this statement occurring is 85.35%, right? Okay. So now what we will do is we'll look at another test, and this test is called the Mann-Whitney test. So here again, this is used if the distribution is not normal, the observations has to be ordinal. This is applicable to independent samples. This is called non-parametric because it does not depend on the underlying distribution. But what is the most important point is that the tests are done on two different groups. In Wilcoxon, we saw that the subject was one. I mean, subject, not the study subject, the experiment subject was student 1, which was the same subject, right? Here, the experiment subject will be two different groups. So let's take an example of Mann-Whitney. Suppose here we have two movies. So movie A and movie B. And whatever you see on the these numbers, these are nothing but the ratings of the movie. So movie A has got certain ratings by the critics. Movie B has got certain ratings by the critics. Now, what we are going to do? We are going to create an ordered list. In the ordered list, what we are going to do? We are going to take the ratings from both the movies and put it here. And then we have ordered it. So first we took the ratings from both the movies and then we have ordered it. So here, what is my objective? My objective is to find whether there is any significant difference between the ratings of these two movies or not. If we are doing a two-tail test. For one-tail test, we'll see again greater or lesser. But we want to prove things statistically. Is it statistically significant that movie A and movie B have got different ratings? They're different in nature, right? And here, as you can see, intentionally, I have done is I have made one less observation in movie 2, which means it's not mandatory that the number of observations has to be same. So this is done by purpose to show you that this test absolutely works even if the number of samples in the distributions are not equal. So here we have created the rank and we have ordered the list. So now what we are going to do is, as you can see, in a lot of cases, there has been a tie. I can see 1, 2. Actually, I think we need to order this. So what we'll do is, let's pick this one. Let's do it from scratch. Let's pick this one. Let's pick this one. So I will not consider this. It's fine with the borders. Now let's try to order this. Oh, I think it was correct only. So, oh yes, this was correct only. We had 3 2s. Sorry, my bad. Everything was correct. So here we have 3 2s. So all these 3 2s are coming at the top. So 1, 2, and 3. Then we have 2 3s, which are here. Then we have a 4. So this is the 4. We have 2 5s. We have 2 6, and then we have 7, 8, and 9. So this is my ordered list. Now what I have done is here, as you can see, these colors signify something. What we see is that all the 3 numbers are 2, but the rank is 1, 2, 3. Here again, both the numbers are 3, but the rank is 4 and 5, which is not correct, right? So I can tell you that what used to happen in my school days is that whenever we used to get same marks, since my name is Suvajit, it was like S was way behind in the alphabet, right? So any guys who are having names starting with A or B or C, right, D, in spite of having the same marks, my roll number was used to be behind. And when we used to study, the roll numbers, at least in my school, the roll number was based on the marks you get on the previous class. So a lot of times, in spite of scoring the same marks, just my name started with a different alphabet, an alphabet which comes later in the series. So my roll number was a bit behind in spite of getting the same marks. So here the same thing has happened, and this is not correct. This is not fair. So what we have done here is, as you can see, this is my initial rank, which is same as this. Then what we have done is we have created an updated rank. And how we have created this updated rank? So we have taken the average of these 3 ranks. So average of 1 plus of 1, 2, and 3 is 2, which we have put here. Average of 4 and 5 is 4.5, put here. Average of 7 and 8, here we are a tie here, so that is 7.5. Average of 9 and 10 is 9.5. So now we have made sure that there is no injustice. So we have created an updated rank. So now let's see what we can do with this updated rank. It's very simple. Now we go back to the original distribution and we plug these updated ranks. We plug these updated ranks against the movie ratings. Once that is done, we take a sum of these ranks. Sum of rank for movie A, sum of rank for movie B. Then we do something which we called as calculating mu statistic. So if you see, mu statistic is the rank sum minus n into n plus 1 divided by 2. What is n? The number of observations. So we'll do it for both the groups. So as you can see here, this is rank sum. Rank sum is B9 minus n, which is this count, into n plus 1 divided by 2. And here we have done the same thing. D9, which is the rank sum, minus n into n plus 1 by 2. And then we take the minimum of these 2 values, which is 5.5. So as you can see here, I have put this in the formula as well. So everything gets automatically calculated. So now let's come back to the calculation. So here we have got 5.5 as mu calculated. Now let's look at mu critical. So here is the Mann-Whitney table. So we'll get the critical values for here for our 2-tailed tests. So now what we'll do is, let's try to figure out this N1 and N2. And as you can see, there it can be different. So here in this case, my N1 is 7 because I have 7 observations. Here my N2 is 6 because I have 6 observations. So my N1 is 7 and N2 is 6, which means 7 and 6 intersects at these 2 rows. So the critical value at 0.5 confidence interval, or alpha, not the confidence interval directly, I'll check alpha at 0.05 is 6. So now let's take that and see. So the critical value is 6. And as you can see here, if mu calculated is less or equal to mu critical, then we can reject H0 and accept H1. And if mu calculated is greater than mu critical, then we cannot reject H0 because we do not have enough evidence to reject, or we do not have enough evidence against the null hypothesis. So as you can see here, the hypotheses are that rank 1 is equal to rank 2, which means the distribution is same, which means the movies are same basically. They come from the same distribution. And H1, the alternate hypothesis is that the rank 1 is not equal to rank 2, which means the distribution are not same. So in this case, we have found that we can reject this theory and accept this theory. So if I want to know the exact p-value, which I always recommend you to do, because that makes the subject interesting. So here we have values from both the groups. We are looking at a two-tailed test at a significance level of 0.05. Everything is fine. Let's calculate. So what do we find? 3.05% chances of the null hypothesis being true. Okay. And as you can see, the smaller the p-value, the more it supports the h1, because p-value always belongs to h0 or my null hypothesis. Now, if I start to make some changes here, say for example, I make it 6. I'm just trying to make it closer to the original data. Now let's see what does it come. Now I expect it to be, we'll not be able to reject the null hypothesis so easily. So here we have crossed the barrier, 5.86%. So the chances are that now we cannot reject the null hypothesis with at least 95% confidence. Let's try to bring them even more closer. Say, I'll try to increase this more. Let's try to see. Now what we see is something very interesting. The p-value has become very high, 94.16, which means 94.16% chances that the two movies are coming from the same distribution, right? Or maybe two movies are same, or the ratings are actually collected from the same distribution, or maybe if I just want to distinguish whether movie 1 and movie 2 are actually the same movie coming from the same distribution, you can think of various interpretations of that. But what we see is the p-value has become very, very high, right? So that's it on Mann-Whitney test. Now the last test for this lecture we will see for ANOVA. So the full form of ANOVA is analysis of variance. So now what we are going to do is, it's a different kind of test. So let's open ANOVA. So as you can see here, we have 3 movies and 4 critics, 3 columns and 2 rows. So far what we have seen is that we are comparing the same subject across 2 groups or maybe 2 different distributions. But with ANOVA, we see that there are 3 distributions, not 2. Moreover, ANOVA deals with variance. So far we have been mainly dealing with mean and median. So what does the basic premise of ANOVA? As we can see, there are 3 distributions. So whenever there is a distribution, they will have some variance. So movie 1 is going to have a bit of variance, movie 2 is going to have a bit of variance, movie 3 is going to have a bit of variance. So the point which we want to prove is the variance of movie 1, the variance of movie 2, the variance of movie 3, are they comparable or not? If the variances across the movie are more or less the same, right? Then in that case, what we can see is that probably the variance is not coming from this side of the data. The variance is probably coming from this side. Let's understand this intuitively. So here there can be 2 scenarios. One is that the critics are very different, which means they're for the same movie they're giving different kind of scores. Like this is movie 1, but suppose for example critic 1 gave 3, critic 2 gave 9, critic 3 gave 5, critic 4 gave 8. So what we see is that there's a huge discrepancy in the way that critics are giving the scores. Like for example, for this movie again, critic 1 gave say 4, critic 2 gave 8, critic 3 gave say 6 maybe, critic 4 gets 7.5. So as we can see, for the same movie, the scores by the critics are very different. Third scenario, third movie, critic gave 3.5, here critic gave 8, here he gave 7, he gave 6.5. So here what we see is that the variance in the data is coming from the fact that the critics are very different. For the same movie, the scores are very, very different. However, when we look across the columns, we do not see much of a difference. So a particular critic have more or less given similar kind of ratings for 3 movies, which means the difference, the variation in the data, the total variation in the data can be attributed from this part, not from this part. So we call it as between or within. So this part is my within and this part is my between. So between the movies or within the critics. You have to think like that. Within is the row, the variance in the row, between is the variance within the column. So in this case, let's do the calculation. So so we have to calculate three things: sum of squares within, which is within the rows, sum of squares total, the total variance, and sum of squares between, that means between the columns. So how to calculate sum of squares within? So this is the sum of group mean minus each element square. So here, this is the group mean for movie 1, group mean for movie 2, group mean for movie 3. So now what I'm going to do, I'm going to take each individual observation and then subtract it from the group mean, square it up, and then keep on adding them. So as you can see here, for each group, for this group, we are taking this value, subtracting it from this, squaring it up, then adding. Then we'll again do it for this, with this, with this, with this, with this. We'll keep on subtracting, squaring, and then adding all of them together. And that will give me sum of squares within, across the rows. Then sum of squares total is sum of grand mean minus each element square. What is grand mean? Grand mean is nothing but mean of all group means. So if I take all these three group means, I get a grand mean. Now from grand mean, I am going to take each observation, subtract it, square it, and then keep on adding it. So I'm going to have 12 additions. 12, subtract, square, and add. So as you can see here, we have 12 expressions. So that will give me sum of squares total. Now what is sum of squares between? Sum of squares total minus sum of squares within. And as you can see, sum of squares between is very, very low, which is expected because there is hardly any variance between them. But sum of squares within is very, very high. In fact, out of the total variance, it's all coming from within part, not the between part. So here, as we can see, between is very, very low. So now how to calculate ANOVA? So here we have to calculate something called an F statistics. So we have calculated SSB, sum of squares between. We have calculated SSW, sum of squares within. And as we can see, the formula is right here. So let me just squeeze it slightly so that you can see the formula while we do the calculation. I'll bring it here. Maybe here. Yeah. So this should be fine. Right. So N is number of groups. How many groups are there? There is the number of columns is 3. N is number of elements within each group. How many rows? 4. M-1 and N-1, because as you can see in the formula, we need M-1 and N-1. So that is 2 and 3. Now we have to calculate the numerator and the denominator, and then we'll get the F statistic. So the numerator is 0.02. How is it calculated? Sum of squares between divided by M-1. So sum of squares between divided by M-1. Then F stat denominator, sum of squares within divided by M into N-1. So as you can see, M into N-1. So that gives me denominator. If statistic is numerator by denominator, which we get as 0.004. Very, very low. So now let's make some changes to the data and let's see how it behaves. So now let's try to create kind of a balance in the data. So let's try to create some difference between the movies. Here, so without doing any calculation, we can clearly say that there is no statistical difference, or there is the difference between the columns is absolutely not statistically significant. The value is very, very low, and the contribution is coming all from within, not from between. Now let's try to create some gaps within. So suppose movie 1 or critic 1. So he has given 5 here, maybe say 2.5 here, and say 8 here. Critic 2, say for the same movie, say 6. 7.5, or rather say 3 and say 7. Critic say 9, 6 is fine, or rather let me say this is 7, this is 4. So I'm just trying to create differences between the movies. So this is 7.5, and then last but not the least, so this is 6, this is 5.5, and this is say 9. Now we can see that the sum of squares between is high. Fair enough. But is it high enough for me to say that sum of squares between is there? So let's find it out. So this F stat which we have calculated is 16.27. So let's come here and plug it. So calculated is 16.27. Now we have to find the critical value. So we can find it from the F table. So degrees of freedom in the numerator and degrees of freedom in the denominator. So in the numerator, my degrees of freedom is 2, denominator is 3. So 2 and 3, which means this is 2, this is 3, and this is where I need to pinpoint. Now with 0.5 as the p-value, this is my critical value, 9.55. So let's just plug it in. So this is 9.55 at 95% confidence. Now let's see what is my H0 and H1. H0 is state of equilibrium. Mean 1 is equal to mean 2 is equal to mean 3, which means the variance between the groups is not more, but the groups are like very similar in nature. And the difference is coming from within the rows. And H1 is mean is not equal to mean 2 and not equal to mean 3, which means the variance of the between the groups is more, or the groups are not similar. And this can be ANOVA works when we have 3 or more groups to compare. It's not only 3, it can be even more. So now let's just plug the values. So this is 16.27, and the critical value is 9.55. We can reject H0 and accept H1. So what is my H0? This is my H0, which can be rejected. And this is my H1, which can be accepted. So variance between the groups is more. We accept this theory and reject this theory. Okay. So that is it from ANOVA. So we have learned a lot of tests, and with this we are going to complete the set of hypothesis test. Now we are in the next series, we are going to look at correlation, covariance, and chi-square, which tests the relationship between categorical and continuous variables. If you have liked our videos, the prior videos, as well as if you like this current video, please like, share, subscribe, spread the word. So today we are going to solve few more problems, and we are also going to learn about t-test. So far we have worked only with z-test. So we'll solve t-test problems today. We'll also look at different variations of t-test, one sample t-test, two sample t-test, and pair t-test. So let's get started. So we had solved till problem number 4. So let's pick up problem number 5. So spend a couple of minutes in reading the problem. Let's understand what the problem is. So a chair manufacturer has spent 5 million in upgrading the equipments to lower the defects in chair. So right now, when the chairs are getting manufactured, we are finding defects in those chairs. The current defect rate is 20%. So out of 100 chairs being prepared, we are finding that 20 chairs are having some defects. So the chair manufacturer spent some money, around 5 million, and he upgraded the equipments to ensure that the defect rate drops. So you are asked to develop a hypothesis that the defect rate has dropped below 18%, or rather you are asked to test a hypothesis. So the owner believes that his defect rate has dropped below 18%. So you are asked to test his hypothesis that it has dropped below 18%. So in order to work with it, in order to prove it, you pick up 150 random samples and found 30 defects. Now can you use this experiment to say that the defect has lowered, or rather the defect has dropped below 18%? I think that will be the right question. Okay, so let's get started with our tried tested formulas. So first what we'll do is we'll write the population data. So we'll take mu. So mu here is, just pause the video and tell me what is mu here. On a count of 5, 4, 3, 2, 1. The correct answer is 18%. If you have thought 20%, then this 21% has been given just to confuse you. It has no relevance in the test. We really do not care about this entire statement. Our problem actually starts from here, from this part. Okay. So now we assume that mean is 18% or 0.18. Let's calculate the standard deviation. Here, by the way, this is, let mu be 18%, right? We do not know whether it is or not. So as far as the standard deviation is concerned, into 1 minus 0.18. So that gives me 0.38. So now we have got the mean and we have got the sigma. From the sample side, let's see what we have got. We have n, which is 150 and we found 30 defects. Now this mu is nothing but my defect rate. So x, or the value against which I am going to test, this should also be a defect rate. So how do I calculate the defect rate? I pick up 30 defects. We got 30 defects in 150 random samples. Okay, so 30 defects out of 150 random samples. We'll just come here in a moment. Now let's construct the null and the alternate hypothesis. So the alternate hypothesis is, so we need to test this. So this is my alternate hypothesis, that mu is below 18%, mu is less than 0.18, and my null hypothesis is that mu is 18%, right? So let's calculate the defect rate, which will be 0.2, right? So if we get 0.2, now let's calculate the z-score. So z-score of x is equal to x minus mu by sigma x bar. So we also need to calculate the sigma x bar. So sigma x bar is sigma by square root of n, which is equals to 0.38 by square root of 150, which is equal to, so 150 square root is 12.24, 0.38 divided by 12.24 is 0.03. So my critical value, sorry, my z-score is of 0.2 is x minus mu divided by 0.03. So if I calculate 0.2 minus 0.18 divided by 0.03, which is 0.67. So we got a z-score of 0.67. From here I have to find the p-value. So p-value is the probability that this particular statement is true. So let's find the p-value from the z table. So this is the z table. So our p-value is 0.67. 0.67 is here. Okay. So 0.67 is 7.7486. Okay. So if this is my distribution, this is 0.18, this is 0.2. So my rejection region is here. So what I have got is a p-value of 0.7486, which means this side is 0.7486. I need this side. So this side is 1 minus 0.7486, which is 1425, or in another term, so this is 0.2514, which means the probability of this statement being true is around 25.14%. Now if that is the case, I cannot reject the null hypothesis. I cannot, right? This statement can certainly be true, right? I cannot reject this. So if I look at carefully into this problem, why I got such a big p-value? It must have struck you that this time the p-value is really high. Ideally we want this p-value to be how much? To be less than 0.05. Then only I can reject the null hypothesis. But this time it's very high. How come this happened? And under what scenario this can happen? So if you carefully observe, when we had formed the null and the alternate hypothesis, here when we had done the experiment, we had found that the defect rate is 20%. However, when we formed the alternate hypothesis, we said that this is less than 18%. So that itself shows that my formulation of the hypothesis is not correct. Here I saw that it's 20%, but my hypothesis says that it's less than 18%. So these two are in stark contrast of each other. And it was expected that something like this can happen. The p-value got very, very high. So which means whenever you're constructing the null and the alternate hypothesis, you should first observe what you are trying to formulate, and you should observe the experiment properly, right? So let's get back to the previous problems once. Like in this problem, my observation is that 68% now is using tablet out of 200 random households, and previously it was 60%. So it's evident that it has increased. And if I put a alternate hypothesis that mu is greater than 60%, I'll be fine, right? But in this case, I clearly see that this is 0.2, but I found a hypothesis that it is less than 0.18, which is difficult to be true in any case. So in this case, my outcome is that I do not have enough evidence to reject the null hypothesis, or I do not have enough evidence against the null hypothesis. You can use any one of these statements because the chances of the null hypothesis being true in this case is 25.14%. I hope this makes sense. So now let's move on to the next problem. So far, whatever we have seen, that all the problems we have solved are part of one tailed test. Now what does that mean? So if you look at our alternate hypothesis, so we had said mu less than 60%, right? Or mu greater than 110. So we have tried to solve this kind of problems, where in the alternate hypothesis, if you see that I am checking only one side, that is either greater or lesser. This is called one tail test, when I am checking only one side of the distribution, which can be either greater or lesser. Now if we want to test whether something is equal or unequal, that's where we use a two-tail test. Why it's called two-tail? Because not equal to means it can be greater or can be lesser. So let's write down. So if you see, it is not equal to, which means it can be greater or lesser both. It can be greater than 60 or it can be lesser than 60. Unequal means that. So here it is testing both the sides. So that's why it's called two-tailed tests. Are things going to change fundamentally? Not much, apart from one minute change. So let's take a look. So let's take this problem. So you have made a new recipe in your restaurant. Okay, so you're a cook maybe, and you constantly innovate. So as part of your innovation, you have made a new recipe, and previously in your restaurant you used to have a footfall of around 60 customers on an average per day, I would say, with a standard deviation of 10 customers. So after you have made the recipe, you counted the number of customers over the last 5 days, and you found around 400 customers over the last 5 days, which means an average footfall of 80. So has this recipe worked magic? So if I have to convert this in a two-tailed test, ideally, from this question, I would say, okay, if it is greater or lesser, but let's convert this into a two-tailed test, right? Or so has this recipe worked magic or has it bombed? So basically, we are trying to see if there has been any change after you have introduced this new recipe. So what we'll do is, let's write down the problem. So the problem is, you have a footfall of 10 customers on an average per day with a standard deviation of 10. Okay. So population data, that is the first thing you should write. Mu is equal to 60 and standard deviation is equal to 10. That is my population data before we introduce the recipe. Now from the sample perspective, you have X and you have N. So X is 80, last 5 days number of customers is 80, and N is 5. So let's write down the alternate and the null hypothesis. Let's go to the problem. So the hypothesis which we are testing is whether it has changed from 60 customers or not. So not equal to 60. Always remember alternate hypothesis has to always deal with a change. So whenever you notice some changes, then only you want to do this hypothesis testing. And whenever you have noticed a change but you just want to confirm that statistically, that's where you end up doing hypothesis testing. So alternate hypothesis is what your belief which represents a change, and null hypothesis is something which represents a kind of a equilibrium. That means nothing has changed. So let's do the calculation. So first we'll calculate sigma x bar, which is sigma divided by square root of n. So sigma is 10 by square root of n, which is 5. So 2.23. 10 divided by 2.23 is 4.48, which is my standard deviation. So z of x is 80 minus 60 divided by 4.48. So 20 divided by 4.48 is 4.46. It's too high. I don't even need to look at anything. I don't even need to look at the p-value. A z-score of anything, if it crosses 1.6, 1.7, it's like too high. So I can confidently, and in this case what will happen is that the p-value will be too low. So if the p-value is too low, the chances of this statement occurring is going to be very, very low, which means I can reject this and I can accept the alternate hypothesis. Now let's try to make some changes to this and see how it works intuitively. Now if you think this is 80 and here like it's 60 was the previous footfall with a standard deviation of 10, and here we found 80. So what we can clearly say is that it's very obvious that something has really changed. The number, if you see the number intuitively also, it looks to be changed. Now let's take an exercise. What we'll try to do is, let's try to see how we can increase the p-value here. Which means if I have to increase the p-value, I have to decrease this z-score, right? If I have to decrease the z-score, what are the ways in which I can decrease? One way is I can increase this. If standard deviation goes high, then automatically z-score will decrease. So let's come here. If I have to increase the standard deviation, what I can do is I have to decrease this n. If I decrease this, then standard deviation will go high. That's one way. Another way is if I increase this standard deviation, then also sigma x bar will be higher. So for example, let's say make it 20. If this is the case, then what will happen? So 20 divided by 2.23, which is square root of 5, is 8.96. Will it make a difference? So 20 divided by 8.96, it will still be, if this part is 8.96, so 20 divided by 8.96 will be 2 point something. No, still high. So still I am not convinced. So let me make it even higher. Say 30. Let's see now. Does that make a difference now? So 30 divided by square root of 5. Let's try this one. 13.45. Yeah, now I think we should get something meaningful. So this part will be 13.45, which means, so 20 divided by 13.45, that is 1.48. So if that is the case, let's see. So z-score is 1.48. Okay. So now the p-value does not, I don't think it will be too low. So 1.48. So let's first draw the diagram. So this is my mu, which is 60. This is 80. And this part is my rejection region. So if I go and find out 1.48, so 1.48 is 0.93, which is this side. So if I have to calculate the other side, this is 1.1 minus 0.93, which means 0.07. That's my p-value. Now, for a two-tailed test, so far what we have seen is that for one-tailed test, the p-value has to be less than 0.05. In this case, this is slightly higher. So anyways, I cannot reject the null hypothesis. But for a two-tailed test, this is a change. It is not 0.05 anymore. Because now I am testing two sides, greater as well as lesser, which represents inequality, right? So this 0.05, which I was getting for one-tailed, where I was only testing either greater or lesser, now this 0.05 is going to be get divided by 2, because this will, both of them will take or stake claim in this 0.05. Previously it was only being taken by greater or lesser. So here this is not equal, which means both greater and lesser, and both of them will take a pi on this 0.05. If that happens, then what will happen is, for each of them, like this one is 0.05, fine, no problem. Both of them combined is 0.05, but each of them will get 0.025, which means when I'm getting the rejection region, I'm only getting it from one side. So whatever we are getting from 0.07, this is not sufficient for this. It's only testing greater side, but I also need to check the other side. So in this case, my p-value will be this into 2, which means it will be 0.14. So we can clearly see that I cannot reject the null hypothesis here. So let's make some quick changes. So let's bring down the sigma, maybe make it 25, just to now check if I want to now reduce the p-value slightly, and I want to reject the null hypothesis. So if this is 25, so 25 divided by 2.23 is 11.2. 20 divided by 11.2 is 1.78. So if that is the case, let's find out the p-value. So 1.78, p-value is 0.9625. So let's write down 9625. So 1 minus, so 3.75 is this one. So in this case, 0.03.75 into 2 will be my p-value. So no, it's still we are not able to reject. So what I have to do is I have to reduce this slightly more. So if I say make it 22, I think we should be able to do that trick. So 22 divided by 2.23 is 9.86. So this is now 9.86. So 20 divided by 9.86 is 2.02. So our Z score is 2.02. So 2.02 is 0.9783. And now I can clearly say that yes, we can reject it. Why? Because now if you look at carefully, whenever I'm calculating one side, right, I want one side to be actually less than 0.25, right? Then only if what is my ultimate objective? My ultimate objective is to get a p-value of 0.05 for both greater and lesser, which means each side is getting 0.25, sorry, 0.025 actually. So each side is getting 0.025, which means this is my cutoff, because this side is 0.97. If I have to get a p-value of 0.025, then I have to cut at this point, which means 1.96 is my cutoff. If my Z score goes beyond 1.96, then I can reject the null hypothesis. So for a two-tailed test, the shortcut is a Z score. If the Z score is between this range, then you can not reject A0 or null hypothesis. Okay, and if the z-score is greater than 1.96 or lesser than minus 1.96, then you can reject the null hypothesis. So now let's quickly do one more problem, our last problem in z-test, just to recap our concepts. After this we'll move on to t-test. So your restaurant has got red interiors and the customers were spending before 5,700 with a standard deviation of 3,000. Fair enough. Now you have changed the color. So from red, probably maybe you have done green or blue, whatever. Now you believe that the customer spend will also vary with it. So you randomly surveyed the spend by 300 customers and you found that their average spend is 6,000 rupees. So now the question which we need to answer is, did this change of interiors or did this change of colors, did it have any impact, rather any significant impact in spending by the customer? So let's write down the problem. From our population, we have mu, which is 5,700. We have sigma, which is equal to 3,000. And here we have sample. So I have x, I have n. So this is 300 and my x is 6,000. Now let's write down the null and the alternate hypothesis. So the null hypothesis is that mu not equal to 6,000, sorry, not equal to 5,700, and here mu is equal to 5,700. Now let's calculate sigma x bar. Sigma x bar is sigma by square root of n, which is 3,000 by square root of 300. This is 17.32. So 3,000 divided by 17.32 is 173.21. Now let's calculate the zx, which in this case is x minus mu by sigma x bar, which is equal to 6,000 minus 5,700 divided by 173.21. So we get a z-score of 1.73. So if we see here, it is falling in between, which means I cannot reject the null hypothesis. I'll say, sorry, I do not have enough evidence to say that the spending has changed. So I cannot reject this. Now if I have to increase the z-score, here notice that I have not even looked at the p-value. In case I have to, let's do that as well. Here's 6,000, and this is one of the rejection regions. The other is on this side, but I'll not calculate there. I'll rather find it here and then multiply it. The z-score of 1.73 is 0.9582. There is the other side. This side is 0.9582. So this side will be 1 minus 0.9582, which is equal to 0. So my p-value 0.0418 into 2, which is 3608, which means the chances of this being true is 8.36%. So that's why I cannot reject the null hypothesis, because this has to be less than 5% for me to reject it. So let's try to just make some changes and try to see if I can make it reject. At what value? So ideally this has to be greater than 1.96. So if I have to increase the z-score, I can probably increase this value by a bit. See if I make this 6,500. So in that case, this will be 6,500. So 500 by 1.73. So 500 divided by 173.21 is 2.88. A z-score of 2.88. If I come here, 2.88 should be this one, I guess. Yes, 0.9999.8. Okay, so this is, if that is the case, then this is 200, which means even if I multiply it by 2, it's not going to be very high. So in that case, I can reject. So this is it from z-test. Now we'll continue with or start t-test. Okay, so now let's start exploring t-test. So let's look at t-test. So t-test is a mini version of z-test. It works like z-test but with some differences. So all the conditions which we have done so far, which we have satisfied so far, the concept of null hypothesis, alternate hypothesis, concept of z-score, concept of central limit theorem, to a very large extent they apply to t-test as well. Of course, there are some tweaks. So as I said, t-test is a mini version of z-test. So when do we use t-test? So we use t-test when, number one, normal distribution, the underlying distribution is normal. In one of the later lecture series, I will give you a brief overview on what test to use when and what are the conditions. So just now know that t-test works with normal distribution. The same is also applicable for z-test, by the way. So both z-test and t-test work on normal distribution. Here the metric in consideration is mean. So metric in consideration, so we'll be working with mean. There are some non-parametric tests where we will consider median, which will, as I said, show in the later videos. So here metric in consideration is mean. In t-test we do when generally the number of samples is less than 30, and number 4 when the population standard deviation is unknown, is not known, right? However, rest of the concepts are more or less the same. Here also we'll try to calculate something called a t-statistics, the way we were calculating the z-score, and then we will be looking at the p-value, though in a different way. We'll be looking at a critical value and we'll be comparing the calculated value and the critical value, and then we'll make decisions whether we should accept or reject the null hypothesis. So let's look at a problem. Okay, before that, let me also mention the varieties of t-test available. So the main varieties of t-test are one sample t-test, two sample t-test, pair t-test. So let's look at each of these problem one by one. So let's read problem number 8. So let's read the problem first. So it is recommended to walk 10,000 steps per day to be healthy. So when you walk more, you reduce obesity, and that's good for health. And the doctors have prescribed to walk 10,000 steps per day. And these days, as you know, there are a lot of apps, variables through which you can track how many number of steps are you taking per day. So you randomly surveyed 10 people and found that they are taking these many number of steps respectively. So when we look at this particular data, it's like very evident that these people are taking less than 10,000 steps, most of them. Yes, there are some exceptions, but most of them are taking less than 10,000 steps. But can you use this data to infer about the entire population? Can you use the samples which you have taken for 10 people to infer about the entire population and say that the entire population is taking less than 10,000 steps? That is the problem. So here, first things first. So this is a one sample t-test, because what we want to test is if the sample mean, which means sample mean is coming from here. These are the samples which we have taken. If this mean is statistically different from a hypothesized mean. Here, this is not an exact mean. This is not my population mean. This is the hypothesized population mean, right? This is not the exact mean. I do not know, right? How many steps people are taking. We have hypothesized that people are taking these many number of steps, and we want to compare the mean of this group, the mean of samples, versus this hypothesized mean. So this is my hypothesized mean. So looking at these two numbers, can I say that this mean of samples, whatever we are getting, right? And here, mind it, we have worked with only 10 people. And looking at this, can we infer the same about everyone in the population? That's the problem. So let's try to solve it. But before we try to solve it, one question which might be striking you, that it's actually looks very simple, which means if I have to do a survey, I just need 10 people, which means I can talk to my father, I can talk to my mother, I can talk to my sister, I can talk to a couple of friends, couple of colleagues, couple of neighbors. I can collect that data and then infer the same about the entire population. It's actually simple. Why does statisticians take so much of pain in gathering so much of data? It's just 10 people whom we need to talk, and we know more than 10 people, right? That might be coming in your mind. Now, one thing which you need to remember is that these 10 people are randomly surveyed 10 people, which means that it cannot be biased. You cannot say, okay, I am going to pick this person, this person, this person. I know that they are taking 10,000 steps or less than 10,000 steps. I speak to them, I form my hypothesis, I do the testing, and I can give a result. No, because they are not randomly surveyed. You know about them and you are picking up their information. That's not random survey. Random survey means you do not know about that person. Suppose you go stand in front of the road, you just randomly ask people, and that also cannot be from a particular state only or a particular city only. Then you will lose diversification. So it looks very simple that I just talk to 10 people and my work is done. That is not the case. Okay, so now let's try to solve this problem. Let's first see what information do we have in our hand, and then let's try to solve it. So the first information which we have in our hand is a hypothesized population mean. So just for simplification, I say this is my population data. No, this is a hypothesized mean. This is not the real mean. So this is 10,000. So now we'll find sigma. So we come to the problem. We are trying to find a hypothesized sigma, but hold on. This is hypothesized mean. This is not my population data. And in this case, I don't have a standard deviation. And if you remember, I use t-test when my standard deviation of the population is not known. Fair enough. So I do not know this. Let me just put a cross. This is not x, this is a cross. Next thing what we'll do is we will form a alternate hypothesis and a null hypothesis. So my null hypothesis is that it's less than 10,000. My alternate hypothesis is that it is equal to 10,000. Now I do not know the standard deviation. So this is my sample site. So let's write down whatever we have. So we have a mu bar, which is equal to mu, which is equal to 10,000. Then sigma x bar is equal to sigma by square root of n. But unfortunately, in this case, we cannot do this because there is no sigma. I do not know the sigma. Okay, fair enough. Let's look at n, which is equals to 10. And we also need a critical value, which we can call as x, which is also something which we do not have. So let's try to figure these things out one by one. So let's test. So here I have pasted all these numbers. So all the numbers I have copy pasted, and then I am calculating the mean and the standard deviation. As you can see, the mean is 8595 and the standard deviation is 1428.36. So here from the sample I can calculate the standard deviation. I do not need the population standard deviation. So it's possible for me to calculate the standard deviation. So my standard deviation is 1428.36 and the mean is 8595, which is nothing but this x. So if you remember during z test, right? If you remember during z test, this used to be our x, the average in the in the sample site. Here also used to compare it against this average in the sample site. Here we do not have it directly, but we can certainly calculate it from here. So we have the standard deviation and the mean. Either they will be mentioned explicitly, or you can be given data like this and you can calculate the mean and the standard deviation. Now for t-test, we will calculate something called a t-statistic. So the funda is the same, x minus mu bar divided by standard deviation by degrees of freedom. I'll just explain you in a moment what is degrees of freedom, and you get a square root here. Okay, so we'll just pause here and let's just quickly understand what is degrees of freedom. Again, a common mistake which I see between people is they say degrees of freedom is n-1, where n is the number of samples or the population size. That is not correct. In most of the scenarios, it is n-1, but let's understand the concept. Suppose I have 4 numbers. Suppose there are 4, 4, 3 and question mark. Now what I tell you is, I tell you that their average is say 5. Now looking at these details, can you calculate this particular missing number? The answer is yes, we can, and the answer will be 9. So as you can see, knowledge about these three numbers was enough for me to derive the fourth number, as long as I know the average or some metric. Average actually works in most of the scenarios. So in this case, out of 4, knowledge about 3 variables or 3 observations is good enough for me. So in this case, my degrees of freedom is n minus 1. For this particular data, it's n minus 1, where n is the total number of samples. However, is it always n minus 1? Let's take a scenario. Suppose I say I have 4 numbers, 4 question mark, and I tell you that the average is 5, and I also tell you that suppose this is 1, 2, 3, 4. I also tell you that number 3 is equal to number 4. If I tell you these two things, can you calculate these two numbers? The answer is yes, we can. And in this case, the answers are 6, 6. Looking at these two scenarios, right? The answer is 6, 6. So here in this case, as you can see, the degrees of freedom is n minus 2. So not necessarily that it has to be n minus 1. That's the message which you need to take over or take home. Most of the scenarios it will be n minus 1, but not necessary. Here it's n minus 2 because knowledge of n minus 2 variables was good enough for me to derive the next numbers when I know this particular condition. Okay. So now we understand all of these things. Let's just plug the numbers. So x is 8595 minus mu is 10,000 divided by 1428.36, which is my standard deviation, divided by degrees of freedom, square root of degrees of freedom, which means here my n is 10, so 10 minus 1, and that comes to, so let's first calculate the denominator. 1428.36 divided by 3 is 476.12. So this is the denominator, 476.12. Now let's come to the numerator. 8595 minus 10,000 is minus 1405. That divided by 476.1. And we get minus 2.95. So this is my t statistic, and we'll going forward we'll call it as t calculated. You can call it as t calculated. Also, you can call it as t statistic. It's very similar to our z-score. Now, let's find out something called a critical value. So here we have the t table. Now, since this is a one-tailed test, here as you can see, this side is the degrees of freedom. So let's look at the critical value for a one-tailed test. So here my degrees of freedom is 9. So I'll come here, and this is the critical value for degrees of freedom is equal to 9 for a one-tailed test with the significance level of 0.05. So this is my critical value for degrees of freedom 9, significance level 0.05, being it a one-tailed test. So let's note down this value, 1.833. So my t calculated, we had found it to be minus 2.9, and t critical is 1.833. So if we just draw the curve, suppose this is my mean and this is my threshold, which is, since here the way the t table is constructed, it does not take care of the negative values. So whenever we get a positive value, in case we have to work with a negative value, in case here since t calculated is negative, what we'll do is we'll put a negative value here. So this part is my, or this point is my t crit. Now the significance of t crit is that t calculated should be between mu and T-crit. T-crit is the maximum point beyond which I'll reject the null hypothesis. So here, if my T calculated is here, anywhere here, between here and here, if I can find a T calculated say here, then I cannot reject the null hypothesis. If it goes on this side, then I can reject the null hypothesis. This is my cutoff. The moment it crosses this cutoff, you can reject the null hypothesis. So that is the significance of the critical value. It's a cutoff, it's a threshold. So in our case, let's see where we find our value. So this is our T calculated. So as you can see, T calculated is beyond T critical. So in this case, the thumb rule which we will follow is if T calculated is less than T critical, then reject H0. So in my case, H1 was that mu is less than 10,000 and H0 that H0 is mu is equal to 10,000. So in this case, I can comfortably reject the null hypothesis and I can accept the alternate hypothesis. So here I reject the null hypothesis that people are walking 10,000 steps. That hypothesis is rejected, and the hypothesis that people are walking less than 10,000 steps, that particular hypothesis is accepted. So here my hypothesized mean is this, and as you have seen here, so we see that yes, the sample mean which we calculated from here is statistically different from my hypothesized mean. Okay, in this case it's less because it's very evident that they're taking less than 10,000 steps. Now we'll look at a two sample t-test. So this test is significant when we are trying to test the difference between two population means. So let's read the problem. So we have visited two schools. In school A, we randomly surveyed around 30 kids and found that their average IQ is 110 with a standard deviation of 5. In school B, we randomly surveyed 20 kids and found that their average IQ is 115 with a standard deviation of 10. So now we can test the hypothesis that the IQ between the kids in the two schools are not equal. So I have, as you can see here, we test the difference between two population means. So here my two populations are school A and school B. And in school A, I have randomly surveyed 30 kids and I have noted down their average IQ and the standard deviation. I have done the same in school B, where I have randomly surveyed 20 kids and noted their average IQ along with the standard deviation. Now I have to test the hypothesis. The IQ between the kids in the two schools are not equal. So in this case, let's do a two sample t-test. So as you can see here, my null hypothesis is that mu A equals to mu B. Mu A is for school A or group A. Here as you can see, we have two schools. H1 is that the mean are not equal. Now how do I calculate the t statistics or the t calculated? The formula is this. So we take the mean of group A, in this case which is school A. We take the mean of B, in this case which is school B. We take the standard deviation and then we have the number of observations with which we are dealing. So let's just plug it and see what we have. So in school A, we spoke to 30 kids. In school B, we spoke to 20 kids. In school A, the average is 110 with a standard deviation of 5. In school B, it is 115 with a standard deviation of 10. So now let's calculate this step by step. First, I have calculated the numerator, which is mu A minus mu B. So 110 minus 115, that is 5 or minus 5. Then denominator 1 is nothing but this part. This is deno 1, this is deno 2. Then I'll add them, and then I take the square root. So I've done it step by step. So we have calculated numerator. This is the numerator. So denominator 1 is 0.83 sigma square divided by n1. So sigma square, as you can see, I have taken standard deviation square, which is b4, and divided by b2, which is nothing but n1. Similarly, denominator 2, c4 is nothing but my standard deviation square divided by c2, which is the total number of kids we have surveyed. Then I have added these two, which is this part, this addition, and I have taken the square root, and then I have calculated t statistics, which is nothing but numerator divided by the denominator, and we find that t statistics of minus 2.07. So this is my calculated value. Now what is my critical value? If I do a two-tailed test, then my critical value will be this two-tailed test with 0.5 as my p-value, or 95% confidence, whatever you want to say. Here let's see how many records we have actually. So here we are dealing with, here for my bigger case it is n is equal to 30, and here it's n is equal to 20. So in this case both are different. So let's pick n is equal to 20. So here if I look at it, the p-value or the critical value is 2.086 if I pick n is equal to 20. So this is 2.086, this value for n is equal to 20, critical value of 0.05, and I am doing a two-tailed test. So let's take this value. So my critical value is 2.08, and I will put a negative sign, and as we can see that it's like very close, and the t statistics is inside is less than the t critical value. So if I had to draw a graph, if this is my mu and this is my t critical and this is where my t calculated is, very close, it's like neck to neck. So in this case I do not have enough evidence to reject the null hypothesis. In this case I cannot reject the null hypothesis. I hope this is clear. So now we'll move to the last test as far as t-test is concerned, and that is a pair t-test. So we use this test when we are interested in the difference between two variables for the same subject separated by time. Suppose you have studied the score of few students, or say in this case one student, I would say score of a student, pre and post joining a course. Now, assuming that here the data is normal and here also the data is normal, both pre-course and post-course, the question is, do you observe any statistical difference between the scores of the student after joining the course, which means did joining the course help the student or not? So here we are looking at the same subject. The same subject is the student separated by time, pre-course and post-course, and we are interested in the difference between the two variables. So let's put these values in Excel. So here I have put these values in Excel, and the way to calculate the t-test is, first we'll calculate the difference, which is this part. We'll calculate the difference square, which we require here, and then the rest is straightforward. So here what we have done is numerator minus 33, which is nothing but difference. Then denominator 1 is 2457. Let's see what do we have for denominator 1. So denominator 1 is nothing but n, which is this. It is nothing but the count multiplied by summation of d square. So here what we'll do is, so multiplied by summation of d square, which we have got from here, the difference square, minus summation of d square, which is this part. So I take the summation of difference, which is something which I've got here. Then I want to subtract this minus this. So denominator 1 minus denominator 2, and I get this value. Now denominator 3 is this entire expression, the numerator versus the denominator. The numerator in this case is this value. This is my numerator, and this part is my denominator. And then finally I take the square root. After that I calculate the t-statistics divided by numerator and denominator. So that gives me my t-statistic. And here for degrees of freedom 9, we have already seen that the value is 1.833 for one tail test. For two tail test, let's figure out what is the value. This is the value 0.05, 2.26, and the value which we have got is 2.52, so slightly off, which means I can reject the alternate hypothesis, reject the null hypothesis and accept the alternate hypothesis. So that's about paired t-test, where we are pairing for a same subject attributes which are separated over time, pre-test and post-test. The substitute of this test, this paired t-test, we are assuming that this distribution is normal. If this is not normal, then the substitute of this test we'll learn in the later videos. We have something called a Wilcoxon test. So we'll learn about it in the next video. So I hope you have been able to grasp z-test, t-test, hypothesis testing, the formulas, and we have solved 10 problems. So if you like the videos, please like, comment, share, subscribe.
Okay, so I'll just quickly go through the agenda for today. See, we want to revise probability quickly. Okay, so I'm sure we all understand probability, right? So the basic notion of probability, we want to revise it quickly. Then we'll go directly into distributions, both empirical and theoretical. These are two important perspectives of distributions which we need to understand. Right, then we'll talk about random variables. What are random variables? And we'll specifically get into discrete random variables. And then we'll see an example of a discrete distribution, that is the uniform distribution. Okay, and I believe in the TA session that follows this session, you will also look at some other examples of discrete distributions such as Bernoulli. Okay, Bernoulli and binomial. But yeah, so for this session, this is the agenda. Great. So let's quickly revise probability. Okay. Let's start with why probability. See, probability is obviously a mathematical concept. So first, let's talk about mathematics in data science. Now, if you look at data science and machine learning, at the end of the day, if you take a perspective look, right, you sit back and you look at this domain, all of this is working mainly because of the supporting mathematics behind all these algorithms, techniques, and models. Okay, so mathematics is actually the underlying system, or underlying, let's say, ground, okay, on which all of these things work, right? Be it mean, median, mode histograms, visualizations, be it hypothesis testing, be it regression models, machine learning models, neural networks, whatever it is, right? Everything is working because of the underlying mathematics. In a sense, what we are talking about is measurement, right? Mathematics in the sense measurement. So for example, a machine learning model is basically just a system of numbers and operations, both mathematical, right? Mathematical numbers, mathematical operations. And human interpretation is more or less required where? It's required in the first step, it's required in the last step, maybe a little bit here and there in the middle. In fact, in machine learning, it's strictly in the first and the last step. The human interpretation and interference, so to speak, in machine learning is mostly in the first and last step. Okay, so you'll obviously look at machine learning a bit later in the program. So the a model itself just strictly works on numbers and not knowledge. So we need to understand how these numbers work and how we interpret these numbers. Now let's get to a subset of mathematics, which is probability, and why it is used in data science. So see, this is your real world, okay, and you're essentially collecting data, right? So suppose this is data of heights, salaries, number of web page hits, whatever it is per day, things like that. You're accumulating all this data. There is always uncertainty associated with the nature or the value of the data, you can say. For example, if my website today say had a million hits or something like that, tomorrow is it going to be million? Day after is it going to be million? Is it going to be million every day? If it was million every day, then I don't need data science, I don't need machine learning, I don't need to understand probability, nothing, right? If it was just 1 million hits and this is the truth every day, then I don't need any of this. The whole thing is that there are fluctuations in the data values. Are there patterns in these fluctuations? This is where probability comes in, right? So we need to have a strong understanding of probability, which will then allow us to properly analyze this real data, right? Instead of just looking at it without any understanding of why things are behaving a certain way, without any knowledge of, okay, this is a higher probability, this is lower probability. We don't have all this knowledge, suppose, just randomly analyzing, right? That is that gives me less insight. If you want more insights, which is what we want at the end of the day, then we have to also look at the data in terms of how they are distributed in the real world because of all these fluctuations. Okay, so some and of course everywhere we are going to have probability distributions. If you sort of look at data analysis, most data analysis in the industry, right? You'll always have a distribution mentioned somewhere. You'll always have a confidence interval mentioned somewhere, right? You'll always have a confidence percentage mentioned somewhere. It's all probability based. Why? Because there's uncertainties everywhere in market conditions, in the domain of finance, right? Probabilities of accidents and deaths, right? These are also possible things. We need to model them in terms of probabilities. Then only we can understand what kind of insurance plan we should design, right? In transportation, so I'm in Bangalore, so nowadays the probability of traffic is equal to 1. It's pretty bad, but generally speaking, over the course of 24 hours you're going to have a distribution of traffic. It's going to go up and down, right? Same with accidents and things like that. So if you're designing transportation governance rule systems and things like that, then you need to take conscious calls, of what to do when, and things like that. In all of these domains, you have to deal with how data are distributed. Okay, so let's start from the basics. Okay, we'll start from the basics. As I said, all of these concepts and techniques cannot be done in one session. Okay, we'll have to start basic, then we'll go a little bit more advanced, then we'll go a little bit more advanced, right? So it's like layer and layer of understanding. Okay, so we'll start with some terminology, then we'll do some other things. You'll understand discrete distributions, you'll understand expected value and variance, right? Then you'll go to continuous in the next session tomorrow, right? So, and that presupposes that you know this. Okay, so it's easier to go this journey step by step. You may not be able to see the final sort of outcome immediately, but that's the nature of the course. Not the course, maybe the 2 weeks. Okay, probability and inferential stats and hypothesis testing, right? It'll take some time to be able to have all these underlying concepts so that you can immediately use it on a data set. Okay, so we'll start with some terminology. So these are things that we know, right? An experiment is essentially just a repeatable procedure with observable outcomes. So for example, very simple, right? Very simple examples so that we can understand properly. A standard fair die is rolled 10 times and the number that appears is observed. I think this is exactly what you can see here on the right side. These are the numbers that appeared on my die, and I have rolled the die 10 times. That's my experiment. Okay. So the description of the experiment actually depends on the problem statement. I have of course taken a very simple experiment here, right? But when you sort of do on the real data, so you may think about say traffic and things like that. The kind of experiment you do and the kind of thing that you're observing, what are you observing, that will depend on the problem statement. Okay, what is a trial in an experiment? So a single performance of the experiment is what we call a trial. You can call it trial, you can call it observation, anything, right? One experiment is performed here, right? I roll my die 10 times, that is one experiment. But in that experiment, I have n trials. So I have 10 trials in this experiment. So another way of saying that is the size of the experiment. And another way of looking at it is the number of data points in the data set. These are all same thing. Okay. And what is the result? The result is just the result of the trial. So here the result is 2, result is 1, result is 3, and so on. Okay. And one more thing, an experiment may be tried any number of times. So nobody is saying stop at 10, right? You can go on and on. It can be tried any number of times. Hence, we have the term trials. Okay, these are the basic terms. Now, some terms on top of that. What is an outcome as opposed to a trial? An outcome is essentially a possible result. So you're converting this list of results into a set. Okay, if you see the outcome, which is the possible result or possible outcomes, there are only 6, right? If you're talking about rolling the die, right? If you're talking about rolling the die, there are only 6 possible results. That's 1, 2, 3, 4, 5, 6. This is what we know as outcome. So here in this experiment, I have 10 trials, I have 10 results, but I have only 6 possible outcomes. Okay. Now, what is the sample space? I hope we all remember this, right? Sample space is the set of all possible outcomes. So you just put all these outcomes into a set, you get your sample space. And the size of the sample space in this case is 6. Okay. Compare this with this size of experiment. Same experiment. Okay. This I went to the previous slide. The size of the experiment is 10. There are 10 trials, right? But the size of the sample space is 6. So keep that in mind. This will become important a little later. What is an event then finally? An event is essentially a subset of this sample space. So you have many types of events. Okay, you can have elementary event, you can have compound event, so on and so forth, right? So you could have the event that the number 1 appears, you could have the event that even number appears when you roll the die. So in this case, it's just 1 element. In this case, it is 3 elements, so on and so forth. Okay. Of course, all possible events may not be of interest in the real world. When you design your experiment and you collect data for that, and when you define the events, you need to look at important events which are important to your problem statement, right? All the events may not be of interest. Now, finally, I just want to close this terminology bit with this part. Mutually exclusive and exhaustive events. Again, it's just revision. So mutually exclusive events cannot occur simultaneously, right? So 1 and 2 cannot occur, 1, 2, and 3 cannot occur. Of course, this is a very simple example, but these are events which if one occurs, the other cannot occur. And what is an exhaustive event? An exhaustive event is something, if you put those events together, it needs to make up the sample space. So here you have 1, 2, 3, here you have 4, 5, 6. If you put it together, you will get 1, 2, 3, 4, 5, 6. Same way here you have 1, 2, 3, 4, 5, and 6. If you put these 6 together, you will get the sample space. And what is the set of events which is both mutually exclusive and exhaustive? So that would be the elementary events. Okay. Any 2 events from this set, of course, they will be mutually exclusive, and all elements together in this list of events will be exhaustive. You will get your sample space. In this session, yes, Priyanka, I'll go a little slow, sure. In this session, we will focus on elementary events. Okay, so there's no need to worry about the terminology difference in, one might be called an event, elementary event, outcome, possible outcome, right? The if I have to summarize this, there's a very easy way to summarize this. If you see the number 1 just written like this, then we are talking about outcome. Okay. If you see the number 1 written inside curly brackets, then we are talking about event. It's a very, very small distinction. But why is this distinction there? Because elementary events are not the only kind of events. In the die example, all the outcomes are mutually exclusive, right? But what happens if you define your event as even? So I went to the previous slide, you can see here it says even, right? So then the question comes, are you rolling the die once or thrice? Now if you're doing once, then you have to do what? The two so you have 1 2 3 4 5 6 in your sample space, right? So then you're counting how many times we have 2, how many times we have 4, how many times we have 6, and then you're adding those addition. So things get little bit more complicated in probability when you deal with events which are not elementary. But for this session and for understanding how probability is used in data science, I feel that we should focus on the elementary events. So you don't need to worry about this difference, this curly bracket, you don't need to worry about it. So let's move on to the main track now. Okay, so from now on, from this point onwards, we will focus on all the concepts and techniques that we need to understand, so that we can take this knowledge ahead to the next sessions, to the next week, and so that when you encounter things like hypothesis tests, that time we should be fully aware what we are talking about. What is the distribution? Why does the variance matter? All sorts of things, right? So let's start with the most important concept in data science, probability, whatever it is. This is exactly what we are analyzing. Okay, frequency. Frequency is essentially the number of times an event occurred experiment. I would request everyone to look at the rightmost column, the result column. So this is the experiment where I rolled a die 10 times. So you can see 10 observations, 2 1 3 1 6 6 whatever, right? You can of course convert this into a frequency table, right? Now the events here are what? Number 1, number 2, number 3, number 4, number 5, number 6, and the frequency with which these events occur is what I have jotted down here, 3 1 2 1 1 2. Okay, so the number of times an event occurred within an experiment, and the way that generally we write in mathematics is n of 1 equal to 3, n of 2 equal to 1, so on and so forth. Okay, simple. For mutually exclusive exhaustive events, the sum of the size of each event will be equal to the size of the experiment. Okay, this is also obvious. 3 plus 1 plus 2 plus 1 plus 1 plus 2 should be equal to 10, because where did these numbers even come from? They came from you counting, right? You counted from the result, so you got these numbers. Great. What's a frequency distribution? Now see, the word frequency distribution, most people think we are talking about this diagram. Technically speaking, we are talking about some kind of a function. Okay, technically what we are talking about is we're talking about a map. So if you see in mathematics, the word function can also be interchanged with the word mapping. Okay, those who have maybe remember some of these functions are also called maps in mathematics. So when we say frequency distribution, we are essentially talking about a map between the event and the frequency. Okay, this map you can show in the form of a diagram. Visually, of course, all of us will understand better, including me, right? Everyone will appreciate better if you visualize and understand these things. But we should not forget that actually frequency distribution means what? It's actually a mapping. It's actually a function. Okay, what it does? F of event equal to frequency, basically. Okay, great. So for this experiment, you can see the frequency distribution here on the left side. 1 has a frequency of 3, 2 has a frequency of 1, 3 has a frequency of 2, 4 has a frequency of 1, and so on. Okay, we'll come back to this a bit later. Now, before we move further, we will look at definitions of probability. Since probability itself is not the most, how shall I put it, it's not the most easily interpretable thing. Okay, probability is a very enigmatic thing, right? So many people have tried to define in many ways, right? So there are 4 very common types of definitions of probability which is followed all around the world. Okay, and the first is the empirical or the experimental. Basically what it's trying to say, perform an experiment. Okay, you perform the experiment and you use the frequency distribution that emerges from your experiment. Classical or theoretical is the definition where you define an experiment, okay, and then you basically assume your sample space. You don't need to worry too much about this statement. What I'm trying to say here is sample space needs to be defined. Once you define the experiment and define the sample space, you create the probability distribution from that. This is theoretical. Okay, so this is basically in school, math teachers would have told Shubham, Karan, Naga, Sai that this is a sample space, calculate the probability. And Shubham, Karan, Naga, Sai, all of you got the same probability. Why? Because you derived all those probabilities from the theoretical definition of probability. Okay. Subjective probability. Subjective is kind of niche. It's not very actively used, but nowadays it is being more and more used. It is the measure of belief of a person. So think about surveys, think about polls, think about the end poll, right? After this session, you will be giving your feedback and things like that. That's a subjective definition of probability. And then in academic circles, where rigorous research happens, rigorous mathematical research happens, most mathematicians just combine all the 3 previous ones. They combine this, and this, and then they use something called the axiomatic approach. This is purely mathematical. And in this session, we will be looking at empirical and theoretical, and this will help us, set our foundations on how to use data to make conclusions about populations and things like that, right? These are the 2 things that we need. So I've written title here as relative frequency because that is what probability is. Okay, I want everyone to internalize that there is no difference between frequency and probability. Okay, frequency sounds like a very friendly word, frequency, number of things, very nice, right? It sounds like a friendly word. Probability sounds like some sort of a dangerous word. Oh, probability, very difficult. They are the same thing, right? In the empirical case, what you're doing, you can just read this out loud. I performed the experiment n times. I saw the event E occur n of E times. So experiment could be 10 times, event E occurred 2 times, for example. So the probability of event E according to my experiment is what? 2 by 10. Simple. That's all. This is what empirical probability is. What about theoretical probability? You can read this. I haven't performed the experiment even once, but I know how the probabilities of my elementary events are distributed. Question is, how do you know? So there are a lot of assumptions. Okay, according to my assumptions. So according to my assumptions, probability of the event E, maybe it is 3 by 10. I don't know. Of course, here the question is, where do these assumptions come from? Without doing the experiment, how do you know the probability? But of course, here you will refer to things like intuition, right? Physics, things like that. I'm sure all of us have had discussions with our peers, friends, family members, that when you roll a die, why is it that we assume that 1, 2, 3, 4, 5, 6 have the same chance of occurring? Why, right? So I'm sure all of us would have discussed this. Okay, physics, from the point of view of physics, there's nothing differentiating the 1 side from the 2 side, right? Or maybe some of us said 2 side has 2 dots, more ink, so it should go down more, so its probability should be less, right? Things like that. Anyway, in theoretical, there are a lot of assumptions that you're making. Okay. The whole point of today's session will be to connect these two realistically. Okay. Not just connect in the sense this is point 2, this is point 3, be happy, both are equal. No. We will connect this realistically, and in the next session tomorrow we will import this to continuous distributions, continuous variables, which are lot of the variables floating around, right? Height, salary, traffic, whatever. Of course, traffic I think is discrete with number of vehicles, but a lot of things are continuous, right? We'll connect those, and then once all of this connection is made and we fully understand how this thing works, then you will start with sampling and then hypothesis tests, things like that. Okay, so for that we need strong base in this. So empirical versus theoretical probability, this is our discussion. Now if you see on the left hand side I have a table, and again this is just the rolling of the die. I don't know how many times I rolled it here. You can check the denominator here, it says 50. So I rolled the die 50 times. As you can see, this is the actual collection of the results from the experiment. Okay. In the theoretical case, what the table is just the sample space, and sample space is a set. Sample space is a set. You see these frequencies 1 1 1 1 1. These frequencies cannot be anything but 1, because our assumption is that the numbers on a die have the same chance of occurring. So all the frequencies will be reduced to the same frequency, right? And then if you want, for example, probability of 2, you will say, okay, 2 is 1 out of 6, right? So this is how you calculate 1 divided by 1 plus 1 plus 1, 1 out of 6. And I get 0.17. This is theoretical. In the empirical case, if you want P of 2, you need to go back and see in your experiment how many times did 2 occur. It occurred 9 times. And how many times did you throw the die? 50. So 9 by 50 is 0.18. Well, of course, they look similar, 0.18, 0.17. But then I told you, I would like to convince the audience today that it's not just coincidence that you're getting, equal. There is some kind of law at work. Now, how do we really interpret probability, generally speaking, right? What is the interpretation of this thing? So, so obviously I am taking this session for an audience who is well versed, with these concepts and the real world and day to day whatever we do in our work, right? So when I used to teach, let's say college kids, younger kids, right? That time I used to tell them that there is no interpretation to probability, because that's all I could tell them, right? They wouldn't understand the implications of this, right? But now we are here, right? So what is the interpretation of probability? See, most people say it is measure of likelihood, this is kind of textbook definition, right? Measure of likelihood of occurrence of event. Okay. Honestly, to me also, what does it mean, right? It's honestly not very useful if the number of trials is low, right? So it's like this. If somebody did an experiment for 10,000 times and they got some probability of 0.6, they say, oh, 0.6 is greater than 0.5. It's a positive probability. You perform your experiment once, you will get the result. No, right? That's not how probability works. Probability, if you want to interpret, you have to think in terms of large numbers. You actually have to think in terms of large numbers, right? So consider this case of, coin toss with increasing number of trials. So here I have 1 trial, 5 trials, 10 trials, so on and so forth. I'm also recording the number of heads, number of tails each time, and therefore you can get the probability, right? Just divide by the total. What you will see is some kind of fluctuation, right? Initially it will fluctuate 1.4, whatever, and then it will slowly come down to 0.5. Same thing for the tail probability also. It will fluctuate, and then it will come to 0.5. So you need to do this experiment so many times, then only you will observe similar results, right? And this is true. If I have to translate this into, for example, business language, just because I sold one product, I cannot make a comment on whether it was profitable or not, whether the project was profitable or not, whether the enterprise was profitable or not. I cannot comment. I need to sell thousands and thousands, maybe even hundreds of thousands of the product, and then I have to see in terms of probability analysis was or will it be profitable, will it not be profitable. All of this has to be done not in terms of selling one product, right? You have to sell multiple, and all of that, whether to sell, how to sell, what is the selling price, what's the price point, all of that you need to do proper probability analysis, right? So large numbers, keep that in mind, large numbers. Which takes us to, empirical and theoretical distributions. How do we connect these two things? First of all, what's a probability distribution? So just recall this dice experiment in which I, rolled the die 10 times. These are the events, these are the frequencies. I have my frequency distribution here. Great. All I have to do now is divide by 10, correct? I just need to divide by 10 all of these frequencies. So how do you compute probabilities empirically? Just divide by the total. So you convert the frequencies into probabilities. 3 by 10 becomes 0.3, 1 by 10 becomes 0.1, so on. And your distribution is going to look like this. This is a probability distribution. Okay, more or less the same thing. I guess all of us right now are thinking it's the same thing. Yes, more or less it's the same thing. Correct. So in terms of empirical methods, frequency distribution and probability distribution will be the same thing. Okay, they are the same thing, more or less. So if you can see, the two shapes also look similar. You just scaled it down by a factor of 10. How do we move from this empirical to theoretical? Okay, so this is a question to the audience again. I guess this is my 10 size 10 experiment rolling die. So this is n equal to 10, I think. My question to you is, just imagine if n is infinity. What do you think will happen to this probability distribution? Will it retain the same shape that you're seeing here? You may put your answers in the chat. So this is me rolling a die infinite times. And for the sake of, for those who are realists here, suppose 1 million times. Okay, I roll my die 1 million times. So just imagine that after rolling it so many times, yes, what's going to happen is it's going to become flat. Now you can try it out, right? All of us do have this intuition. As I said, when we roll a die, our assumption, our internal assumption says each of those events, 1, 2, 3, 4, 5, 6, they are equiprobable. There is nothing special about 2 or 1 that it should occur more number of times. That is what we would call a biased die or a loaded die. Okay, this is a standard die, normal die. So point is, when your number of trials is less, okay, you cannot make too many conclusions about your experiment. Not possible. You need to have a large number of trials, and if you do increase your number of trials a large number of times, you will see that this specific experiment, it's going to become a flat line, as Palash said, as Subodip said. And essentially speaking, every empirical distribution is actually an imperfect copy of the same theoretical distribution. Now this theoretical distribution, which we will study at the end of the session, this is called the uniform discrete distribution. Okay, uniform, which means all the events have the same probability. What is the example of uniform? Throwing a die or tossing a coin, right? These are all uniform. In fact, if I told the audience right now to choose a number between 0 and 9 and put it in the chat, and I get those numbers and I make a distribution, that is also uniform distribution. Why? Because there's nothing special about number 3 that Subodip likes number 3 so much he'll keep putting 333, right? Or say, in general, the class has, I think, 27 people. Yeah, we have 27 people. So there's nothing special about the number 3 that out of 27 people, 7 people go for 3, 20 people go for 3. Nothing special about the number 3. So if I told the audience right now, choose a number between 0 and 9, I will generally see a kind of, flattish, this kind of thing. And if we had more audience, if we say 100 or 1000 audience, then it will more or less settle in this. Okay, this is what we call a uniform distribution. So the empirical distribution is an imperfect copy of the uniform distribution. Notice how the tables have turned. Okay, initially we said theoretical distribution, assumptions, no real substance there, right? But if you keep doing the experiment many times, you will see that the empirical one goes to the theoretical one. There's a very strong connection there, right? So theoretical probabilities can be estimated by performing the actual empirical event multiple times. Okay, now why is this important? Why exactly is this connection important? See, once a type of experiment has been performed and performed enough number of times, and you have a resulting distribution which has been studied and verified, you don't need to perform the same experiment ever again. Okay, people in the past have done this, right? They have rolled a lot of dice, they've tossed many coins, and they've done all sorts of experiments just to verify, okay, that are these things matching with the theoretical claims, and they do. Okay, and that's quite an interesting point. It's not practical to build frequency tables when you have large populations of data. It's just not practical, right? For each experiment, you might be dealing with what, 10,000, 100,000 data points. So for each one, counting each time, and then making a frequency table, all of that, unnecessary. As long as you make some safe assumptions about the population, then this connection between this empirical theoretical, which is what, n approaches infinity, right? Which means if you have enough sample size, if you have enough population size, then you can make safe assumptions and you can completely ignore the empirical distribution. You can directly work with theoretical distributions. There are, of course, even more advantages, which we will deal in the next session tomorrow. Okay, as I said, all these things cannot be covered in, it's kind of a wide subject, right? So we'll again touch this point when we do continuous distributions, as I'm saying here, which is what I've said in this bullet point. I think this becomes even more important in the case of continuous distributions, right? You cannot keep collecting data about continuous variable till its distribution is good enough. For example, if I ask you, can you tell me generally what are the probabilities of human height, right? Heights of humans, right? Can anyone in this audience let me know what is the mean height, let's say, of Indian people? That you can Google and find out. But if I told you, you should find out, not Google, then just imagine how hard that is. Okay, just the mean. Then if I ask you, find me the probabilities of each of those things. Find me the probability of 168.2 centimeter. Find me the probability of 161.4 centimeter. Can you imagine the kind of data that you have to work with? So when you're dealing with large populations, there are certain techniques that are used in data science, which allows you to skip collecting and working with the data of the population. This is exactly what we call inferential statistics. Okay, and what we are studying now, which is the connection between this empirical theoretical, this allows us to perform this thing that we call inferential statistics, where we make certain safe assumptions about the population and about the distribution, and then we are able to do meaningful experiments. Okay, anyway, we will deal with that. Right, so let's move on to discrete random variables. Okay, so till now we've understood probability, we've understood probability distributions, which is essentially map between the outcome or the event and the probability of that event. And we also had a discussion around empirical distributions and theoretical distributions, and we also concluded that if you perform this empirical the experiment enough number of times, then the probability numbers that you get, they will start to flat out. At least in the case of the rolling of the die, it will flat out. Of course, other variables need not be uniformly distributed. There are many types of distributions, and in the next session we'll see other types of distributions. But the point is that there is there seems to be some kind of a connection if you perform an experiment enough number of times, and if you get the theoretical probability using assumptions, whatever logic, right? There seems to be a connection there. Okay, so this is what we've studied till now. What are random variables? Okay, now again we've heard this word many times, random variable, right? So let's get into it. What I would like to say though is it's not necessarily a new thing. See, a lot of the things that we are going through now in the discussion of probability distributions, right? It's just new terminology for the same thing. So a random variable is essentially a quantity or a variable whose probability of occurrence can be associated with a probability distribution, essentially the x-axis. Okay, if long story short, what we are talking about is the x-axis, right? Now, in the simple case, you will call it event, outcome, so on and so forth. In mathematics, we try to generalize and we call it a random variable. So for example, in the experiment of rolling a die and observing the number that comes up, the RV is the number that comes up because that is what you're observing. Okay, then next one, toss a coin, observe what symbol comes up. The random variable is the symbol that comes up. And suppose we have an experiment where you choose a person at random and record their height, right? Here the random variable is the person's height. So random variable is essentially the thing that you're measuring in an experiment, right? Now there are two kinds of random variables, discrete and continuous. Discrete will take exactly one value out of exactly some finite number of possible values, right? Continuous random variables may take any numerical value. So example of discrete is number on the die. Okay, number on the die. This can be 1, 2, 3, 4, 5, 6. Example of continuous, many real variables are continuous. You know, height, salary, anything, weight of baby, weights of babies, all of these can take any numerical value. Now, the first session is on discrete for a reason. Okay, we could have started with continuous, right? I could have easily just started with heights, continuous distributions, formulae, integration, whatever, right? I could have, but I feel that if we understand certain concepts using discrete, it is easy to understand those when you go to continuous. The math in the continuous is a little bit more complex, right? So sometimes we lose out on the ability to understand what's going on. So it's always better to start off with discrete and then move to continuous. Okay, so again, new terminology, PMF, right? PMF. So why so much terminology? That's kind of the way it is. You know, as I said, you might be seeing a slide in front of you called PMF, probability mass function, as if it's something new, but it's not. It's not something new. Okay, so initially this is what we had. You rolled your die 10 times. These are the possible events, 1, 2, 3, 4, 5, 6. These were the frequencies you recorded, 3, 1, 2, 1, 1, 2. When you performed the experiment 10 times, you converted the frequency to probability. Now, if you see on the right side, you have the exact same numbers. Okay, these are exact same numbers. So here 1, 2, 3, 4, 5, 6. Here you have 1, 2, 3, 4, 5, 6. Here you have the probabilities, 3 by 10, 1 by 10. Here also you have the probabilities, 3 by 10, 1 by 10. So the only difference is now we are saying, instead of looking at each event as a separate event, rather we are looking at each event as a value of a variable. If you remember in the beginning of the session, I told you that essentially these distributions are functions, right? These are functions, and in the full mathematical sense of the word, right? If we remember relation, function, and all of that stuff from school, these are actually functions. So we say that there is a variable x who takes these values 1, 2, 3, 4, 5, 6, who takes these values, and we associate a probability of having those values. So x and p of x. Essentially what you've done is informal, you moved from informal to formal. That's all. You moved from informal to formal. Now the reason for this is we want to do a lot of computations, right? We cannot keep talking in informal terms each time. So to formalize and universalize all of these things, we use this notion of probability mass function, which is a function, and we use this notion of random variable. Okay. So I'm showing here a PMF for an empirical distribution or empirical case. Generally speaking, people directly use the concept of x and p of x with continuous case. Okay, so I'm just showing it for empirical for the sake of understanding. Generally, when you see random variables, they are associated with theoretical distributions, okay, not with empirical distributions. Okay, so the empirical one is, sorry, 1 second. Yeah, so what did we do? We essentially went from event and probability. We went from event and probability to random variable, okay, x, and its probability mass function p of x, okay. And as you can see, the tables are essentially the same. The only reason we did this is because we want to do computations. All right, so now you know what, let's actually put all of this into action, and we'll take up a simple experiment and we'll try to investigate it. Okay, see, suppose that a biased coin was confiscated from a gambling house. Okay, now the gambling house obviously allows for gambling, right? The game that was being played using this coin was a very basic coin toss game. Okay, if a player gets a head, they win $10 from the gambling house, but if the player gets a tail, they will lose $5 to the gambling house. Okay, now on the surface, this is the information that the public has, correct? This is the information that the public has. If I win this game, wherein I'm just tossing one coin, if I win the game, I will get $10. If I lose the game, I will lose $5 to the gambling house. Okay, so on the surface, this looks profitable. This looks good for me, right? Heads equal to $10, tails equal to lose $5. This looks good for me. Now, the gambling house was suspected that, okay, there was some suspicion that something's going wrong here. So this coin was confiscated, okay, say by some authorities. What they did was they tossed the coin sufficiently large number of times in a controlled environment. Sufficiently large, please imagine 10,000, 100,000 number of times. Okay. Now, ideally, if you do that, one might expect that your probabilities for head and tail should come 50-50 or at least near 50-50. But it was found out that the head probability is 0.2 and the tail probability is 0.8. Okay, which means the coin is biased or unfair. Now, of course, a coin in a gambling house is going to be biased or unfair, but just how much bias, how biased or unfair, that's what we are trying to look at. Okay, so the gambling house is justifying this biased coin, saying that winning amount is larger. They are saying, okay, winning amount is $10, losing amount is $5. Why do you have a problem? That is how the gambling house is justifying. So how are you going to tackle the gambling house? How are you going to go and say, no, this is not fair, or there is a problem here, right? You have to speak in the language of numbers. First of all, let's convert this situation into a mathematical model. Can we define a random variable and describe a distribution for this case? Yes, we can. Okay. So the event is essentially getting a head, getting a tail. The random variable is the value we are interested in. Now, the game says what? If you get a head, then you will gain $10. So that's plus $10. Okay. If you get a tail, you will lose $5. So this is minus $5. This is the random variable in this game or experiment. The amount of money, okay, going from the user or the player. So in the head case, the player gets $10. In the tails case, you will lose $5. So this is our random variable x. What is the probability mass function for this x? For heads, we know that the theoretical probability. Note that I've written here sufficiently large number of times we have tested this coin and we have observed p of h equal to 0.2 and p of tails equal to 0.8. So these are theoretical probabilities. Okay. So for the head, it is 0.2. That is 1 out of 5 times, right? And for tails, it is 0.8, 4 out of 5 times. This is your distribution. This x and p of x combination is the complete distribution for this case. Okay. plus $10 with a probability of 0.2 minus $5 with a probability of 0.8. Great. Now, how do we start analyzing this, right? How do we say 0.2 is bad, 0.8 is bad, this is good? How do you even start talking about these things? What is the language? So there are certain things, certain metrics that we should be familiar with, and this will become more important as we go deeper into inferential stats and things like that. Let's start with expected value. Okay, so suppose I'm asking the question, is the gambling house looting the public? Okay, one way to find out is empirically. You play the game a lot of times using a lot of players, right? Now what we can do is we can create a team of undercover investigators, say 10 people, right? 10 people from the authorities undercover, and you just send them to the gambling house, tell them to play the game for a large period of time, many games. Tell them to play many games and then see what happens. So from this we will be able to see out of the 10 investigators how many were able to win money, what is the distribution of how, are people winning, losing. One way to do that is just go and do it many times. So suppose we have these results from one investigator. Okay, so we know that our random variable is this plus $10 minus $5, and this investigator played 100 games. Okay, suppose this investigator played 100 games. So here you have frequency. The investigator won $10 25 times, and the investigator lost $5 75 times. What is the total loss or profit of the investigator? That's the first statement here. It's very simple. If I gain $10 25 times and then lose $5 75 times, that's just 25 into 10 plus 75 into minus 5. Just multiply and add. Answer is minus 125. Totally, this investigator lost minus $125. What is the average loss? So how many games did the investigator play? 100 games. So minus 125 divided by 100, right? 25 plus 25. So you're getting minus 1.25. So on an average, this investigator is losing minus $1.25 per game. Minus $1.25 per game. Okay, my dollar sign, yeah, minus $1.25 per game. I've only used the frequencies. The point is that you can convert the frequency into probabilities. So you know that your experiment size is 100. We've already studied before how to get probability from this. So 25 divided by 100 is 0.25. 75 divided by 100 is 0.75. So the same equation, if I just divide it by 100 everywhere, if I just divide by 100, you will get the same answer. You will get minus 1.25. So instead of frequency, you can use probability, right? So if you see in the last equation, I am using the probability 25 by 100 into $10 plus 75 by 100 into minus $5. That's essentially 0.25 into 10 plus 0.75 into minus 5, which is 2.5 minus 3.75, and you will get minus 1.25. So you can directly use the probabilities with the value of the random variable to find out on average how much the investigator is winning or losing. So this investigator is losing $1.25 per game. Suppose we have results from other investigators. Now, as you can see, this investigator played 200 games, which is why the frequency is 40 plus 160 is 200. This investigator played 1000 games, 180 games, 820 games. So you can just convert these things to probabilities. 40 by 200 is 0.2, and 160 by 200 is 0.8. 180 by 1000 is 0.18, and 820 by 1000 is 0.82. Then you use the probability values, right? So P of X, you use that. Where is that? 0.2. 0.2 is my probability of what? Of winning $10. So 0.2 into 10 plus 0.8, which is the probability of losing $5, which is into minus 5. So this investigator is losing $2 per game on average. This investigator is losing $2.3 per game. So this is one way that you can try to make a case, right? One way that you can gather evidence and proof, which, the gambling house will be forced to look at. If all 10 of your investigators, even after playing 1000 games, say 10,000 games, on average, if they are losing 2.3 dollars per game, then you can go to the gambling house for that. But we want to be more efficient. The whole point is we want to be more efficient. We don't want to send investigators, and do this 1,000 times and things like that, right? We don't want to go around the whole country trying to gather the data of everyone just so I should, build a product, right? We want to be efficient about this. So what did we do? If you remember initially, these probabilities 0.2 and 0.8, we estimated that these are the theoretical probabilities of tossing the coin. How did we do that? We just tossed the coin n number of times. Rather than having somebody go and play the game, we just took the coin and we tossed it a large number of times. From that, we estimated the theoretical probabilities to be 0.2 and 0.8 for winning and losing respectively. This is where the notion of expected value comes in. Okay. Expected value is nothing but the same process that you have been doing till now. All of these calculations are averages, right? Expected value is when you use the theoretical probability and not the empirical probability. In these cases, you were using exactly the probability values that you got from the investigator who went out there, really went out there. These 1000 games really happened, and you have 1000 data points, on a sheet, on a sheet of paper or whatever, right? You have real data here, right? Investigators went out there. In this case, in the expected value case, investigators are not going anywhere. You just take the coin, estimate the theoretical probabilities. You know the rules of the game, right? $10 if you win, $5 if you lose. And all you do is you plug the same formula. If you see the formula here, X, this is the value. So $10, $5, these are the X values, and the probability of such X value occurring, theoretical probability. Generally, people shorten it down to this sigma x p of x. And in this case, E of x is what? 0.2 times 10 plus 0.8 times minus 5, which gives me minus 2. Now, if you see all the empirical values, here I have minus 2 as a value, here I have minus 2.3 as a value, and the first investigator has minus 1.25 as a value. All of these are close to this number, and essentially the claim is that the closer the empirical probabilities get to the theoretical probabilities. When will that happen? That will happen when your experiment size is larger and larger and larger. So the first guy, the experiment size was only 100, right? The second person 200, the third person 1000. If the number of times that a person plays goes to 10,000, 100,000, then your empirical probabilities, these values, here you have 0.18, 0.12, these empirical probabilities will get closer to the theoretical probabilities. And the moment that happens, what will happen? The averages that you are calculating here will actually be much, much closer to the expected value. That is the theoretical expectation. It will be very close. This is what we call in mathematics and specifically in data science, this is what we call the law of large numbers. Expected value in which you are using theoretical probability is getting close to the mean, which is the real average, right? These two will join. When will that happen? When n tends to infinity. Okay, so essentially, instead of going and investigating using investigators, I can replace that whole process with the theoretical probabilities. I don't need to send anyone anywhere, and I have a value in my hand. So through these calculations, I can say, hey, look, the expected value of any person playing the game is minus 2. That means, conceptually speaking, if anyone plays this game for a large number of times in the gambling house, they will lose $2 per game average, right? And that may not even be sufficient. That may not even be close to the price of the game. Maybe the price of the game is much less. Why should you be losing $2 for each game, right? So expected value is the general or the long-term experiment. The key difference The key difference, I want the audience to understand, the key difference is the probabilities that you're using here are different. Okay, these are empirical probabilities. You went out, you did the experiment, you got the frequency, you divided by the total. That's how you got 0.18, 0.82. That is different from these two. These two are not the probabilities of the game. These are the probabilities of the coin. You estimated these, right? And you're using this for any game, any future game, you're using the same probability, 0.2, 0.8. Okay, that's the difference. I hope that part is clear. Here, if you see the P of X values, it's not 0.2, 0.8. Okay, not at all. Because for each investigator, the number of games they played, how many times they win and lose will be different, or the proportions will be different. But here, we are directly using the theoretical probabilities, which you just toss the coin, say 10,000 times, and you get very close to the theoretical estimate, and therefore you don't need to play the game as such. Now see, there is strong proof and strong mathematical justification is there, okay, for this stuff, law of large numbers and things like that, but that's more or less out of scope of the sessions. So if those who are interested can go check it out. But a word of caution is there will be a lot of mathematical language, sigma and all of that stuff. But as long as we all agree, okay, if I perform an experiment large number of times, then the empirical probabilities which I calculate from each distribution, all of those will get very close to the theoretical probability. If we understand this concept, then we are good to go. This is called the law of large numbers. Okay, so the data shows that the game is designed to make money from the public in general. Okay, this is fair. This is fair because of course the gambling house is offering the gaming services, right? They are letting you sit down, play a game, blah blah blah. So this is fair. Now the question is, okay, even if we say it's fair, there is something that we can also, there's another layer of in the case that we can add. We'll get to that soon. Before that, one thing I would like to reiterate, note that if you have the theoretical probabilities, there's no need to conduct all these experiments with the investigators. All of these things are not required. This saves a lot of time, a lot of resources, and essentially you're speaking about large populations in a meaningful way. You're making predictions about the future, okay, expected value. Now, variance and standard deviation. This is another thing that everyone has encountered, right? What exactly is variance, standard deviation? Now again, let's ask this question. Is the gambling house looting the public? See, if the results experienced by different people who play the game are varied, right? Some lose, some win, some lose less money, some lose more money, so on and so forth. Then people are less likely to feel that they're being cheated, correct? It's supposed to be a random thing. A gambling activity such as these, or a gambling game, should be random in the outcomes. On the other hand, if everyone who plays the game even for a small amount of time ends up losing similar amount of money, this is what we saw, minus 1.25 average, minus 2.3 average, minus 2 average, and theoretically the answer was minus 2, right? Then it's quite apparent that there is some mischief going on, right? If everybody is losing similar amount of money, then there is some mischief going on. Essentially, a high variability in the results is generally expected from a gambling game, not consistent results. Okay. Again, see, we can do this investigation empirically, but as stated earlier, theoretical methods save us time, right? So we'll directly use the theoretical distribution. And what is the theoretical distribution? This much. This is your theoretical distribution, correct? These probabilities were estimated by just throwing the coin infinite number of times or sufficient number of times. Then the same probability will be used for the winning and losing values. This is your theoretical distribution. We also calculated the mean already, not mean, sorry, expected value. But of course, mean and expected value become the same for large number of experiments. Anyway, expected value is minus 2. What is variance? So the formula for variance is pretty simple. You find the deviations from the mean or the expected value of the actual value, right? So this is plus $10. This is a win of $10, right? And the average expectation is losing $2. What is the difference? 10 minus minus 2, that is 12. Okay. Here the value is losing of $5 minus $5, and the mean is of course -2, or the expected value is -$2. What is the difference? The difference is -3. And then you square these two. So 12 square is 144, minus 3 square is 9. The squaring is done to remove the negative sign, so on and so forth. Okay. So once you have these delta x square, that is the deviation square, variance is nothing but the expected value of the square deviations. That's all. It is the expected value of the deviations. In a very, very basic sense, it is the average deviation, you can say. It's kind of like the average deviation from the mean. This allows you to define something called variance. Now see, when you say deviation, you have to deviate from something. That's why the mean is involved. Why is it x minus e of x? It could be x minus anything. It could be $10 as compared to $100, but $100 is a random number, right? It makes sense to compare the actual random variable values and how much they deviate from the expected value. It makes sense. This is why they are called deviations from the expected value, deviation from the mean. Okay, so you're finding the expected value of the square deviations. So this is expectation on top of expectation. Yeah. Okay, so again is the same formula. What is the probability of a certain value of $10? What is the probability? Multiply that with the square deviations, 144. So in this case, the variance is what? 0.2 for winning, right? And the deviation square in that case is 144. 0.8 for losing, and the square deviation is 9. And you calculate all of this, you will get some number 36. Now, not to worry too much about this number 36 right now. Okay, I will of course comment a little bit on how to interpret this in this case, but as we go on to the continuous distributions and things like that, this will become even more clear. And in fact, when n of s is larger, this kind of I've written on the bottom of the screen. The key takeaway here, or the key observation, what we want to remember is, technically speaking, higher variance means that the results are more scattered away from the mean. Okay, so in this case, our expected value or the mean, that is -2. Higher variance means that whatever results you have are scattered away from this -2. Lower variance means that the results will be close. So when you perform this experiment, right, again I'll take the last three names I can see: Ashutosh, Nagasai, Shubham. When you perform this gambling experiment, say 100 times, 200 times, 500 times, if this experiment had a lower variance, right, then Shubham, Nagasai, Ashutosh will see similar results. If the experiment had a higher variance, then you will be seeing different results. Okay, this is the importance of variance. And let's look at the comparison, right? So if you see here, what I have done is I have only changed this. This is the default case. This is new 0.5, 0.5, and this is another case 0.3, 0.7. Everything else is the same. The event and the winning losing value, all of that is the same. In the first case, we know the mean or the expected value is -2. We know variance is 36. Okay. What if I change the probability to 0.5, 0.5, right? Somebody might say, why is the coin even loaded? Why don't we use a normal coin? Okay. So if I use a normal coin, 0.5, 0.5, then the expected value becomes 2.5 and the variance actually becomes higher, 56.25. Okay. Very interesting. So in the second case, the public is winning money, right? Public is looting money from the gambler, right? Because the average, the expected value of the experiment, anyone plays the experiment per game, the gambling house is going to give you $2.5. That's what this means, right? So that's weird. First of all, why should the gambling house donate money, right? That's weird. But interestingly enough, the variance went up. This is a good thing, right? This means that people will be getting different results. Good thing for you, of course, but bad thing for the gambling house. So, okay, then maybe you say, look, you have to use a loaded coin. You cannot use a normal coin, because otherwise how will you have fun? How will you have winning is more amount than losing? That's where the fun comes from, right? So then suppose we tweak the probability to 3 and 7, 0.3 and 0.7. Okay, suppose we load the coin. In this case, the expected value is -$0.5 and the variance is 47.25. This is middle ground. This is middle ground. So here the public is losing less money on average. Still the gambling house is making money because the expected value is minus 0.5. So gambling house is definitely making money. Variance is also higher. Okay. It feels like a random event, right? It will not feel as though everybody is losing the same amount of money. So this is the middle ground in this case. I would like to tell the audience that look, this is just two outcomes, right? H and T. When you work with mean and variance and events which have multiple possible outcomes, then you will see these concepts even more solidified, right? But I'm giving you the core essence, the meaning of these things. All right, meaning of these things. I'll not spend too much time on standard deviation. See, the table is exactly the same, so I'm just going to keep my video on because table is the same. Standard deviation is nothing but it's the square root of the variance. The only reason that we do this, it is easier to compare the standard deviation and the actual random variable. So when you do the variance calculation, the units are squared, right? So you take the square root, you get the original unit. So in this case, dollar is the original unit. You can think of standard deviation as some kind of comparable to the dollar unit. So $6 or something like that. You can think of it like that. Okay, not exactly, but it is comparable. Again, this will also be, this will be even more sort of expanded on in the continuous distribution session. Okay, you can see similar results for the standard deviation also. Same thing, like previously we saw the tweaking of the probabilities, right? And we saw the expected values of the games. Here standard deviation is nothing but square root. 36 square root is 6, right? So out of all of this, if you see these three tables, most people will sort of agree that we should tweak the probability to 0.3, 0.7, and this coin is unfair. The 0.2, 0.2 is unfair. Another way to tweak, obviously you can tweak the winning and losing values. That also something you can tweak. Yeah, whatever it is, you have to tweak something. That's essentially the learning that we are getting from this. Okay, so let's summarize. Is the gambling house looting the public? See, the gambling house is playing a game with the public whose expected value is loss of $2 for the public. The variance of the game is relatively low, or the standard deviations lower than other possible cases, right? This means that in general, outcomes of the game are closer to the expected value. If this was unintentional or done unknowingly, then the gambling house should have noticed this and you should have fixed the issue. Either you make it an almost zero mean game, like in this case, almost zero mean game, right? Or you at least increase the variance, right? But yeah, if neither of this is being done, then surely you can build a case and sort of, take it with the gambling house. So quick summary, what is an expected value? An expected value is the overall general expected results of an experiment. You are using theoretical probabilities in this case. It is more informative than a weightless mean. Of course, if you just take the values and take the mean, so $10 minus $5 divided by 2. What is this? This is $2.5. Clearly, this is far from the truth, right? $2.5 is wrong. Okay, it is way more informative than a weightless mean. Sorry. It's not just any number. Okay, if you perform an experiment consisting of multiple trials multiple times, you will sooner or later obtain the expected value. Okay, law of large numbers, LLN. Those are interested can Google this and read about this a little more. Now the only issue with the expected value is it does not give you information of the risk, right? So this is what we studied, variance, which tells me, are the outcomes going to be different for different people in general, or all the outcomes going to be similar for different people, right? Risk, variance, that is not given by expected value. That's given by variance and standard deviation. Okay, the uniform distribution. And we've already spoken about this, right? Examples of uniform distribution: rolling a die, asking the audience what color they like, what number you want to choose. There are, and in the real world, continuous uniform distributions also, there are a few market conditions, some things like that. We'll see that in the next session. Tossing a coin, all these kinds of uniform. What is the common thing in all of these activities? What is common? Each event is equiprobable. That's what is common. So suppose that your sample space has n elements. Okay, so this is the number of elements, small n, or outcomes, and these n events are equiprobable. So basically what I'm saying then, that the probability of each event is 1 divided by n. That's it. If I have 2 events, then it's 1 by 2, heads and tails. If I have 6 events, then it's 1 by 6, rolling a die, 1, 2, 3, 4, 5, 6, 1 by 6. If I have 52 events, like the card that we discussed, the shuffle deck of cards, then it's 1 by 52, right? So many of these things are uniformly distributed. And of course, this is what your distribution is going to look like. This is your probability mass function. Each of these events, E1, E2, E3, it is mapped to the value 1 by n. Okay. So not all real variables are uniformly distributed. This is something we need to keep in mind, but many of them are. Now in data science and mathematics and general scientific domain, this is the way we refer to it. Okay. So capital X, and then you have this tilde operator, UN. Okay. That's what I've written here. So how do you read this? X follows a uniform distribution of size n. This is how you read this statement. Okay. The random variable X follows a uniform distribution of size n. Okay. So yeah, here are some examples, right? Rolling a fair die, tossing a coin, picking a card, random number generation. So random numbers also use certain uniform distribution to generate randomness, right? Lottery analysis, this is also can be modeled as a uniform distribution. So wherever you have equiprobable outcomes, you can use the uniform distribution, right? Okay, quickly, we'll just look at the formula for expected value and things like that, just so we can solidify our understanding. Okay, and then we'll wrap up the session. So if let's say a random variable X is distributed uniformly and it belongs to the possible outcomes 1, 2, 3 ... till n. So these are the values. Okay, 1, 2, 3. These are the values. Then you can quickly calculate expected value. It's very simple. It's x into p of x. So 1 into probability of 1, 2 into probability of 2, 3 into probability of 3. But we know that each of the probability is 1 by n, right? Because it's a uniform distribution, each of the probability is 1 by n. So you're essentially just doing what? 1 plus 2 plus 3 ... till n divided by n. And this is an arithmetic progression. We remember the formula, n into n plus 1 by 2. And you have this n in the denominator. So finally the answer is n plus 1 by 2, right? The answer is n plus 1 by 2. So you can just use the formula for expected value in this distribution, and you know what is the expected value of a uniform distribution. So you can even quickly do this, right? What is the expected value of a coin toss? Very simple. Coin toss, number of possible outcome 2. So just put 2 inside here. 2 plus 1 by 2, right? 3 by 2. If you put heads as 1 and tails as 2, right? The answer will be 1.5. It's exactly between 1 and 2. Suppose you take dice 1, 2, 3, 4, 5, 6. What is the number of possible outcomes? 6. So just put the 6 in the end. 6 plus 1 by 2, 3.5. So very quickly you can get the expected value of a uniform discrete distribution. Similarly, and I won't walk through the proof, you can try to work it out yourself. Similarly, the variance of this random variable, if you name your values 1, 2, 3 till n, the variance will be n square minus 1 by 12. Similar derivation. Okay, you can use arithmetic progressions and all that. So quick example of rolling die, we already saw this. E of x will be 3.5 and the variance is 2.9. Standard deviation is 1.7. Again, I'm not going too deep into outside the meaning of what we discussed a while ago, which was expected value being the long-term result, variance being how these results look like for different instances of the experiment. This is what we learned in the second part, right? There is more actually. There's more to these things called variance, standard deviation, right? Those points will pick up in the continuous distribution session.
In today's rapidly evolving business landscape, machine learning and AI are no longer buzzwords. They are essential tools for staying competitive. Are you ready to lead the AI revolution in your industry? upGrad, in collaboration with IIIT Bangalore, brings you the Executive Diploma in Machine Learning and AI. This program is designed for ambitious professionals like you seeking to leverage AI for strategic decision making and innovation. Gain hands-on experience with cutting-edge technologies, learn from renowned faculty, and network with industry peers. Elevate your career, drive business transformation, and position yourself as an expert in AI. Enroll today and future-proof your career.
So the agenda for today, we'll obviously start off with continuous random variables. Last time we discussed discrete random variables. These are essentially just the metric or the variable that you are measuring in a certain experiment. It could be somebody's salary, it could be somebody's height, it could be the number on the dice, it could be any of these things that you're measuring. And essentially what you're interested to see how random are these and are there any patterns in their distribution, so on and so forth. And last time we saw something like the uniform distribution, and of course there are other kinds of distributions also, right? And a distribution for a random variable is essentially a pattern, right? It's so that we know that, okay, this value will come with this probability, this value will come with this probability, right? We know that. So that's what we studied last time. So this time we'll go with continuous. We will then study the uniform continuous distribution. We'll get a sense for exactly how do we work with probabilities when we are talking about continuous random variables. The uniform distribution, discrete one we saw last time, and this time we'll see the continuous one. So fairly simple distribution to get a sense of the operations and computations, things like that. Then finally we'll discuss one of the most important, if not the most important kind of distribution in data science and in general statistics also, which is the normal distribution, also known as the Gaussian distribution. Okay, so part one, continuous random variables. First of all, let's look at the type of random variables. As we just discussed, there are discrete random variables. It takes exactly one out of a finite or countably infinite number of discrete values. Okay, so some examples can be rolling a die and observing the number that comes up, tossing a coin and observing what symbol comes up, observing an inbox and counting the number of spam emails, right? All of these are discrete. So when you put, for example, the spam email, right, your x-axis is going to be 0 spam email, 1 spam email, 2 spam email, 3 spam email, and so on. There's no such thing as what is between 2 and 3, 2.5 spam email. That doesn't exist. But in the case of continuous RV, this process does not work, right? This continuous random variable takes exactly one out of infinite number of values, okay, on a continuous scale. So think in terms of choosing a person at random and recording their height. So one person may have 162 centimeter height, another person may have 163 centimeter height. So does that mean that nobody has 162.5? No, definitely there may be somebody with 162.5 centimeter height, right? Same, another example is choose a bottle of juice at random from a supermarket, record the amount of juice in it, how many milliliter, right? These have values which you cannot fix in discrete way. Okay, you cannot fix it in this discrete way. And of course salary also follows the same pattern. These are continuous random variables. Okay, so random variables that take value from continuous scale of values, height, salary, time, revenue, so on and so forth. Potentially there are infinite possibilities. So now comes the problem. See, in the previous session we were saying things like what is the probability that the number 3 comes up in my dice roll, or what is the probability that I have 2 spam emails in my inbox, right? It makes sense to ask that question, but I would like the audience to think right now, does it make sense to ask what is the probability that a person has height of 165.3 centimeter, right? Or let us say, what is the probability that a person has a height of 165.45 centimeter? Are these meaningful questions? Does it make sense? Can we keep asking these questions in terms of probability? The answer is no. Then the question is, how would the probability distribution of these continuous random variables be built, right? So we cannot keep asking these questions in decimal points, right? These are continuous numbers. So then how would we build a probability distribution? So before we go into that, let us start with a simple data set. So here I have a data set of height of Indian males. Okay, so here I have, as you can see here, this is the height. and all of these are in centimeter. Okay, the height is in centimeter. Each row represents one person, one Indian male, and you have totally 10,000 observations, that is 10,000 people. So the number of observations here is 10,000. Now, of course, since these are 10,000 discrete values, you can go ahead and find simple things like mean and standard deviation. These are things that you can easily calculate, right? You have 10,000 values. You can just use the normal formula, the very common formula to find the mean and standard deviation. So here we have a mean of 165 and standard deviation of 2. 10,000 values, but notice the values. Okay, 164.13 centimeter, 165.95 centimeter, and so on. So this is where I was asking the question, does it make sense to ask what is the probability of 164.13, what is the probability of 163.82? It doesn't make sense to ask this, right? First of all, let's try handling this finite amount of continuous data using histogram. Okay, so height of people by itself is actually a continuous data, but practically you have recorded 10,000 observations. So in front of you, there are 10,000 discrete numbers, but we all accept and understand that actually height itself is a continuous phenomenon. So height is a continuous variable. We have picked out 10,000 observations, right? Okay. So these 10,000 observations, how do we get a sense of the distribution? So one very simple thing which we do in data analysis is histograms, right? So these 10,000 observations, you can break it up into brackets or bins. Okay, when you do histogram, generally the word used is bin. So you can break it up into bins, right? And any height that falls within a bin, you can count that height in that bin. So this way you can compute the frequencies for each bin. Right? This is what we call a histogram essentially, right? It's a frequency distribution. And we studied in the last session that frequency and probability are basically the same thing, right? So let's see what this might look like. So we took the data set, okay? We took the 10,000 people height data set, and we used Python's Seaborn library, okay, to build a histogram. And there is a parameter where you can actually set the number of bins. Okay, so suppose we divide the data into 5 bins. This is the kind of data that you're going to get, right? So here you can see 158 to 160, almost like nobody, right? This is maybe 100 people out of 10,000. Similarly, 170 to 172 also very less. And as you get closer to the mean, so mean, I think we mentioned it was 165 centimeter. As you get closer to the mean, there seems to be some pattern, right? It's like you can actually draw some kind of line like this. Now at this stage, with 5 bins, the pattern is not obvious. So let us increase that to 10 bins. So as you can see here, now I have used 10 brackets or 10 bins to visualize those 10,000 heights. Immediately I can see slightly better pattern. Okay, so if I try to, in fact, you can even just try to join the midpoints of these bars. Okay, if you just try to join the midpoints of these bars, you will get a very interesting pattern. Many of you may have seen this shape before. So slowly you will see that the shape is being formed. So in the next diagram, I have used the same data and I have broken into 25 bins. So now if you try to see, there's a very, very clear pattern which is emerging, right? Looks like some kind of mountain. Generally, people refer to this as the bell curve. We'll come to the details later. So if you take 50 bins, right, you take the same 10,000 data, break it up into 50 brackets. Very, very clear pattern. Very, very, very clear pattern you can see. Okay, bell curve. 100 bins, of course, you can increase the bins also more, right? You have 10,000 data points. Why not use 100 bins, right? So again, you can see there's a very, very, very clear pattern which is starting to form, right? So let's go with the default bins. Okay, so in Python, you have an option to just go with the default bins. So in the default bin also, I am able to see this pattern. So let's just keep this pattern in mind. Okay. And of course, till now, if you see the y-axis, we are talking about frequencies. And I told you in the last session also, there's not much difference between frequency and probability. You just need to divide by 10,000, correct? So the total number of observations is 10,000. So y-axis, you just divide by 10,000. And of course, you will get the probabilities. So now you have a probability distribution. Instead of a frequency distribution, you have a probability distribution, right? Great. Notice that what have we done till now? So let's just summarize what we have done till now. Okay, we have understood that height of human beings is a continuous variable. We accept that between 162 and 163 centimeter, 162.5 centimeter, maybe somebody is there. 162.32 centimeter, somebody is there, right? We accept that it is a continuous scale. We also accept that, okay, I cannot sit and take the height of millions and billions of people. Okay, so whatever the people I have to break it into discrete brackets called histogram. The only good thing here is I can change the number of bins to see the pattern, right? This much we have done. Okay, so what are the advantages and disadvantages of this technique? All right, so the advantages are, look, we have control on the number of bins, okay, and we can specify that depending on our business problem. Perfectly fine. This is an advantage. A lot of data analysis actually uses this method, right? There is, it's not as if it's a less powerful method, right? You can definitely break your distributions into histogram buckets, and it's quite a powerful technique when you're doing in-depth, analysis in a discrete way. And if you're not thinking of your variable as continuous, that is, if you are in your problem statement, if you're thinking in terms of thresholds and brackets and that kind of thing, then of course you can use this method. But see, the disadvantages far outweigh the advantages. That's the main point here. What are the disadvantages? See, the more the number of bins, you are actually trying to store more data. The whole point is we had 10,000 observations, right? If you see the data set that we saw, it had 10,000 observations. That's a lot of observations. And in real life, we will be dealing with what? Many lakhs, many tens of thousands of observations. So that's a lot of data, computation and storage that you're asking for a simple distribution. Essentially, now that we know, okay, there is a very clear shape that is coming, why do I need to store all these numbers, all these different heights of the bars? So, the way that a histogram is displayed in Matplotlib or Seaborn, you are actually calculating the height of each bar, right? Each bar height is stored, calculated, and then displayed. So that's a lot of data computation. Whereas we know that, okay, there's a very simple but obvious pattern, right? That's a disadvantage. So there's a lot of data storage and data computation that is happening. Secondly, on a more academic and conceptual level, and even a bit realistic level, it does not capture the true behavior. So as I showed you before, we went from 25 bins to 50 bins to 100 bins. You can go to 200 bins, 300 bins, 400 bins, whatever, right? Each time your histogram is going to change. So you're not necessarily capturing the true behavior of this distribution. And however many data points you use, this distribution is still empirical. It is not theoretical. So whatever analysis you do is not universal. It is specific to your analysis. Okay, these are the disadvantages of the method that we saw. So let's, with that context, right, with that setting, with that setup, let us move into continuous probability distributions. So let's recall the empirical to theoretical in the discrete case. Okay, I'm sure that we all remember this example. So this is the rolling a fair die example. And I think this was n equal to 10, which means I rolled the die 10 times. And of course, we saw that, some numbers may come up more, some numbers may come up less, and so on. That is because you performed the experiment very less number of times. But as you perform the same experiment more and more number of times, as n approaches infinity, this is mathematics language, but practically this means what? N equal to 1000, 5000, whatever, right? You can actually take a die, take 1 or 2 hours out of your time and actually see this law in action, right? You can do it practically and verify for yourself. it will all stabilize into the same probability, right? 1, 2, 3, 4, 5, 6. They all stabilize into the same probability. This is called the uniform distribution. This is what we saw last time. The point I'm trying to make here is, instead of recording separate numbers for the different events, see, this is a very important point. In the first case, when n was equal to 10, that is the empirical case, we had to record each probability value separately for each event. But as we increase the number of trials, we saw that this random variable called number on top of a die, which is what we are referring to as the event here, this random variable, it actually follows a pattern. What is the pattern? The pattern is the uniform distribution. That is the pattern. Once you know that pattern, instead of recording 6 numbers, so on the left hand side you can see you have recorded 6 numbers. On the right hand side you have recorded only 1 number. And this is the power of the connection between empirical and theoretical distributions. It makes your analysis faster. Okay. So we saw this last time, right? You have reduced the all of this data into a simple formula. So here I'm showing you 6 data entries changed into 1 number, correct? My question is, can we do the same thing for continuous random variables also? So you must be thinking, you must be thinking, how is it even possible? So here we have taken 6 possible events, 1, 2, 3, 4, 5, 6. Okay, I roll the die, 100 times, 1000 times, whatever. And then I'm convincing myself, okay, I have equiprobable events. So 1 by 6, 1 by 6, 1 by 6. These are my probabilities. So I just need to remember that one number, 1 by 6. In fact, if you remember last session, I think the probability value was 1 by n, right? In the uniform distribution. So question is, can the same thing be done for continuous RVs? So in continuous RVs, what are we asking? We are asking, here it is 6 values to 1 value. In continuous, we are asking infinite values to 1 formula. Is that possible? The funny answer is yes, it is possible. Okay. Basically, think about this kind of data. This is our heights data. This is the height of the Indian males data. Okay. The question is, can we really have a theoretical distribution for this data? So if you remember the size of the data set, it was 10,000 data points. So question is, can we convert these 10,000 pieces of information into a single formula? Interestingly enough, the answer is yes. Okay. But before we study this distribution, we will first accustom ourselves to continuous distributions using a simple case, which is the continuous uniform distribution. Okay, which brings us to part 2. Now recall, in the discrete case we had the uniform distribution, and this is how we showed it. The random variable x follows a uniform distribution whose size is n, and then we have this probability function which we called probability mass function, which essentially maps the events to the probabilities. Now in this case, every event 1, 2, 3, 4, n, all of these are mapped to the same value, same probability, which is 1 by n. Now how did we get this 1 by n value? Look at the set of equations on the left. So it's very simple, right? You just take the sum of all the probabilities of the events, right? Probability of 1 plus probability of 2 and so on and so forth, right? And we know that this probability should be equal to 1. The summation should be 1. But we also know that each of these probabilities are equal, right? Let's call it P. So summation of P from I equal to 1 to n should be 1. This means P plus P plus P plus and so on, n times should be equal to 1. So n into P is equal to 1, P is equal to 1 by n. Very, very simple. This is the discrete case. Now in the uniform distribution, in the continuous case, what's going to happen? The graph is not going to have any breaks. Okay. So in the continuous uniform distribution, if you can see here, this is the distribution. If you can see this magenta purple color line segment, this is exactly the distribution. As you can see, there are no gaps, right? There are no gaps. There is only a range. So the distribution starts from the value A and goes to the value B. We will see an example soon, so don't worry too much about the algebra. The only difference is that first of all, it's a continuous line segment, right? So there are infinite values here. And secondly, we call it a probability density function instead of a probability mass function. Again, as I said, terminology just keeps changing, but everything almost means the same thing. So don't worry too much, but this is something we know. PDF, PMF, they all mean the same thing, right? You're trying to track the probability of a certain random variable. And the way to show this continuous distribution, the only thing that changed is x follows a uniform distribution in the range A to B. Basically, x can take any value from A to B. That's what we are trying to say. There are two values, A and B, and x can take any value from A and B. Now, given this, how would you find, first of all, how would you find the value of P in this case? Question number one. Second of all, how do we work with probabilities in this case, right? So in the discrete case, we used summation. If you go back, this sigma operator, this is what we used in the discrete case. I think it's quite intuitive for all of us that in the continuous case, we are going to use integration, right? Summation, the counterpart of summation in the continuous case is integration. The reason for that is something called limits, which is a mathematical concept. As you increase your number of computations to infinity, the summation is replaced by an integral sign, right? But on the surface, if we understand that summation becomes integration when discrete becomes continuous, that is enough for us. So first, let's tackle the value of P. Okay. And I'm sure we all remember some of these things at least, right? How do we find the value of P? Now, this is my uniform distribution. In the discrete case, the sum of the probabilities was equal to 1. In the continuous case, the area under the curve is going to be equal to 1. So this is actually a rectangle. I know I have done integration and all here, but this is a rectangle. So the area of the rectangle is very simple, right? This is B minus A. The length of this side is B minus A, and the length of this side is P. So you don't need all this integration. You can just say length into breadth is equal to 1. Why 1? Because probability works that way. It's a law of probability, right? Area under the curve equal to 1. So I can arrive at this last equation just by using the formula of a rectangle. But I've written the integration steps because when you look at other distributions which may not have such a simple shape, you should know what's going on behind the scenes, right? And the way we do this, you integrate from A to B and you put the PDF value, that is f of x, which is the PDF value. In our case, that is P. In the discrete case also, that's exactly what you did, right? In sigma, inside sigma, you put P of x. Same thing, sum of probabilities, right? In the continuous case, same thing, integral of the probability values, f of x, right? And you just go ahead with the integration. P is a constant, it comes out, you are integrating A to B dx, which is x, you put the upper limit, lower limit, you get B minus A, and therefore you get P equal to 1 by B minus A, okay? By the way, I should mention that I have shown you the first equation from A to B, but theoretically it's actually minus infinity to infinity, okay? The law of the probability says minus infinity to infinity if you integrate, then that is equal to 1. But if you see the graph, there is nothing before A, there is nothing after B. So instead of minus infinity to infinity, we are restricting ourselves to the range in which the distribution exists. Okay. Let's try to bring some example into this so that we can solidify our understanding. So consider, there's a city. Suppose there's a city and you consider the rice demand in the city in kilograms per head per month. Okay. So we spoke to many shopkeepers, we spoke to many dealers, okay, and we got an understanding. Everybody is saying that the demand in kilograms per head per month in a city of rice is uniformly distributed continuously between 3 and 6. So what are we trying to say here? The minimum that a person demands for rice is 3 kg and the maximum that person demands is 6 kg. And all the dealers and the shopkeepers and the grocers, they are saying, look, there is no difference in probability. Everyone, people are asking for 3.5 kg, they're asking for 3.2 kg, they're asking for 4.1 kg, whatever, right? So this is the understanding from the market, suppose. So then it is safe for me to say that, look, I am going to assume that the rice distribution is uniform. and I know that it goes from 3 to 6 kg. This is exactly what I've shown in the graph here, right? 3 kg is minimum, 6 kg is maximum, and anything in between is allowed. So that's exactly what the distribution shows. Now, based on our formula, it's very easy to find value of f of x. F of x as in p, right? The height of the uniform distribution. That's very easy to find. Just use either you use the integration or you use the rectangle formula, whatever it is. Area under the curve is going to be equal to 1. So if you apply the formula, you will get 0.33. Okay. This much is clear, right? So this height is 0.33. This much is clear. Now the question is, what is the interpretation of P in this case? See, in the discrete case, there was some interpretation, right? Because in the discrete case, when you said P equal to 1 by n, it essentially means what? Probability of event 1 is equal to P. Probability of event 2 is equal to P. Probability of event 3 is equal to P, whatever the value of P is. There was a simple interpretation in the discrete case. In the continuous case, what is the interpretation of P? There is no real immediate meaningful interpretation of the P value of this P in the continuous case. Okay. Rather, there is another way to interpret, which we will see. More importantly, how do you even compute probabilities? Basically, my question is, if I ask the question, what is the probability that a person demands 3.2 kg of rice? Is your answer going to be 0.33? Suppose I ask the question, what is the probability person demands 4.5 kg? Is your answer going to be 0.33? How many such values are there in the interval 3 to 6? Infinite values. Each of these probabilities is 0.33. How is that possible? It's not possible. So the interpretation of P is not immediately meaningful here. But what is meaningful? So in the discrete case, it was easy. You just select the x value, random variable value, and then you find the probability on the y-axis. This is the same for discrete uniform, discrete Bernoulli, discrete binomial. You take the random variable value on the x-axis, go to the y-axis, get the probability, and then you can add, subtract, whatever, right? In the continuous case, generally we talk about intervals. Now see, I have given a sub-interval C and D. If you see here, there's a C and there's a D. So we can try to ask the question, what is the probability that my requirement lies between C and D? This is a reasonable question to ask in the uniform case, continuous case. And if we do ask that question, again, you can just use your integration fundamentals and all of that, or you can use rectangle formula. Essentially, what you will get is the probability that the random variable lies between C and D. That is, my demand for rice is between C kilograms and D kilograms, right? It's an interval. That probability is actually equal to D minus C by B minus A. Okay, or you can say D minus C times P. Okay, and in fact, if you try to interpret this D minus C into P in the diagram, do you know what it is? It is actually the area of this rectangle. That's all it is. Basically, we are talking about the proportion of the total distribution, right? So what is D minus C? It's this length. This is D minus C, correct? What is P? P is the height of the rectangle. So what is D minus C times P? It's essentially the area under the curve for your subinterval. That's all it is. Okay. So either you can use the integration or you can use the rectangle stuff. But generally, as your distributions get more complex, integration is required. Right. Now let's try to bring this into perspective using the rice demand example. Okay. So we know that there's a demand of rice in a city. The rice demand value X is uniformly continuously distributed between 3 and 6 kilograms, 6 kilograms. Now I can ask the question, what is the probability that the person's demand is between 3.6 kg and 4.5 kg? I can ask the question in intervals, right? So suppose we pick out any random individual from the city. I can ask this question, what is this individual's probability going to be of having a demand between these two values? This is how we analyze continuous distributions. Okay, so then it's very easy to find. So using the formula or just using the understanding, all you need to do is find the area under the curve of your interval, correct? So 4.5 minus 3.6, into the height, which is 0.33, or you can use the formula d minus c by b minus a, whatever it is, right? So 4.5 minus 3.6 by 6 minus 3, you will get the answer as 0.3. Essentially, what we are trying to say is the probability that an individual's rise demand is between 3.6 to 4.5, that their demand lies in the subinterval 3.6 4.5 is 0.3 in this distribution. Okay, so in the continuous case, we talk about intervals. We do not talk about single values. Okay, that is the discrete case. So this is the key difference between discrete and continuous distributions with the normal distribution. So first, what we'll do, I told you, we saw the heights of the Indian males data, right? And then we asked the question that, okay, I have 10,000 numbers, 10,000 values, and I'm trying to put them into brackets. I'm trying to see is there a pattern, right? And then we saw, okay, there's a very, very nice, smooth, beautiful pattern. And we asked the question that, okay, in the discrete case, we used the connection between empirical and theoretical distributions, that is the law of large numbers. We used that connection to say that, okay, we can convert 6 values into one formula, right? 1 divided by n, for example, in the uniform distribution case, right? And we asked the question, can we do similar thing for this? Now, the basics of the continuous distributions we have understood from the uniform distribution, right? We just saw it a while ago. Let's answer that question. Okay, is there a formula for this distribution? So this is our heights data. Clearly there is some underlying pattern here, right? This much all of us are agreeing. There is clearly some very, very smooth, nice, symmetrical kind of pattern, right? This is generally called the bell curve. Okay. So what is that pattern? It's called the normal curve or the normal distribution. The other name for it is the Gaussian curve or the Gaussian distribution, right? It has many names: bell curve, Gaussian curve, normal curve, right? There are many names for this distribution because it's a very, very famous, popular, and important distribution. Okay. So we have a curve which looks like this, right? We have a nice curve which looks like this. My question is there a simple formula for this PDF? Is there a simple formula for this curve? Yes, there is a formula for this curve. Okay, that is called the normal or the Gaussian distribution function. And I would say do not get overwhelmed by the formulae. I will explain each and everything. Okay, first of all, let's look at this thing here. Basically, the random variable x follows a normal distribution with mean mu and variance sigma square. Okay, this is how we are going to read this statement. Okay, the random variable x follows a normal distribution with a mean of mu and a variance of sigma square. Great. What is the formula of the PDF for this random variable? So PDF meaning p of x equal to x, but this was in the discrete case, correct? Similarly, in the continuous case, you have the continuous formula. Now, if you see, the only variable in this formula is x. Everything else is constant. See, it looks like very confusing or anything, but there's only one variable here, x. This is the only variable. Everything else is constant. Your mean is here, your standard deviation is here, root of 2 pi is here, so on and so forth. Now, what is the reason for this 1 by root 2 pi? Basically, we add this constant to make the integration value equal to 1. It makes the area under the curve equal to 1. Because at the end of the day, this is a probability distribution function, right? PDF, it's a probability density function. Then it should satisfy the rule integration of f of x equal to 1. For that reason, you have this constant 1 by sigma root 2 pi. You can see that on the y-axis here, it's generally referred to as the amplitude. Okay, but it's just a simple constant which makes the area under the curve equal to 1. The variable is inside this exponent, e power minus half x minus mu divided by sigma, right? This is where the random variable actually is there. Okay, so this is called the Gaussian or the normal probability density function. And as you can see, We already saw that the curve is, very nice and symmetric and everything. It is actually symmetric about the mean. Okay, now let's put this into some perspective. If you remember the heights data, we had what, 10,000 data points with mean of 165 and standard deviation of 2, that is variance of 4. So the Gaussian formula or the Gaussian distribution for the heights data is going to be the random variable x, which is height of the Indian male, follows normal distribution centered at the mean 165 with a variance of 4. Okay, that gives you this exact distribution that you're seeing. And now if you take this blue curve and you put it on this orange histogram, exactly it will fit, right? That is exactly the curve that I'm showing you here. This curve, right? The curve that we have estimated, which perfectly fits this distribution of the heights. That is the curve that you will get using this formula. F of x equal to 1 by 2 root 2 pi. This 2 is nothing but the standard deviation. Okay, into e power minus 1 by 2 x minus 165 divided by 2. As you can see, this 165, this is the mean, and you can see here 2, this is the sigma or the standard deviation. Okay, and of course you can also see the y value here, but as we saw before, the y value by itself does not have any meaningful interpretation, right? If you remember the p thing that we discussed in the uniform case, by itself the p value doesn't have any meaning. We have to talk in terms of intervals, right? Okay, before we move on with that, one thing is very obvious here, that the center of the normal distribution is also equal to the mean, equal to median, and is equal to the mode. Now in this case I have taken 10,000 data points, so some bins seem higher and some bins seem lower, and you might say that the mode is to the left or mode is to the right. But if you increase this 10,000 to 1,000, let's say 1 lakh data points, then all these bars also will start going inside this purple curve, and you will get, almost perfectly it will fit inside the purple curve, right? So the mean and the median and the mode, all of them will lie exactly in the center, which is 165. And quite obviously the curve is symmetric. Okay, left and right, it is symmetric. The Gaussian curve is symmetric. Now see, this is where things get a little bit interesting in the normal distribution. The role of standard deviation. Okay, so mean, we know it is in the center. As you can see, I have put a straight line at mu. Please see the x-axis. This is mu. Mean is in the center. And we know that the normal distribution is symmetric. Left and right, it is symmetric. Okay, what is the role of standard deviation? Now, after appreciating and acknowledging that yes, this distribution is symmetric, and by the way, you can verify this from the f of x mathematics formula also. Okay, even from the formula you can prove that it is symmetric. After seeing that it is symmetric, I have put some things on the x-axis. See the x-axis. This side I have mu minus sigma, this side I have mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus 2 sigma, mu minus 3 sigma. Okay, basically I have taken random variable values, one standard deviation away from the mean on right side left side, 2 standard deviation away from the mean right side left side, and so on. Okay, the very interesting part, right, the very interesting part in this is that you can see percentages and proportions of these values exist in the intervals. So basically about 34% of your data will always lie between mu minus sigma and mu. This is true of all normal distributions. So my height case, the mean value is 165, right, for my 10,000 data points of height, and the standard deviation value is 2. What I am saying is 163 to 165, right, mu minus sigma comma mu, this interval, right, heights between 163 and 165. People with heights between 163 and 165 in a large population will always be 34% of that population. All normally distributed variables behave in this way. See, it is symmetrical. So now you can see on the other side also, mu to mu plus sigma. So 165 to 167 centimeter. People of height from 165 to 167 centimeter in a large population will always be 34% of that population. Okay, and see, these are all pre-calculated values. Okay, we'll come to how to calculate these values and all that. We will come to that. Okay, the answer is integration. Obviously, we just saw in the uniform case that we just need to integrate the area under the curve, nothing else. So mathematically speaking, the area under, for example, this shaded region, the area under this shaded region is 34%, 0.34. So if you do the mathematics, you will get 0.34. Okay, the area. But the interpretation should start making you think, a little bit. So if a variable is normally distributed, then this is always true. Okay, regardless whether you take the samples from different samples from the same population. Like if I have so India has what, 1.5 billion people, right? So from this, if I randomly select even, let's say 1 lakh, 10 lakh randomly, always this rule will be true. Okay, and of course there are more intervals. So from mu plus sigma to mu plus 2 sigma, it's about 13.5% of the population, and so on. Okay, these are pre-calculated and always true values. So in the heights, so basically you if you want to think of as symmetric intervals, then mu minus sigma to mu plus sigma, 68% of the population lies here. Mu minus 2 sigma, mu plus 2 sigma, 95% of the population lies here. Mu minus 3 sigma to mu plus 3 sigma, right? 3 standard deviations away on both sides, 99.7% of the population lies here. Okay. So what does this mean in the heights case? So as you can see in the diagram, and here are the numbers, people between 163 to 165 centimeter height, 34% of the population. Therefore, the probability that a person will have between 163 and 165 centimeter, what's the probability? 0.34, right? That is the way to interpret this normal distribution, correct? And of course, you can take any interval and you can answer these questions. Okay, so see, till now you were using pre-computed values. Okay, these values actually came from integration, of course. Now I think it's an understatement when we say integration of, what was that, e power minus 1 by 2 x minus something something square dx. Of course this integration is going to be complex, right? So that's why we have those pre-computed values. In fact, if you Google right now, just Google normal distribution, you will get the same numbers. Just go to Google Images, okay, and just Google normal distribution, okay, and you will get these numbers: 34, 13, 2, 99, 95. You will get the same numbers. So these are all pre-calculated, okay, and we agree that this integration is messy, which is what I've written here. The integration becomes very messy. And so what? So now if I ask you the question, what is the area under this part of the curve? So as you can see, I have two numbers. I have 162.3 and I have 168.6. And if I ask you, what is the probability that x lies between 162.3 and 168.6? How are you going to do it? You don't have the pre-computed values, right? This is not exactly minus 1 sigma, 2 sigma, right? It's random two numbers. We need to put the value in the integral, right? We need to put these here. I need to put 162.3. And here I need to put 168.6, and then I need to integrate. Of course, this is messy. This is messy, but since this is universal, statisticians and data scientists have universally come up with something called the z-score and the z-table. We will come to this very soon. This is kind of like a logarithm table. If you remember in high school and all, we used to use this log, anti-log tables, right? Now, actually calculating log to the base of 2 of 23 and everything, the calculation is so complex. What is the meaning of log? 2 power x is equal to 23, right? So if 2 power x equal to 23, then x is equal to log to the base 2 of 23. Now to calculate this, how are we going to do it? We used to use log tables, all pre-calculated values. Since the normal distribution is so universal, and again, I will give the example soon. Since the normal distribution is so universal, statisticians, mathematicians, data analysts, data scientists have come up with a universal table of these values. Okay, so we'll get to that very soon. Before that, we should understand the implications of this. See, what are the normally distributed data in real life? A lot of the variables that people deal with in different fields, be it medical, transport, finance, economics, governance, a lot of these variables are normally distributed. It is something that naturally arises in nature. The normal distribution naturally arises. So heights are normally distributed, birth weight is normally distributed, job satisfaction measure, these are normally distributed, runs scored in cricket matches, age of people, salaries, IQ scores, so many variables in so many domains are normally distributed. Not uniform, not anything else, normally distributed. This bell curve. Okay. So my question is, does the previous method of simplifying this vast amount of data safely into single formula? Now, what is that single formula? In the heights case, where was the formula? Where was the formula? Let's see the formula in the heights case. In the heights case, this was the formula, right? F of x equal to 1 by 2 root 2 pi e power whatever, and you put the mean value and the standard deviation value in the correct places. Okay. Does this work for all these other things? Age, birth weight, salary, and everything else? Yes. Answer is yes. Exact same formula works here. Some examples, and I've given the links also. Age of Nobel Prize winners. As you can see, this is normally distributed. Okay, the mean seems to be around 60, and I guess the standard deviation is maybe 10, 15, something like that. From this distribution, looks like 15 or something years is the standard distribution. Okay, age of Nobel Prize winners. There was one study on the length of housefly wings. Okay, the length of the wings of housefly. This is also normally distributed. Okay. Then there is one study on the distribution of shoe sizes, right? So this is also normally distributed. In fact, this link, I think there are many more examples. You can check that. Salaries also are normally distributed. Now this graph is a skew normal. Okay, this is what we call skew normal. So skew normal analysis is a bit out of scope of this session, but suffice to say that if I take care of some of these outliers, if I just take care of some of these outliers, the remaining data will become perfectly normal. If I just remove some of these outliers, remaining data will become perfectly normal. Okay, so many of these real variables are normally distributed. And interestingly, and this is the funny part, this is actually why are we studying all this? Why did we study discrete distribution and empirical and all of that in the last session? Then why did we study normal distribution, continuous? Why did we study all this? This is the main thing. There is something called the central limit theorem, which you will study in the next session. I believe the session is dedicated to central limit theorem. There's a theorem, okay, in mathematics statistics, which ensures that sampling distributions are normally distributed. In other words, even if your population is not normally distributed, you can devise your sampling technique in such a way that the sampling distribution is normal. So there is a lot of motivation to study the normal distribution. Even if your data is not normal, you can work with it in assuming the sample is normal, which not an assumption, sorry, making the sampling in such a way that it is normal. Okay, so more on the central limit theorem in the next session. Okay, but suffice to say that this normal distribution is almost everywhere when you deal with real variables. Okay, so now there's an interesting thought right now. Shoe size, age, height, salaries, cricket runs, whatever, right? There are many real variables which seem to be normally distributed. Now each of these has a different mean and variance. Yeah, we saw height's mean was 165. I think the something was mean was 60 and different variance values, right? Can we transform all of these normal distributions so that a single formula can represent all these? So right now we need to specify the mean. That is, in height's case, 165 centimeter was the mean and standard deviation was 2. And in another case, the mean was 60 and the standard deviation was 15, age of Nobel Prize winners, right? But since all of these have the same pattern, is it possible to transform to some kind of new distribution with single formula for all these distributions? The answer is yes. Okay. And what are the motivations? Why should we do that? See, you can start comparing variable distributions more easily. Okay, cross comparison becomes very easy. That's one motivation. It allows for simplification of computations. If you saw those values initially, 68%, 95%, and all these values, they are just 2-3 values for 2-3 intervals of this thing that we call the Z table. We'll come to that soon, right? Here I've written Z table. So it allows for making the Z table in the first place. Once we have this universal kind of distribution formula, from that we can generate Z tables. I'll show you how to use that also. And it also enables the generalization of statistical rules. So data scientists and statisticians, when you do hypothesis testing, which you will be dealing in the next week, there are something called significance thresholds. Okay. Now, these are many of, and all of these normal distributions, if there is a single formula or a single distribution which can represent all of these, then you can have a single significance threshold. You know, I am happy with 95% confidence, I am happy with 90% confidence, whatever, right? Some of these things you will study in the future sessions. So there are many such motivations to try to find this formula, and that's called standardization. This process is called standardization. Okay, and the mathematics on the screen may look very complex and messy, but it's very simple. The main thing that we need to see is the substitution in the middle. So on the left hand side you can see this x, that is the original random variable x. So that is the height of the person. It could be 163, 167, whatever. That is the x. Mu, that is the mean of your data. In the heights case it is 165. Okay, and sigma, that is the standard deviation of the data. In your heights case that is 2. All you need to do is you need to make this substitution. Okay, this x minus mu divided by sigma, which is there inside this formula here, substitute with z. And of course internationally z is pronounced z, which is why we call it z score, z score. So please don't mind, sometimes I'm saying z, sometimes I'm saying z. Okay, so you need to make the substitution, and this is exactly what we call the z score. Z score is nothing but x minus mu by sigma. Okay, it is a transformation. You're converting x to z. You do that, and then interestingly your distribution now has 0 mean. Why it has 0 mean? Try put x equal to 165 in this. 165 minus 165 is 0. So wherever originally you had 165, now it is 0. Okay, so the new distribution is centered at 0, and the standard deviation sigma becomes equal to 1. Okay, it's not 2, it's not 15. So standard deviation was 2 in the case of height, standard deviation was 15 in the case of age of Nobel Prize winner. Now with this distribution, all standard deviations for all of these different variables become 1. So the full mathematical proof is out of scope, but there are some links that I've given. So I believe you'll be getting the PDF. So in your free time, you can go through the links. Okay. What does all this mean? So let's recall the normal distribution for the height data. So as you can see here, it has mean of 165, variance of 4. Okay. And in the formula, we have x minus 165 by 2 here. That x minus 165 by 2 replaced by z. And if you replace by z, if you do the transformation, then your distribution, the normal distribution, becomes something that we call standard normal distribution. Okay, standard. It's there in the word itself, right? Standard. It is standard. Across all the normally distributed variables, it is standard. They all follow the same distribution. And this distribution is independent of the mean and the variance of your original data, right? Because the mean of this distribution is 0. It is centered at 0 always. And the variance is 1, or standard deviation is 1 always. So in the x-axis, you don't have minus 1 sigma, minus 2 sigma. That is mu minus 1 sigma, mu minus 2 sigma. No. You now have 0 minus 1 into 1, which is minus 1. Then 0 minus 2 into minus 1, which is minus 2. These are very, very, very simple values to work with. They are also universal. Okay, everything on this slide is not just representative of Indian male height. This is true for any normally distributed data. Okay, great. Now that brings us to something called the Z table. So we have seen that many real variables more or less follow the standard normal distribution. Now, if we have a quick way to calculate the probabilities under the standard normal curve, right? So basically in this curve, if somebody can give me a very fast way, quick way to find the area under the curve for different intervals, right? For different intervals, if there is a simple way to calculate these probabilities, then I can answer a lot of questions. Many questions can be answered. Why? Because many real variables are normally distributed. So I can answer questions like, what's the probability that an employee of a certain company has a CTC between 5 LPA and 15 LPA? Random question, but I can answer it. What's the probability that a random student I select for a candidate for basketball team has height between 163 and 166? Again, random question, but I can get the answer, right? All of these are normally distributed, and if I have a simple way to calculate these areas, then I can answer these questions confidently. Okay, now let's go back to the heights problem, in which I told you that we had these two two values, 162.3 centimeter and 168.6 centimeter, and that time we did some quizzes on 163 to 167, 161 to 169, the very common intervals. But what about random intervals, right? So we said, okay, integrating this is going to be messy. So how do we calculate this probability? So basically the question is, what's the probability that an Indian male has a height between 162.3 centimeter and 168.6 centimeter? That's the question. If I had a quick way to get those probability values, then I can answer this question. Okay, so let's go to this step by step. The first thing that you need to do is standardize your normal distribution. So as you can see, the original value was 162.3. Okay, how do you standardize? Subtract the mean, divide by the standard deviation. Okay, x minus mu divided by sigma. This is called the z-score. Basically, I think, yeah, there's a mistake on the x-axis. It shouldn't be x, this is z. Okay, the x-axis variable is now z. If I standardize it, it will become z. Okay, so anyway, minor thing, but I hope the point is very clear. The x-axis, originally it was the original variable. After standardizing, it's now z. So for all the different distributions, you have the same x-axis. For height, for housefly wing length, for age of Nobel Prize winner, for anything normally distributed, after this transformation, x-axis is the same, z. Okay, minor mistake on my part. Please ignore that. The x-axis should be z. Okay, so how do you standardize? X minus mu divided by sigma. So 162.3 original value minus mean 165 divided by sigma 2. This gives me a z-score of minus 1.35. Okay, then for what about 168.6? 168.6 minus mean 165 divided by 2, standard deviation. This gives me 1.8. So the first thing you do is standardize this. Next, what is your question? You want the area between this, right? Now, in the normal case and in the standard normal case, both cases, area under the curve, total area is 1. So whatever area you calculate here is the probability in the normal distribution also. So basically, I've just divided this into two parts, which is easier to do the calculation, right? So I have one region here, let us call it region A, and another region here called region B. So basically, my objective is to find A plus B. What is the area under A plus B? That is going to be my probability value. Okay. Now, this is what we call a Z table. Can everyone tell me if it's somewhat visible at least? See, the Z table is actually very large. Can you please let me know in the chat, are you able to see the numbers in the table? Yeah, visible? Great. So how do we read this table? Okay, how do we read this table? What we need to understand here is, you might be wondering, the first value in the table is 0.5. That itself is a bit weird, you might think. Why is it not starting from 0? Right? Why is it starting from 0.5? The reason is that the normal curve is symmetric. It's symmetric. Okay. And your z-score is centered at 0. So what the table is showing is additional to the left hand side. Okay, so this whole thing, right, this whole thing on the left hand side, whatever the area is under the blue curve, is 0.5. Obviously the total area is 1 and the curve is symmetric across the mean, so left side of the mean has to be 0.5, obviously. But the mean in the standard normal case is what? It is 0 because of the standardization process. Therefore, if you see here, for z equal to 0, for z equal to 0, the number starts from 0.5. It is giving you complete area from left hand side up to the z point. So completely from left hand side up to z equal to 0 has to be 0.5. Correct? In this case, completely from left hand side up to z equal to 0 has to be 0.5. So that is what you are seeing in the first cell, 0.5. So how do you read this table? If you go left to right, you will say, for example, just take the first row, 0.0, then the next one is 0.01, then the next one is 0.02. These are the z-score values. Okay. If you take the second row, it starts with 0.1. So then when you go to the right side, you will get 0.11, 0.12. So these are the columns. As you can see, it says plus 0.03, right? So choose the first decimal point vertically, then choose the second decimal point horizontally. Okay, that is how you read the table. So essentially it is giving me the area under the curve from minus infinity, that is full left, to the z point cutoff. And we know that the curve is symmetric, so we should be smart enough to use this table. Let's look at how to do the calculation here. Okay, so let's just concentrate on A for the moment. See, if I flip the curve left and right, still the table will be the same. So minus 1.35 and 1.35 both will be symmetric. So where is 1.35? 1.35 will come somewhere here, right? This is going to be 1.35. So for me, if I want to calculate this part, I need to do what? I need to calculate basically this part. Okay, let me just this is a bit critical part, so I'm going to do this visually. Give me a second. Yeah, so as I said, it is symmetric left and right. So let's just take this, right? I need to find out this area, and then I have to subtract 0.5 basically. Now you must be asking, the z table is giving me from left hand side, will I get the same value from right hand side? Yes, the standard normal distribution is symmetric. So if you split if you switch this, and instead of minus 1.35, if you go for the value 1.35, you will essentially get the same result that you're looking for. So from the right hand side to the z value, in this case what it is, minus 1.35, is the same as from left hand side to positive 1.35, same. Okay, so let's go back to the z table. What was the value? 1.35 is the z value. So where is 1.3? Where is 1.3? Here you can see 1.3. There's the, go vertically and search for 1.3. Then you have to add 0.05. So this column, right? This is plus 0.05 column. So essentially we are looking at this value here. Okay, this is the area under the standard normal curve from full left to positive 1.35 or from full right to negative 1.35 because of the symmetricity property. And what is that area? 0.91149, and that is exactly what I have written here. Okay, so from the full right up to minus 1.35, that value is 0.91149. It's a probability value. Okay, cumulative probability value. Minus what? Why minus 0.5? Because I need to cut off this value, right? First I need to calculate A, so I need to cut off this value. And what is this value? This is the middle value. from extreme right to 0 has to be 0.5 because total is equal to 1. Very simple. So the area under the part A is 0.91149 minus 0.5, which is this value here, 0.41149. Okay, so basically 41% of my population is in the region A. Okay, so let me just erase this part so that things are a bit clear. Okay, right. So I now know that 41% lies between the center, that is 0.5, and the z-score minus 1.35. Basically, z equal to 0 to z equal to minus 1.35. I have 41%, 0.41149. Same logic for 1.8. What do you do for the region B? Calculate the area under the curve from negative extreme minus infinity to 1.8 and then subtract 0.5. That's all. So can we see the z table and see how to do this? So go vertically, you will find a row which is z equal to 1.8 and the value, and it is 1.80, right? It's not 1.81, 1.82. So go for the first column and the value here is 0.96407. All right. So that's the value I have here. And then you just subtract 0.5 because you're trying to find only the area under B, and the z table is actually giving you from negative extreme to 0.8, right? It is giving full this much area it is giving. So we have to subtract the 0.5, right? This part is 0.5 and that value is 46%. Okay, so therefore the area under the region B is 46%. So now I have both my values. The area under A is 41%, the area under B is 46%, and you can see the computations on your screen, right? So we have here 0.41149, 41%, 0.46407, 46%. You just add it and you get 0.87556. Okay. And now all you need to do is you need to essentially just go back to your basic distribution, the normal distribution, and you can make the claim that about 87.56% of Indian males have the heights between 162.3 centimeter and 168.6 centimeter. In other words, we have essentially found out the area between the value of 162.3 centimeter and 168.6 centimeter. And what does area under the curve mean? It is essentially the probability. The probability that a random Indian male, you can see the statement in the bottom, probability that a random Indian male has a height between these two values is about 87-88%. Let's look at a quick use case. See, suppose you're a data scientist, okay, or a data analyst working for a high-end clubhouse, okay, and suppose that the clubhouse requires 20 security personnel or 20 security persons, and they have received 2000 applications. Okay, you need 20 security people, you have received 2000 applications. The clubhouse is asking you to come up with a suitable height threshold. Now, for some reason, the clubhouse is thinking that height is a good feature or good variable with which to threshold the job applications. Of course, this can be different in your domain, right? If your domain is different, then you might be using other metrics, okay, salary, experience, whatever. In this case, the clubhouse is saying use height as a threshold and come up with a suitable cutoff so that you reduce these 2000 applications to 50 applications. Maybe because clubhouse does not have the time, okay, they cannot go through 2000 applications. They saying, okay, give me 50 applications. How do you go about doing this in a very fair way, right? So let's take the height distribution here. Okay, let's take the height distribution here. Now what does the normal distribution tell us? We have 2000 applications. The mean height is 165 centimeter. We know that the normal distribution is symmetrical. Therefore, I can confidently say that about 1000 of the applications have height less than 165 centimeter, and about 1000 of the applications will have height greater than 165 centimeter, half. Okay, because 165 is the mean. And these 2000 applications, the heights of the security people, the 2000 applicants, is following the normal curve. So if I set a minimum threshold of 165 centimeter, I can cut off 50%, right? So I will say everybody below 165 centimeter height, do not take the application. So out of 2000, you are left with 1000. Great. But what was the question? The clubhouse wanted me to reduce 2000 to 50. So obviously this threshold is not enough. Okay. Suppose I go to 167. If you remember, 167 is mu plus 1 sigma. So my mu is 165, my standard deviation is 2 for the heights data. So 167 is basically mu plus 1 sigma, 1 standard deviation further. And we know that the chunk has 34% or something, right? If you remember the normal distribution chunking of plus 1 sigma minus 1 sigma, about 34% after the mean. So if you set the min height at 167 centimeter, then 50 plus not 34, I don't remember exactly, but we should check the number. Okay, if you set the minimum height at 167 centimeter, you will be left with 32% remaining applications. Okay, in fact, let's essentially go back and check. I believe it is 34. Yeah, 34%. Okay, so 50% is here and 34% is here, right? Okay, there's a small error in this slide. Yeah, forgive me, there's a small error in this slide. So this is 50% and this is 34%. Okay, so the remaining is not 32. That's my bad. Okay, it should be 50 plus 34 is how much? 84%. So remaining will be 16%. Okay, so if I move the minimum height threshold to 167, which is 165 plus 1 standard deviation, 165 plus 2 is 167. The total area under the curve till 167 is 50 plus 34, 50% plus 34%, 84%. So I'm removing 84% of the 2000 applications. 16% will remain. So it's not 640, that's a mistake. 320 applications will remain. Okay. Again, what was the original question? 50 applications. So let's move this even further, right? Let's go to mu plus 2 sigma. So 165 plus 2 into 2, which is 2 into sigma, which is 169 centimeters. So suppose I set my threshold at 169 centimeter, and I say everybody less than 169 centimeter, just reject the application. Now again, the normal distribution tells me what? It tells me that only 2% afterwards will be left. So about 98% of these applications we are rejecting if we set the threshold at 169. So now how much will remain? 2%, which is 40 applications out of 2000. Okay, but the original question was 50, not 40, right? So I went too far. Okay, so till now we are doing trial and error. Okay, but should we always be doing trial and error? Like, see, again, for example, if I just say, okay, 169 centimeter became too much because only 40 applications remained, so let me reduce that a little bit to 168.5 and see what happens. And if you do reduce to 168.5, what you should do? Standardize this value. 168 minus, you just do the standardization. 168.5 minus 165 divide by 2, go to the z table. I've written the steps in the bottom. Go to the z table, calculate z score, get the probability, and you do all of these things. You will essentially get 80 applications. Okay, so if you use 168.5, you will find out that 96% is on the left side and 4% is on the right side. But should we be doing trial and error so much? No, there is actually a very easy way to figure this out. How do you do that? See, the full thing is in this slide. We want 50 applications out of 2000. What's that proportion actually? 50 by 2000. So if you do 50 divided by 2000 into 100, you will get 2.5%. Basically, we want to retain 2.5%. So we need to find a z-score, that is, we need to find a height threshold that covers 97.5% on the left side. So we need a z-score that gives me area under the curve of 0.975. Now you can of course look at the table and see which z-score gives me 0.975. Okay, let's go see the original z table. Where is the z table? Yeah, here's the z table. So I want 0.975. You know, search the z table. Where is 0.975? Here it is. See, somewhere down in the corner bottom right, you can see 0.975. Which z value is giving me 0.975? Just check the row and the column, 1.9 and 0.06. So 1.96. So by quickly looking at the z table, I know that the z-score of 1.96 gives me 97.5% on the left side. So I know that the z-score I'm looking for is 1.96. Now remember the transformation formula. Z is nothing but x minus mu by sigma. So just rearrange the terms. What you will get? X equal to mu plus z sigma. That's all. So you can go from original variable to z-score. Same way you can go from z-score to original variable. Okay. So let's revise this. Okay. We want 2.5% to be retained. That means we want 97.5 to be rejected. Therefore, we want the z-score whose area under the curve on left side is 97.5%. That z-score from the table is 1.96. Using that, I can convert the z-score back to my original using the substitution formula, z equal to x minus, in this case 165 divided by 2, right? 165 divided by 2. And what is the z-score? 1.96. So x is equal to 165 plus 2 into 1.96, which gives me 168.92 centimeter. So if I set my height threshold at 168.92 centimeter, I am more or less ensuring fairly that my 2000 applications reduce to exactly more or less 50 applications. Okay. So if I set the threshold at 168.92, this gives me 2.5% on the right side, which translates to 50 out of 2000 applications. Okay. So of course you can extend this to any domain, right? It's not just number of applications or anything like that. Heights of people, you can expand this to any normally distributed variable and make these kinds of decisions. Okay. All right. So I hope we have understood the use case, and I hope that all of you can take what you learned from here and go and see with your own domains, with your own kinds of data, where these normal distributions are arising and how decisions are being made using the distribution. So just some closing comments from my side. Many real data are normally distributed, like height, birth weight, and so on. We saw that. Normal distribution can be used to analyze data and provide more confidence in decision making, which is what we saw, a very simple use case just now, right? It will be different in different domains, but it provides confidence in decision making. Okay. And not just that, the normal distribution plays a very central claim in something we call inferential statistics, okay, which is making claims about population based on sampling, okay, which is the central theme of your next session, in which you will be learning central limit theorem and things like that. So I mean, the normal distribution is quite important in statistics, data science, for all these reasons. Okay.